Hello everyone and welcome to the Malware Analysis course. In this course, you will gain the knowledge and experience on dissecting malware. My name is Riel Kosaev. I'm the author of the Antivirus Bypass Techniques book, founder of Malware Analysis Co. Myself, malware researcher and red teamer for over 13 years. Also a YouTuber, blogger, and lecturer. You can follow me on the Twitter handle, Malfazer. The agenda for the course. So first of all, in today's video, we'll understand what is malware. Then we'll go and understand types of malware and what is malware analysis and why is needed in the world. Then we go into some malware analysis methods that we go through the course. And of course, you can always visit Malware Analysis Co. website for gaining more resources, tools, and read about my latest research. So what is malware? So malware is derived from the word malicious software, and it plays a part in most computer intrusion and security incidents. Most of the intrusion and cyber attacks are based on malware. It can be a ransomware, info stealers, remote administration tool, or in short, rat, and other very sophisticated stuff. Let's continue to the types of malware. The first malware is virus or worm. So virus is a malicious code that can copy itself and infect additional computers. There are those viruses that can copy themselves or a malicious code into other files in the same system, and worms can propagate even to other computers. Then we have also Trojan horse. Trojan horse is not literally a malware, but it's more a type or a capability that is becoming part of the malware that an attacker is writing. For example, an attacker can write a war malware or ransomware and make it look like a legitimate malware. And the fact that the malware looks legitimate makes it a Trojan horse. Then we have the ransomware, which is a type of malware that prevents users from accessing their system or personal files and demands ransom payment in order to regain access. Of course, ransomware will encrypt files and other type of artifacts in order to prevent users from using their system, and of course making a great harm to organizations. Then you have also what's so-called rootkits, which are malicious code designed to conceal the existing of other code or other malware. Rootkits are running in the inner recesses of your system, in places like the kernel itself, and in several cases even conducts attacks like DCOM or direct kernel object manipulation in order to manipulate kernel objects or structures in order to evade defense systems and also to hide other malicious code. And we have also backdoors, which are malicious code that installs itself onto a computer to allow the attacker an access to the system, if it's via opening a listening port or installing a service as a persistent mechanism, and so on. We'll, of course, will see all of those in our course. We have also other type of malware like fileless malware, which is a malicious code that executes in the memory and persists as a known file object like the registry, scheduled tasks, and more. We have adware, which its main purpose is to inject and display ads in the browser or even monetize ads by using your browser but without actually presenting the ads to you. So it's all of its code and ads that are injected into your browser is under the ground. You can take one of my blogs that I wrote, for example, Schleyer, which is a macOS malware, and you can see that it actually hides the ads but makes money. Of course, if you want to understand how it makes money, you can read it on the blog. You have other type of malware like spyware, which basically spies on the end user. Mostly they're attacking cell phones and smartphones, but there are spywares also for computers. They want to know about your location and the apps that you're using messages, SMS, and so on. And of course, we have keylogger, which is a malware piece of code which logs keystrokes, mouse clicks, and even takes screenshots. You can see my video on dissecting Ardamax keylogger, for example, on a keylogger, which not only takes your keystrokes, but also screenshots and other stuff. So what is malware analysis and why we need it? In short, malware analysis is the art of analyzing and research of malicious software behavior and patterns. And in this course, I don't want to make things theoretical, but I want to go as much as possible and as much as practical as we can, and show as much as more examples as I can. And the way that I will present you the course is with a lot of practical examples, and I don't want it to be theoretical, but more practical. But of course, in order to understand the practical aspects, we need to understand the theoretics behind it. So after we understood in general what is malware and what is malware analysis, let's go into understanding some different malware analysis methods. So the most basic malware analysis method that a researcher or an analyst can use is what's called an automated analysis. An automated analysis is based on what's called a virtual sandbox, which is a virtualized environment with an operating system installed on top of it. It can be a Linux-based, macOS, Windows-based operating system. And in top of the system, you can basically drop and execute any type of malware you want. It can be a document file, PDF, Word, can be an executable, and so on. And at the end of the analysis, it will present you a report with all of the indicators of compromise, malicious functions that were used, and other interesting and valuable stuff. The downside of automated analysis is there are malware that have the capability of detecting the presence of automated sandbox and can basically evade them. So if you run a malware inside an automated sandbox and you see a very short report, you can rest assured that this malware detected the presence of an automated sandbox. Then you have what's called static analysis. This is where you analyze malware and its artifacts, you see its strings, functions, and other things without actually executing or running it on the system. After you understood the story behind the malware in its static level, you can go into the dynamic analysis. And in the dynamic analysis, you actually execute the malware. So if in the static analysis, you gain the foundation and the stuff that you can expect from the malware, then you can think of what will possibly happen when you will execute the malware in the dynamic analysis phase. So it's not that you go first into automated analysis, then you go into static analysis, then into dynamic, and then into reverse engineering. You can go in whatever way you want. So in cases, for example, that you research a malware or analyze it and you see that it's packed, you don't really have too much of a choice to reverse engineer the packing mechanism and extract its payload, or to basically execute the malware and see how it behaves on your system. So you will not always have the ability to statically analyze the malware and learn everything from it. So basically think of it like this. Malware analysis is a very, very dynamic and open-minded profession or thing. It's not like you're going into a penetration test and you have a very, very specific methodology. Here you can sometimes start with static analysis and sometimes even start with dynamic analysis and then get over back to automated analysis, or even just start with reverse engineering. It very depends on your own methodologies, on your own way of thinking. Of course, the last step or the last stepping stone is reverse engineering, which is the most or the harder thing to do, but you have to sharpen the skill. And reverse engineering is a skill that can be developed for years and years. So if someone will tell you that you can be a reverse engineer in a couple of months, is a liar. So of course, for each of those methods, you have a very short and straightforward explanation. I will put those presentations as part of the course. Feel free to visit Malware Analysis Co. anytime for new research blogs, new tools, and other interesting insights. Thank you very much and have a great weekend. See you in the next video. Hello everyone and welcome back. In this video, we'll go through the procedure of a malware analysis lab setup. First of all, we'll go through the lab topology. We'll choose our sandbox environment. We'll go through installing and optimizing Windows 10 for our malware analysis lab. We'll do this actually in a different video. We'll deploy Flare VM, which is the suite of all the necessary malware analysis tools, and install the connectivity between Windows 10 and inetSIM or Remnux virtual machine. So let's go through our lab topology. Our lab will be very basic and straightforward. In our Windows Malware Analysis OS, we will configure an IP address, a gateway, and on top of subnet mask, 24 bits. You can choose your own net mask and IP address. It doesn't really need to be the same as presented here. The malware analysis machine will be connected to another machine, which is our Linux inetSIM or Remnux in our case, which will include all of the necessary tools for intercepting network connections. So basically, the gateway of the Windows malware analysis will be the Remnux machine, and the gateway for the Remnux machine will be our actual gateway on our physical network. So in our Remnux machine, we'll have two interfaces. We'll have the NAT or bridged internet interface, and the second one will be VMNet. VMNet will be used for the connectivity between the Windows Malware Analysis OS and the Remnux machine. Of course, we'll see everything and how it is configured in our next video. Now, you can use any type of sandbox that you are regular with. My type of virtual machine sandbox environment or hypervisor will be VMware. For others, it can be VirtualBox, Parallels, Chemo, and others. In our next video, we will show the practical procedure and how to deploy Malware Analysis Lab from scratch. Thank you and see you in the next video. Hello everyone and welcome. In this video, we'll see how to deploy Flare VM on a Windows 10 machine. So as you can see, we have a brand new Windows 10 machine deployed. One of the first things that I like to do before deploying Flare VM is to disabling basic stuff like unneeded services and so on. So let's go into services.msc and disable services like fax, another service like Xbox, and of course there are a bunch of other services to be disabled. For better optimization, you can check for yourselves and research more about it. Next thing to do is to go to the settings and privacy and disabling all of those settings. As you can see, cameras off, location, count info, all of those, and make sure also the file system tab is off. After we validated all of this, we can go to the Flare VM GitHub page. First of all, let's download the PS1 file. Download it. And now let's see how we actually need to execute it. So first thing, we need to configure this command, set execution policy unrestricted, to allow partial script to be executed. So let's copy this, fire a PowerShell with an administrative privilege. Execute the command and make sure you do a yes to all. Now we can go to our users downloads folder where we download our PowerShell script and execute the install.ps1 script. So now we'll make sure that we choose the R. Then we do yes. This message is to make sure that you have a virtual machine snapshot. So if you want to take a snapshot, you can go over here and take snapshot. If you're taking snapshot while the virtual machine is on, it will be with the sign of this play button. I would recommend to take a snapshot in a cold state whenever the virtual machine is shut down. Like you can see here, the clean snapshot that I had here is on a shutdown state. After this, you do yes. Then you put the password for your user and it starts to install it. I already have a virtual machine deployed here with the Flare VM. Of course, I will provide you with a OVA file, which you can double click and deploy it. But for those who want to do everything from scratch, this is what I show you in the video. Another thing that I recommend to do after you installed your Flare VM on top of the Windows 10 machine, you can go CMD and do Choco upgrade all. This will make sure that all of your Flare VM tools are upgraded to the latest version. So this is for this video. See you in the next one. Thank you very much. Hello everyone and welcome. In this video, we're going to do the practical demonstration of installation of our malware analysis lab. So we will deploy two virtual machines. The first will be the Windows 10 malware analysis VM, and the second one will be the Remnux. The Remnux is based on a Linux distribution, and both of those VMs are easily to deploy. You basically go and double click on them, give them a name, a path, and do import. The next thing you need to validate is to go to the virtual machine settings. So we'll go to the Windows 10 malware analysis machine first. Do right click and settings. Here you can see I have 16 gigs of RAM. You can also work with 4 gigs and even 8 gigs of RAM. And we have the quantity of processors or the cores per processor. And you can configure as much as you have. We have at least 250 gigs of storage. And we have two interfaces. The one will be bridge or NAT for internet connection. which will most of the time will not use. We'll use the custom VMnet 19, which will be used as an internal communication between the Windows 10 machine and the Remnux machine, and the internet will be through the Remnux VM. So this is the settings that need to be deployed in the Windows 10 Malware Analysis machine. Let's go to the Remnux machine and do right click and settings. Now we'll see we also have NAT and VMnet 19. In this case, the NAT will be enabled and the VMnet 19 also will be enabled. You can choose other VMnet, as you can see here, from 0 to 19, but make sure that two of the virtual machines have the same VMnet, as they operate like the same network switch. So now let's go back to the Windows 10 machine, do WinKeyR and ncpa.cpl. This will open up for us the interfaces of our Windows machine. As you can see, the NAT is disabled and the LAN interface is enabled. I already renamed them beforehand, so I will have better understanding what type of interface I'm tackling. So let's do right click and properties. I'm disabling the IPv6 and doing double click on the IPv4. And as you can see, I already configured it to 10.0.020, 24-bit of subnet mask. And the full gateway will be the IP of the Remnux machine. And the same will go for the DNS. This is basically the configuration we need in the Windows 10 machine. Now let's go to the Remnux machine. First of all, let's validate that the VMnet 19 interface is configured with an IP, as you can see here. In my case, the VMnet 19 interface will be ENS36. Now, in order to configure the ENS36 in my case as a static IP address, we need to do the following. First, as a rule of thumb, whenever you deploy a Linux virtual machine, always do an apt update and apt upgrade -y. This will update and upgrade to the latest packages in the Linux machine. The next thing that we want to make sure that we installed is if-up-down package. And the NetTools package. Then we'll go into configuring our ENS36 interface with a static IP address. So we'll go etc network interfaces. I made sure that the ENS32, which is our NAT interface, is automatically enabled when the machine is booting up, and that is receiving a DHCP configuration. Our second interface, which is ENS36, will be static, and we'll configure an address and a 24-bit netmask. Then you go and doing Control-O and enter, and Control-X to exit. Then what you need to do is if-down ENS36, if-up ENS36, and sometimes it cannot work and you need to do some troubleshooting. Sometimes even you will not see the ENS36 or 35 or whatever interface it will be. You go into IPA, and the IPA command will show you the interface name that is not listed in the ifconfig command. So you go and do ifconfig ENS36 up. And then you will see the ENS36 interface is ready and available. Then you go and do if-up ENS36. And as you already know, it is already configured and everything is fine. One of the things we need to do in order for our INET SIEM to accept traffic on specific ports and also forward to the internet, we need to run several commands. So let's first of all run the accept all IPs command. So we'll do accept all IPs, start, and our internal interface, which is ENS36 in my case. What it will do, it will accept all IP traffic in this interface. Second, or third in this case, we want to actually enable IP forwarding in this virtual machine, so any type of traffic that comes from the Windows 10 machine will go to the internet. So let's execute this command. And let's validate that it actually is configured with the 1 value. As we can see, it is. And in order to make it persistent in next reboots, we'll go and configure this file with nano, or if you like to use Vim. And let's search for this line. We do Control W. And you can see I already uncommented it. And now it will be persistent across reboots. The next thing to do in order for our Windows 10 machine to have an internet through our Remnox machine is to execute those commands. So let's do it. So in the first command, we need to define the internet facing interface. In our case, it is our NAT interface, which is ENS32. Let's paste this command and let's define our internet facing interface, which is ENS33. The next command will be this one. So first of all, we need to define our internal interface, which in our case is ENS36. And then the outgoing interface will be the internet facing, which is ENS33. The last thing we need to do is to enable the INET SIEM service. Before we do it, let's configure the service that we want to use in the INET SIEM service. So let's go nano etc INET SIEM inetsim.conf. So if we go down here, we'll see all of those services are uncommented. By default, the DNS will be commented, so you need just to delete the comment if you want to use it. And make sure the service bind address is configured with the IP address that you previously configured in your ENS interface. In my case, it's in ENS36, and this is the actual static IP address that I configured to this interface. There are other configurations that I configured here, like the DNS bind port, which will be 53, DNS default IP, which again is 10.0.0.30. You can view the capabilities of INET SIEM and play with it. So let me do Control O to save and Control X to exit. Then I'll go and do systemctl start INET SIEM. Then I go and validate the status of the service. As we can see, it's active and running, which is good. And the next thing, we need to validate that the INET SIEM service are actually in a listening states on the ports, for example, for HTTP, DNS, etc. So let's do netstat planet U. And as we can see, we have all of the ports in listening mode, and make sure they're listening on the IP that you configured in the inetsim-conf file. Another thing that you want to do is do systemctl enable and inetsim, so it will be enabled in each reboot. Now if we go to our Windows 10 machine, I will fire up cmd, we'll do ping 8.8.8 for example. See that we have successfully initiate a connection, and also let's validate that we have a DNS resolve. Let's do ping google.com for example, and as we can see we have successfully resolved the IP address. So this is what we need to do in order for our malware analysis lab to be configured. Thank you very much, and we'll meet you in the next video. Hello everyone and welcome back. In this part of the course, we will learn how to write basic C code and compare it to assembly. In this way, we will understand how to identify assembly code blocks, and for example, we will understand how to identify if statements, function calls, and other important stuff whenever we do reverse engineer malware samples or do reverse engineering in general. So our environment for developing basic C code and compiling it will be Visual Studio Community Edition. So let's go and download it from the official Microsoft website, of course. And click on it. In this part, it will actually download the Microsoft updated Visual Studio installer, and you will need to select whatever you need here. It will be very straightforward and very short video. The only thing we need here is actually selecting the desktop development with C++, which will of course will also support the C language. Now, in the right pane, we will see things that will be by default installed. I recommend to also add the C++ CLI support, build tools, and also if you have Windows 10 machine with the Flare VM installed or whatever, you can use the Windows 10 SDK. You don't have to do it, but it's optionally. If you want to do more stuff like malware development and using different type of includes and Windows API functions, it is very recommended to install the Windows 10 SDK, but it's not actually needed for our course. If you have Windows 11 with Flare VM, you will select the Windows 11 as. Now you go and simply click install, and it will start the download operation. After it will download and install Visual Studio, we can start our development process. So just for the example, after you will install the Visual Studio, this is how it will be presented. And you can start by creating a new project and selecting your type of project. It will maybe even request a user login, Microsoft user login. If you have an Outlook or something in this sense, you can basically log in. And if you want also to upgrade to different versions like professional and enterprise, you can do it, but you don't actually need it. The community version is enough. So this is for installing Visual Studio. As you saw, it's very straightforward. See you in the next video. Hello everyone and welcome back. In this video, we'll go through the 4 stages of how code is developed, compiled, and eventually executed. So in order to understand malware analysis, one of the most important things to understand is the ability of reverse engineering. In order to reverse engineer a code, especially from an assembly code, we need to understand how the code is developed in the first place. Now, as a side note, in this course, we'll not go deep dive into reverse engineering. We'll do some basic stuff in reverse engineering, and we will combine it with other malware analysis methodologies. In the next more advanced course, we will go through deeper stuff and we'll understand more of the building blocks and more deeper and broad aspects of the operating system and of reverse engineering in general. So first of all, it is very important to understand before we go into some practical C code example that whenever you're developing a code, whether you're a developer or some enthusiast in the security community, first of all, you write your source code. The source code can be written in many languages like C, Python, Rust, etc. Eventually, it really depends on the language that you're using, but there are interpreted languages like Python, for example, which in their nature, they basically not compile, they interpreted and executed on your system. You do have the option to compile a Python code using PyInstaller, for example, compile it to a P executable, but it's a different discussion. But there's another yet native languages like C and C++, which are a compiled language, where you actually go write your code and then you compile them to some type of an executable. If it's in Linux, it will be an ELF format. If it will be in macOS, it will be Maho binary. And if it's Windows, of course, it will be the PE format or portable executable, which can be files like exe, DLL, SCR files for screensavers, these files for drivers, and so on. So the first stage is writing your source code, and then is going through the compilation process. You can use different type of compilers like GCC or Visual Studio, and the compiler basically takes your source code and compiles it or translates it to a machine code, something that your CPU can understand and execute. Of course, we'll go through how it actually looks after the compilation. Then you have another thing that's called a linker. We'll not go deeper into what is a linker, but in general, if you use functions like printf, for example, in your code, or for example, create process or create file, which are Windows API functions, the compiler and the linker, or specifically the linker, need to take those functions and link them from an outside source like a DLL file into your actual compiled code. So a lot of other people will say that compiler and linker comes actually together. There are different components, but they work together. So if you're using an external function, including a library, it will link this function to the compiled version of your code. And then you have the last stage, which is called runtime, which is actually when your code is executed. So you have an executable file, you double click on it or run it through other means, and the code is actually executed. So this is for the basics of the 4 stages of development in general. In the next video, we'll go through some actual examples. Thank you. Hello everyone, welcome back. In the next videos, we'll learn the basics of C and assembly from few examples. So first of all, let's create a new project in Visual Studio. So let us do a create new project. Select our language, platform, and we want to select console app. C++, Windows. Next, let's name it Demo Labs or whatever name you like. And this is the location or the path where the project will be created. Let's do create and get our hands dirty. So as you can see here in the right pane, you can see the source files. Here we have the CBB file. Let me change it to D. So Visual Studio will recognize that we're writing in the C language specifically. And let me just copy and paste the code that I already wrote beforehand. And let's start by explaining what we're seeing here. First of all, in C, it's very important to understand that the execution starts from the main function, as opposed in other languages that you don't have to use a main function. So in the main function, we see definition of 3 integer data type variables, and each one of them has a value. And then we have a for loop, which starts with the 0 value and iterates through the number of 5 and basically prints the value. So basically it will go and print the value of the for loop. So it will do print 0, 1, 2, 3, and 4. So the second type of loop that we have is a while loop. Here we can see that we do a check if the variable of num2 is greater than 0, print the value, and make the value -1. So you have plus plus, which is +1, and you have minus minus, in this case, which is -1. It will lower the value by 1. And eventually when it will reach the number of 0, it will stop and exit the loop. So the main function calls 2 other functions. The one called print sum, which takes 2 parameters, num1 and num2, and the same parameters go to the second function, which is called print product. So after it will reach print sum, it will call it with num1 and num2, and then the execution flow will go to the print sum function. You can see it takes 2 integer parameters, a and b, which is basically num1 and num2. Then it goes and do a simple arithmetic calculation of a plus b and prints the sum of them. And the same go, and then after, of course, it will the execution of this function will end. It will go back to the main function or to the last call, and then it will call the print product function. Then it again will go to the print product function, take 2, which takes basically 2 parameters, which are num1, num2, or a and b basically. Then it takes the variable of product, calculates the value, and prints it. So this is how this C code, like we have a main function, 2 more calling of functions, very basic variables. It can be different type of variables. It can be a char variable, and it can be other types. And just to note, the prerequisite for this course, of course, I write it in the syllabus itself, is a prerequisite of C and assembly. So for you already know C and assembly, it's a very, very simple and straightforward. But for those who not, it will give you some type of introduction. But again, if you don't have any knowledge on C or assembly, you can go and learn from a lot of other sources out there. But you can, of course, stick with me, and from the examples, from practical examples themselves, we can learn a lot. So in the next video, we'll go and compile this code into a P executable, put it into a disassembler. We'll use IDA Pro or IDA Free, whatever you like to choose, and understand how the C is actually transferred to assembly. And in that way, we can learn how to identify code blocks in assembly. So thank you very much and see you in the next video. Hello everyone, welcome back. In this video, we'll take this simple C code and compile it to P executable and disassemble it in IDA. So we have two modes in Visual Studio. The first is called debug. The debug mode is used to basically debug our source code, where we can actually put breakpoints, for example, execute the process or execute the debugger, and the program will stop at the breakpoint. And in that way, we can basically see how the program is executed, what type of loops are accessed, what type of functions are called, and in that way fix and troubleshoot problems. The second mode called release. In the release mode, you go and actually build the P executable, and the build process basically compiles the code and links the relevant functions to the compiled P executable. Here you can basically choose whether it will be an x86, which is 32-bit version, or x64, which will be for 64-bit version of P executable. So let's make it x86 for this example, because we want to see the assembly version of the 32-bit, which will be much more simple for our first examples. And then I'll show you the difference between 86 and x64, so you can identify them. So let's save it and do build solution. And of course, if the code doesn't have errors or bugs, it will compile it successfully. Now I want to take the exe file in this path, so we can do right click on the solution or the project itself and open folder in File Explorer. We can go to release. Sometimes it will be in this folder. Sometimes you need to go back actually and go release. And here we go, we have our exe file. So first thing before we actually go and put it on into some kind of disassembler like IDA, I want to talk a little bit about identifying a file, which we'll also talk a little bit more later in other videos, how to identify a file type. Okay, so if I'll use here an hex editor like HXD, I can put the file inside, and I can see there are some values in hexadecimal and the decoded text, which is basically string or ASCII representation. So the first identifier is called the magic number, or the MZ header in this case, which in any type of P file, which can be an exe file, DLL, SCR, sys file, etc. And we have the standard message here, which is called this program cannot be run in DOS mode, which can potentially be manipulated for bypass purposes, bypassing antivirus, EDR, stuff like this. And we have basically other things which define the building blocks of a P file. So here we can see, which basically is the P header, where we can see all of the relevant and existing sections of the P file. Again, we'll talk about it a little bit more later. So here we can see the reference to the text section, which is basically all of the code or the machine code or the assembly code is existing, and when the process is loaded, all of the all of those all of those machine code or all of this code basically be executed from this section. And again, we will elaborate more about other types of sections when we come to the parts of the videos where we explain about the P format. So here we can see a lot of hexadecimal values, which are actually the machine code. So whenever we'll put it on IDA, it will disassemble this machine code, those hexadecimal representation, into a more human readable format. In our case, because we compiled the file in C and C++, the disassembled code will be 86 assembly. If we were to compile this code in .NET C#, for example, and use a tool like the NSPY, we'll get the full compilation or compiled code. Literally get source code, not the assembly of it. Okay, so it's a little bit different. And again, because we compiled this C++ program, we'll get disassembled in assembly format. So let's take the exe file and put it into IDA. So you do here go, and you can basically put it into IDA. And if you want to also have access to the resource section, which we'll explain later in the course, you can take here this checkbox and do OK. Sometimes you'll see some errors in IDA for some reasons. Of course, you can errors or notices, you can just move along. So here we can see the disassembled code. So here we can identify the main function, as we can see in the code here. So we have the main, and here we go, we have the main here. Then we can see that there are some strings like this for loop, which we can identify in this code. And then we have a call to this sub something function. So in IDA, whenever you see sub, it's from the word of subroutine, which is basically a function, but it's not an external function that is linked from a DLL or from an external source. It's a function that the developer that developed the code actually represented here. So whenever a developer creates a function like print sum, which is a function that the developer is defined, so this function will be represented in IDA like this, because IDA don't really knows what is the name of the function that the developer gave. So if we do double click, we can see some calls and some other assembly instructions going on here, and we see something with printf and another call to a function which really doesn't do nothing here, and eventually it will go here. We can identify a loop. You can see here with this green arrow, we'll do some loop, and we can also identify it by the fact that we see this compare to 5. So the fact that we see compare 5 to EDI is a register which will basically hold the value of 5. And by comparing the values, you can see here that it checks if it's lower than 5, it will go and jump into the loop. So if it reaches the 5, of course, it will exit the loop and it will go to the while loop. And in that sense, you can understand how to identify code in IDA or other disassembler in the assembly level. Just want you to experiment with it. I want you to write your own C code, compile it, and put it in IDA. In that way, learn better about assembly and get better reverse engineering skills, which can take literally years. If someone tells you that reverse engineering it's something that you can learn fast, it's a lie. It can take a lot of time, and if you put the efforts, it's worth it. So we'll continue in our next video, understand how all of this actually works, and we'll debug the code, and we'll also use the pseudo decompilation window, which will give us kind of the version of the source code, but in a pseudo way, not the real or the actual source code, but it can help us a lot. See you in the next video. Hello everyone and welcome back. In this video, I will show you how to use IDA Pro as a disassembler and a debugger. So in the previous video, I showed you how to take this simple code, and by using this release mode, we compiled a x86 or 32-bit version of the P executable. After we did this, we loaded the P file into IDA Pro. So what we can see here is basically the disassembled code, which is basically represented as a machine code or as an hexadecimal representation. IDA takes all of this hexadecimal code and disassembles it to a more human readable form. In the left pane here, we can see the subroutines which are defined or recognized by IDA. So for example, a function that is defined by the developer, like this print sum function, IDA cannot really know the original function name the developer gave. It really depends if you have the PDB file or the debugging symbols, so IDA can recognize the original name, but without the PDB, it cannot really do it. So it will recognize it as a function and will put it context as a subroutine. So this sub is subroutine, which is another name for a function, and then it will put underscore and the starting address of the function. So if we do double click on it, we can see we do space that we have the sub and 401000, which is the starting address of the function itself, which we can also see that it's under the text section. If you remember from the previous videos, I explained shortly that the text section, the default name for the section where all of the machine code, where the actual code is executed by the thread that executing the code inside a process. So if we want to go back, we do escape and do space. So we can recognize that we are in the main function, and we have some assembly instruction and call to functions. Now, in order to understand what is the context of this function and to make our life easier, we can double click on this subroutine and see the inside of the code. If we want to go back, we can do again escape, or again, we can just double click and get into it. So from what we can see here, the printf is basically used here. Now, it can be very strange sometimes because in the code we see printf, but in the disassembled code we see a little bit different stuff like this vf printf something. So as a reverser, you don't always need to concern yourself of why things are like this or like that, and just understand and recognize the context. You understand if you execute this function while debugging, you see that it will actually go and print whatever it needs to print. So if you want to rename this, we can do right click rename, or basically use the N key in our keyboard. Let's rename it to printf. And now we can basically see that the function or the subroutine is changed also in the function name window, and we see printf. So now if we do escape, now we see a different context. Now we can understand that we actually use printf here to print, for example, the string of while loop is printed by printf. So Now let's try to understand the code here. So the first thing that you will notice in each function, whether it's the main function or any other type of function, that it will start with some, maybe for some of you that will not recognize it or not necessarily know assembly, can be maybe strange, but the first instruction that you mostly or likely to see is push EBP, move EBP SP, which is basically the stack initializer. It's what initializes your stack memory to be used by the function. So basically each function is initialized with these two instructions in order to initialize the stack for the operation of the rest of the function. So this is called the prologue. The prologue is the starting of a function. And the end of the function, it's called the epilogue. The epilogue, you will mostly see something like with pop and return. Okay. After this, mostly we'll see some cleanups of the stack. Whenever you want to clean up a stack, you use the add. I know it can be counterintuitive, but the stack actually grows downwards. So whenever you use add, it cleans up the stack. Whenever you do sub, it adds or basically fills it with more data. So add basically cleans up the stack or removes stuff from the stack. So while the ESP is pointing to the top of the stack, the EBP is pointing to the base of the stack. Of course, if you want to more understand about, you can research it, but as again, in this course, I will give you only the basics and the most important stuff for us to understand the basics of the reversing journey or the malware analysis that we do in this course. So if we go to the source code, we see that printf takes a parameter. So each function needs to have a parameter. Not all of the function need to have a parameter, but for example, we can see the main function doesn't have any parameters in it, and that it takes, but the printf takes one parameter to be printed, and potentially can take more parameters. Or the print sum, which is a function that defined by the developer, gives or provides two parameters, as you can see here, defined by this void print sum. So if we go back to IDA, we'll see a little bit different styles. So before we see the call printf, those parameters need to be pushed to the stack, so the call to the function can be used. So if I want to, for example, print the while loop string, I push the value to the stack and then I call printf. So think of the stack like the ammo or ammunition or the function of printf to be used while the function is actually in operation. So before you have a call to a function, you have push. Now it really depends. Whenever you use x86 code, you'll see pushes and call. x64, it really depends, but most of the time the first 4 parameters will be moved to 4 registers, which we will see in our next example or the next video. And then it basically from the fifth parameter and so it will take the parameters of the function, basically push it to the stack. So it really depends on the architecture or the binary, if it's compiled in x86, x64, and other stuff. But the most important thing for you to understand is the ability to recognize patterns. And by recognizing patterns and functions, you can get better understanding of the code. So we can see here push ESI, EDI, some registers. Again, there's a push to for loop, and then another move for 3 for ESI for some reason, then call printf and cleanup of the stack, and then XOR EDI, which will give us 0. Then we have a nope, which is no operation. Why the compiler decided to put this nope, I don't really know. If you want to go deeper in why compilers want to do this thing or that thing, you can research it. I can give you a lot of reasons, but not all of them will be correct. It really depends. Okay, So then again, you have push EDI, this offset, printf, and again, you have some loop here, and you see this comparison of if 5 compares to the value in EDI, and it jumps lower. So if the value in EDI is lower than 5, it will get a jump and do the loop. So it basically, this is the for loop that we see here. If it's lower than 5, we'll jump the loop. Now, in the previous video, I basically said that I will also show you the pseudo decompilation window. So if I do F5, I'll just put the window like this and synchronize IDA view. And I will see the real power of using both of those windows. We can recognize this for loop basically. So if you highlight the for loop, you can see, okay, so we have here this code, which is part of the loop or whatever, or to be more specific, you see this increment, add, compare, jump loop, or jump lower. So this is basically the implementation. So in C, it looks like this, and in assembly, it looks like that. If you go and highlight the printf here, for example, it will literally highlight the call. So it's not literally the source code, but it's kind of close to the source code. So this is why it's called pseudocode. So you can learn a lot from it and can help you in your journey of reversing. And of course, if you want to debug the program, you can do it. Now I'll show you in a couple of seconds. Before this, we have other windows like the hex view we saw earlier, with the structures. Those are basically to define the structures of functions, Windows API functions, stuff that are corresponding to stuff of the operating system itself, and really depends on your reversing journey. Especially we'll use it on advanced reverse engineering whenever we need to define structures for our own, or structures that are not known to IDA to aid in our reverse engineering. We have imports. Imports is basically the functions that are imported from outside of the code. So those are the functions that are imported by the linker of the operating system. We have the function that is important. For example, we have the exit function, which is imported from this DLL API, MSWin, whatever. We have the, let's see if we have the printf here, for example. We have the printf. So Visual Studio, or the compiler of Visual Studio, decide to import this stdio common vf printf. Maybe it's for optimization purposes and stuff like this from this DLL. Okay, or it decide to add this get current process from the kernel32.dll library. So we see here the function name and the library that is imported from this library, basically. Okay, you have exports. Exports are basically, you will see, so if imports are the functions that are imported by process or by P executables from DLL files, the opposite is true for exports. Exports where DLL files export for other P files. So if we load into IDA, for example, or into X32DBG or any other type of disassembler or debugger or a P view program, and we load a DLL, the exported functions. Okay, this is the reason of DLL files, to export functions for other exes or exe files. But of course, because they're the same format, an exe file can also import and export, vice versa for DLLs. So in order to do in order to start a debugging, we need to put somewhere a breakpoint. We can put in the start of the program, we can put in other places. Take into account that if you put a breakpoint here, for example, it will execute all of the code till this point. So take it into account. So if you have something to, like anti-debugging technique or something that you need to bypass, you need to take it into account and to tackle it before you get to this point. So if we put a breakpoint using the F2 in the keyboard, or just do right click and add the breakpoint, we can start our debugging. So let's do here local Windows debugger and start. We can close some windows here. Like we have the threads that are running, or the modules that are important from DLLs, or the DLL files itself, or from where the actual module or Windows API functions imported. So now we see here the IDA window. We can see here the stack, the hex view here in the left, and the registers here in the right pane, and the CPU flags. So the register we have EAX, EBX, ECX, EDX, ESI, EDI. ESI and EDI are used for source index and destination index, mostly for moving something from a source memory to a destination memory. For example, if you use the function of memcopy, mostly it will use the ESI as the source address and EDI as the destination address. This is the way of how things work. EBP-SP, as I explained before, is the stack, is what basically defines the stack frame. EBP is for the base pointer, ESP is for the top of the stack. EAX through EDX are basically, each one of them has their own definition, but they used as general purpose registers. And in EAX, you will have the return value of a running function. So for example, if we run the printf function, we'll have a return value from the function. So just as a short explanation about return values, each function we can define whether it has a return value or not. The return value will give a status, whether the function is succeeded or failed or something else. So it really depends on the definition of the function. If we use void and then the function void, you will not expect from a void to have a return value, because void is without a type. It's not an integer or char or other type. Because the main function has the type of int, you expect to give some type of return value. Maybe either 0 or -1. And it really depends on the definition of the developer. One developer can define that 0 is a success and -1 is failed, and the other developer can do it otherwise. Throughout our course, we'll see different type of Windows API functions, and you'll see different cases. It can be sometimes very good, sometimes very annoying. But for this, we have the documentation of the MSDN, Microsoft's documentation for functions. And we'll see by going in this course. So we have a return value of 0. So if this function of main will succeed, we have the return 0. If not, we'll maybe have some other return value. So this is what basically the return value will be stored after the function will be executed, will be stored in the EAX register. Now take into account, the register originally is AX code. AX is 16 bits. It has a lower address, which is called AL, or accumulator lower, and AH, which is accumulator high. It has a low and high. Then you have the EAX or E, which is for extended 32-bit. Then you have the RAX, which is 64-bit. If you compile the P executable in 64-bit, Visual Studio, for example, the RAX, RBX, RCX. Okay, so let's do our debugging. So we have F8 to step over and F7 to step into. Now let me explain it. So now if we do F8, this push ESI instruction is executed, and this value in the ESI, we can see that this is the value, debug whatever something. We can click here and see what it is. We can try to do here DDD for definition. It will change it from, for example, if we do Control Z, from before it was DB for byte, define byte, then it go for define word, which is 16-bit, and then define D word, which is double word, so 32-bit. Then you can see basically goes and has an offset to our own executable path. Okay, so again, we don't necessarily anytime will understand why does this thing or in that way or whatever. Just go with the flow. This is my tip for you, especially for the go with the flow and learn. Of course, read as much as you can and go deeper into the waters as much time as you can. So basically, now it will take the argument list. So basically, it will define the argument for the C. So it will basically doesn't really, in this program, doesn't really takes argument from a user. For example, if you run this executable in CMD, it will not take an argument. For example, if you do this exe file space something, so basically it will execute itself. It's called argument 0, which is the argument itself, is the exe file itself. If you have argument 1, 2, 3, and so on, it's argument that you need to define. For example, if you run, for example, some type of a command.exe, so 0 is the exe itself, 1 is whatever argument that you need to define, 2 is another argument, 3 is another argument, and so on. Okay, so, and then basically, then again, if we do F8, another value is pushed to the stack, as you can see here, into the top of the stack, and another push of this 3B2144, another, which is again another thing that is now pushed to the stack. And we have moved 3 to ESI. So now ESI is defined to be whatever something is the path. Now if we do F8 on move 3 to ESI, we'll see that it actually replaced the value that it had with the 3. So now we see the value of 3. Now it will go and do printf. Now if we do F7, it will literally, let me just close this window, it will go literally and go into this function itself. If we do F8, we can see push EBP, move EBP speed, the stack initialization process, which I explained beforehand, which is the prologue. And it will do its magic. So for now, we don't see any prints here. Now if we do F8 on the VF printf, we can see the actual print, which is nice. Now we'll do its magic, clean up the stack, pop the last value to ESI. The last value, which was here, the 3, is popped to ESI. Now we have the pop of this address to EBP. Now we see the same address in the EBP, and return. Return will basically return us to our place. Now, if you remember, I said that the return value will be stored in the EAX. So now we have basically, and again, it really depends on the function that you have. Some functions have return values from one type, and it really depends on the developer that define the return values for the functions. And there are other functions that they don't have any return value because they are basically defined with this void without int or other type of return value. Okay, so we continue here, and again, it will go and do the same stuff. If we do again F7, we'll go into the function. Now it will do a printf, and sometimes IDA has problems with specific functions like printf, so it gets stuck. So we can stop it, run it again, try to execute it. Let's try it again, and now it works. So now we have the print for loop 0, and now it's fine. So now the EDI is 0. It will increment the INC instruction, increments it by 1. And now we have this add 8 ESP for the cleanup, compare 5 to EDI. So now EDI is 1. So it actually, the comparison will not be true. Okay, so it still, the EDI doesn't have the value of 5, so it does not compute. So basically, then the next instruction is basically jump lower. So if the value of EDI or of the comparison is lower than the value of 5, do again the same loop. Jump to this location 3B1060, which is again the address that, or the offset on the memory of the file. Again, to do this and that and this and that until it actually finished. Now again, I don't know why it has this bug with the printf. And really care. Just continuing. Now it seems to be fine for whatever reasons, and it will go for the same for the while loop. Print the calculations on operations. I will let you to do this for your own, and that's it for the video. If you have any questions, of course, just let me know. So thank you very much. See you in the next video. Hello everyone and welcome back. In the previous video, I showed you how to work with the IDA disassembler and debugger. And also we took this very basic code and compiled it to an x86 or 32-bit version of a P-compiled executable. In this video, we'll take the same code and compile it to release x64 compiled P executable. So let's select x64, build solution, and go to the folder where the P executable is compiled, release, and load it into IDA. Do OK. And as we can see here, we have kind of the similar code, not real of a difference. Now, the difference we'll see here is when we'll start the debugging. But you can also already see that there are some slight differences in the disassembly. We see not push EDI, we see push RDI. So the registers here will use the R convention, which is for the x64 version of compiled executables. So basically, you still see use of EDI or even DI or SI, which are 16-bit versions. Really depends on the context, but in x64-bit, you will see more the usage of the R convention for x64. So let's start our debugger. Let's put a breakpoint, the F2, or just doing right-click and add breakpoint, and let's start our debugger. Let's close here this window. And as you can see, we have the R convention registers in the right pane. You also notice that the address space in the hex view and also in the stack are different. They're bigger than 32 bits. So basically, we have the same type of registers like EAX, RBL, or EBX, ECX, but with the R convention. And you can see here, they have bigger values and address space. So again, we have the RAX, RBX, R6, which are general purpose registers for calculation stuff like this. RAX mostly will have the return value. The RSI, RDI will be the source index and destination index for copying data from source address to destination address. RBP and RSP are what builds actually the stack frame. We have the RIP, which is like the IP or EIP, which is the instruction pointer to the next address to be executed. So as you can see here, we have the 7FF675DC1070, which is the same address for the RIP. If we go and do right click and do modify value, we can modify the address to a different address here, and we'll jump this address. Or we can just do, for example, right click on an address and do set IP or set instruction pointer, and as you can see now the RIP is pointing to this address that I pointed to. So in addition, we have more registers in the x64 bit. We have R8, R9, and so on till R15. So those are additional registers in the x64 bit. And basically, this is what I want to show you for this point. So while we'll go through the course, we'll see a lot of examples. We'll work with the Windows API functions. We'll reverse engineer malware, and you will see this type of things while we're debugging and disassembling stuff. So for me, it was very important for you to get a taste of it or a little bit similarity with it, so I can be more comfortable in showing you the deeper stuff whenever we do malware analysis and reverse engineering. So thank you very much and see you in the next video. Hello everyone and welcome back. In this video, we'll go through the P or portable executable file structure. I'm using here a great resource of Ange Albertani from Korkami.com, which made a great depiction of the internals or the dissection of the bits and bytes or the parts of the P file. So everything here, as you can see, is in a visualized form. This is why I decided to show it like this. So as an example, we see here a simple 64 named executable file, which is basically dissected or open in a hex editor. For example, if I take here the HXD hex editor, I can see here that I opened the previously compiled demo labs exe file that we compiled in the previous videos. I can see here we have the 4D5A hexadecimal magic value, which is represented in a decoded text or in ASCII as an MZ, basically. ANSI or ASCII is basically the characters that you basically see in the keyboard itself, which is letters, numbers, special characters, etc. So this is the decode of 4D5A, which is the magic number or the identifier for P executables. It can be for exe file, DLL files, sys drivers, etc. We also have this famous message with this program cannot be run in DOS mode. Sometimes you can see different type of messages. There is also this tactic that attackers can use to manipulate one of those characters, for example, without breaking the file structure, and basically changing the hash of the file, and in that way bypassing static engine of antiviruses. These things we will see in a different course that I will make. So we also have the P header, which we can see here, and other interesting data. We can see here the some of the sections that are used in the PE, like the text section, are data. So this is a very quick example on a practical manner. You will see me a lot of time using hex editor like HXD to firstly identify the type of the file before I actually throw it into some programs or throw it into IDLE. Like, you need to first understand what type of file you are working with before you take a file. Maybe it's with an .exe extension and you go and throw it to IDLE, but IDLE does not recognize it. Maybe it's a PNG file, maybe it's a PDF. So the first thing, or one of the basic methodologies to go, is basically just go and do a basic inspection of the file inside a hex editor like HXD. This is the first thing. And by the magic value that you will see in the mostly in the start of the file, what's called the offset 0, you can identify the file type. So let me go to the depiction, and as you can see, we have this depiction of the MZP, and we have the parts with the header and sections. So let me explain it in a very simple manner. Think of a file as a book that you want to open and read its content. A book has basically sections. It has parts, okay? So each section has a header and has its own relevant and corresponding data, okay? So it's like a book. So the P file in general, without going too much into details and into the internals, for more details into the internals, you can take Windows internals courses of Pavel Yusefovich, for example, one of the greatest mentors of Windows internals out there. So the file is basically dissected into two parts, the header and the sections. So the header basically indicates about some important and basic information about the file. And based on the information that is found on the header section, and of course also in the sections themselves, basically P parsers, programs that malware analysts and researchers tend to use, like Total PE, for example, which is a great tool of Pavel Yusefovich to dissect PE files to see its different sections and data, or PE Bear of HasherZ, and other great researchers in the industry. And basically, their programs or tools, they know how the P file or structure is built, and by the way of understanding how it's built, they can parse and visualize and show you the data. So the first thing in the header section, or the first part of the file, is the DOS header. The DOS header, as you can see here, it corresponding to this MZ message and also to the other message that we saw. This program cannot be run in DOS mode, and other type of messages that you can see in different type of executables. Depends on the language that is written and the compiler that is used, and of course the linker and other stuff that it depends on. And then we have the PE header, which is basically the PE, as you can see here, the P indication. And for each data, you have basically the offset and the corresponding data, which, for example, identifies what type of processor, whether it's ARM or MIPS or Intel x86 or x64 and stuff like this. And you have the optional header. It's called optional header, but it's not really optional. Any type of P file, you will see this section. So it's kind of, mandatory. It gives you a lot of information. Maybe there are some ways to, omit this section to hide and stuff like this. I don't really say that I know everything in this industry. If someone tells you that I'm something like 13 years in this industry, and the more you understand, the more you learn, you have more and more stuff to learn and to understand. It's an endless things to go on. So there's always this hinge in my mind that says that, yeah, maybe it's something that you don't really 100% sure about. So it's a good approach to go in this industry, to be open to new ideas and new information. So back to our point, the optional header gives us the information, very important information, whether it's 32-bit or 64-bit executable, where the execution actually starts whenever the process is loaded and executed. What is the memory address or the offset that it actually starts in? Where, or the address or where the file should be mapped in memory when it's actually loaded and executed in memory. Where sections should start in memory, and so on. All of this type of information, you can go through all of those. And of course, we'll go in the next videos, we'll go practically and see them in PE parser tools that we can use. So we have the section table, which basically defines what kind of sections are actually out, like in this file, and what are the names of the section. Take into account that the section names can be different. They can be also easily manipulated and changed by attackers or by even legitimate individuals or whatever. So we have the text section, which corresponds to the actual machine code or the code that is executed by the processor, or specifically by the threads. And you have the R data, which is for read-only data, which you have there. Sometimes you have there the imports functions. Sometimes it's in a different section, like the I data. You have also other variables there, and information for the process to be actually parsed and executed. You have the data section, which hold the global variables that defined by the malware author or by the developer, basically, whether it's legitimate developer or not. And so you have the global variables, and you have the parameters that are that can be potentially also pushed to the stack for the uses of the functions of the program. And again, if some of those things that I'm talking about now are not making any sense for now, it's okay. Just keep up with the course, and everything will be connected. This is one of the things in this industry that, especially the research stuff, like malware analysis, vulnerability research, and stuff like this, that can be sometimes difficult to understand. And I can try to do my best to explain these things in a more or the best or in the simplest manner. But just keep going, learn, cross-reference things, connect the dots, and you understand everything. So no worries about that. You can have other sections like iData and eData. iData for the import address table, or the IAT in short, and you can have it's for the imported functions that is imported dynamically in the runtime execution of the process. You can have the eData section, which is for exported functions, mostly for DLLs or for the EAT or export address table. And you can have the .bss section, which are for variables that are initialized as 0. So for example, a developer goes and uses a for loop, for example, and initializes the first value as 0. Most likely this variable will be initialized as, of course, a 0, but it will be recited in the BSS section. And if we go next to the code, we have the code section, which again, it's called the text section mostly. Again, it can be changed or manipulated. We have the imports, and we have the data, which we already talked about. Yeah, so this is basically the general of how things are working. We have also the loading process itself. So we have the headers. The DOS header is sparse, the P header is sparse. So basically the operating system checks that those headers are actually there. So if you try to manipulate the MZ header and change it to a different thing, basically the OS will not recognize it as a P file, and it will be broken. And stuff like this. Then the sections are loaded, and everything is mapped to the memory with the image base, size of the headers, the section table. All of the imports with the IAT are imported. Like those functions that are need to be used by the code. For example, the developer define the create process function to creating another process under it, or maybe the create file Windows API function to create or getting a handle to an existing file, or maybe using the internet open URL function to download file or whatever. So all of those functions will be imported on runtime and executed whenever they need. And of course the execution itself. So this is the general of what you need to understand how things are working. Of course, there are always deeper stuff that can be understood and researched and so on. So in the next videos, we'll go through some and use some P parsers tools. And yeah, that's it. So thank you very much, and see you in the next videos. Hello everyone, welcome back. In the previous video, we did a general overview on the P structure. In this video, we'll go and use the Total PE tool written by Pavel Yusefovich in order to practically parse and dissect the P information. So let's do file, recent, or just open the file that you want. Here I can use it from the recent file, and I will open demo labs, the executable that we compiled in our first lessons. So in the start of the opening of this file, we can already see some important information like the file name, the path, the file size, the time and date stamp, whether it's 64 32-bit, for example, which is very important for us to understand whenever we want to, for example, disassemble P executable or a DLL, want to choose the right version of our software. For example, if we use IDA for reverse engineering or disassembly or even debugging, want to use the right version. For example, if it's a 64-bit executable, we'll use IDA 64. And if 32-bit, we'll use other type of disassembler of your use. We have the number of sections, like we have the text section, r.data, pdata, resource, and reloc in those case. The pdata section refers to the debugging symbols or information of the executable. Can be also potentially omitted from the file in the compilation state, or can configure it in Visual Studio, for example, to not include this section, and the all of the information resided there, to be more um, evasive, or for the attacker, for example, to not disclose his paths or some suspicious strings and stuff like that. And we have the resource section, which also can be basically, it can include GUI stuff like the icon of the file, size of the icon of the cursor while using the software and stuff like this. But it can potentially also hold malicious file inside, and shellcode that can be loaded from there. For example, the WannaCry ransomware, very like common there, that you will see in the resource section. You next stage malware that is actually opened with a zip password in runtime using the um, resource Windows API functions, find resource, lock resource, load resource, and size of resource. All of those 4 Windows API functions are used to actually extract the zip content that is hiding in the resource section in the file. Just a general example I gave you. If you want to see, you can go and refer to one of my free YouTube videos on WannaCry. So yeah, so basically this is it. And one of the important things also to notice here, that we have this entry point value. So we have this 13A0. Basically, it's um, referring for where the code is actually starts to be executed, where the process is loaded and start to its execute. So before we go into it, let's also check our imports here. So the imports here is basically holds the functions that are imported on runtime and potentially executed. So for example, we do click on kernel 32 DLL. Don't be confused. It's not for the kernel. Actually, it's like it's basically user mode Windows API functions. It's Microsoft has their own reasons why naming it kernel 32, but whatever. So you have all of those functions here that are imported to this file, but it doesn't really mean that those functions are actually executed on runtime, because if you remember our source code, you didn't see that we use, for example, is debugger present, checking or doing anti-debugging stuff. So why it's here, you have many reasons why, but the compiler and linker of Visual Studio specifically decide to put it here for whatever reason, and that I will not go into details in this course. Um, yeah, but it's important to understand that not always that the fact that you see this imported function doesn't really mean that it will be executed. You can validate it on either, for example, if you go to imports, you can go and search for example, we go to imports, we can search for is debugger present, double click here, and now we're actually in the iData section. As you can see here, we have uh, it's another thing that is like very interesting. Like you don't really see here an iData section. Think, okay, maybe TotalP didn't parse it or whatever. So the file doesn't really has an iData section, but for IDA inner or internal usage, it will name the functions and put them under the iData section. So it's a section that is basically created by the IDA and is part of the IDB file, or the database file of IDA. So not really there, but for IDA it is, so whatever. So we see the isDebugger present. If we do X or cross-reference, we'll see that is part of this SCRT, fast fail, whatever. So you don't really see it as part of the text section. So most likely it will not be used in the code, will not be executed, as you can see. And so it's like, yeah, we see it's under text section, but not really, it will not really be executed. So if you want to validate it, you can put a breakpoint and basically run the code. Of course, it's on. Be sure that you run the malware or the file inside. If you're sure it's malware, of course, run it on a virtual machine and be safe about it. And there is a potential that until this point of the code, whenever it will be executed right now, malicious or whatever code will be executed. So make sure you know what you're doing. So now I'm putting breakpoint on is debug present, and nothing really happened. The function is not because if it were used, you will see the breakpoint were hit here. So nothing really happened. So this is a validation of a function used and do for yourself. So yeah, this is for this. And for example, if we take the, if you remember, we saw in the code, we didn't really see printf, but we saw a different version of it. We saw vf printf. Okay, so this is what the Visual Studio decided to actually import from this API MSO insert stdio.dll. So we can basically go into, again, to imports, search, to printf, double click, do X for cross-reference, and see where it is actually referenced in the code. So you can see it's referenced under two subroutines, sub whatever, and another basically in the same place, and another place in the rdata, which is basically an RVA to the IAT, to the import address table. So it's not actually the call to the function, but it's the part of the IAT or the import address table of this function. So if we go back, escape, and doing another X for cross-reference, we can double click on it and we can see that it's part of this function. If we do another X, we can see who is the caller function of this, for example, who's calling this sub function. Okay, so we can see that main calls it a couple of times, which makes sense. As we can see here, we can rename it for printf, or in for our purposes. And yeah, so you see here the vf printf is actually used. So now if we put a breakpoint here, of course it validate that it's actually used in the code. So now we have a console here, we do this F8, and voila, we have this for loop printed in the screen. Let me stop the debugger, the breakpoint, and get back. So if you remember, we talked about the entry point, 13A0 in this case. Okay, so the entry point is basically where the code actually starts. So a lot of people can think, okay, so if I do space, I can see the addresses here. So it is logical that, you know, the code will start in the main function, because, you know, we wrote a main function, the Visual Studio or whatever IDE we use, or even Notepad or whatever, the code itself. It makes sense that it will start in the main. So we'll do space, and no, not exactly. Don't really see it reference to the same address. See here. So basically, when we're using this 13A0, we're searching for the last four of those values. Don't check literally for those values, because this is the basically the address that can be changed or loaded. It's very dependent on the executable and how it's compiled and other parameters. But the value that you see here in the entry point is basically on those four, in the place of those four values. So basically, if we go back to our main, double click here, space. So basically, we want to traverse back and understand who calls main, or there's a couple of ways to do it. So first of all, we can do Control E and see all of those entry points that are available. So we see there is a function named start. If we see the address, we can see that is reference to this 13A0 address here. Basically, we can conclude that if we do double click here, we can, okay, we see some code, then we see a jump here, and it does some security checks and some standard code that the compiler and linker of the Visual Studio in this example, you know, decided to put inside the code. There is a potential for hidden functions and malicious code to be executed in those parts of the code. There are research done about it, but I will not go into those details in this course. But Generally, nothing really interesting in most cases. Well, actually happens. And eventually you come to this call main. And there is the main function. Okay, so one of the ways is do control E, and another way is basically to select main, do X, and see, okay, who is the caller function who calls this main function. So if we do again, if we do X and double click on it, we'll see that the function that calls it, this SCRT, whatever function, SEH, and if we do X on it, we'll go back to start. So in this way, you actually traverse back the calling function or the execution kill chain of your code. You can, okay, so this function called that function, enumerate relevant places or regions of the code that are in interest for you. Again, I'm trying to like putting things here in simple manners as much as I can. Really depends um, on your attitude and the time you put on it, the efforts. So yeah, this is basically about it. Thank you very much for watching this video and see you in the next one. Hello everyone and welcome back. One of the most important things for a researcher or malware analyst in general is to identify or to know how to identify different file types. So let's take example that we need to differentiate between two P files. One is a exe file and one is a DLL. So a lot of people will say, yes, so an exe file is with a .exe extension and a DLL is with a .dll, but yeah, actually know if it's .dll or exe, be an attacker or whatever it was, changed the extension of the file. Maybe it got or found a new way to bypass systems or manipulate file extensions while they're exe, running them as a DLL or filed as a DLL, exe, whatever. You have different types of attack vectors and other unexpected behaviors that you can find in Windows. So let's try to understand the things in a manner that we can. So, and of course, show you some ways to identify different P files. So for this example, we'll take an exe file, the demo labs that we used, and AMSI DLL. Okay, AMSI, for those who don't know, it's part of the basically a DLL file that is posing interesting functions to be used by antivirus and EDR vendors. For example, it is used by the Windows Defender antivirus and has functions like the AMSI scan buffer and scan for potential malicious code and PowerShell scripts, script, stuff like this. And yeah, it's an interesting DLL and very important ones, especially for red teamers and attackers that want to know how to bypass um, stuff like this, functionalities in those DLL or their payloads or malicious code to not be identified, detected, or prevented. So notice talking here about tags, like a lot of people think, okay, I'm an malware analyst, don't really need to red team how the attacker mind or how attackers are actually working, what kind of tools and tactics using. And it's incorrect, fundamentally wrong, because as a malware analyst or as a researcher in general, you need to understand how attackers think. So you need to go into their head, their craft. This is one of the things that are very important for give you to explain to you. I have one of those videos on YouTube talk that I did on B-Sides Las Vegas called Malware Analysis Red Team Edition and the power of malware research in red teams, how also use red teams and blue teams. Give you a different perspective. So try it out. So if we use it in hex editor, we see, okay, we have the demo labs X and we have AMSI DLL. What's really the difference here? We have this MZ header, we have this program cannot be run in DOS mode, we have the P header, we have the sections. Don't really have any other indications where it's a DLL or an exit. Both them are P format, but we don't really know how to differentiate them here. We need to use different tools that does the job for us or helps us. Things like so. Again, we're back to total PE. We see here in the left pane, I loaded the run DLL32 exe, which by the way used a lot by malware to load and execute malicious DLL files. It was one of those execution vectors that used very commonly by malware and attackers in general. Okay, so we see it's so basically one of the things that we can identify right away is that the run DLL32 exe has only imports. So it imports functions for different DLLs, but the AMSI DLL, of course, it has imports also because for functions, but it basically exports function. Talked about the AMSI scan buffer that is exported, can be used by antivirus and EDRs, and attackers can try and find ways to bypass it, unhook it, or whatever, and or do some string manipulation of a different course. But you see basically that we have export. Most likely, whenever we use, whenever we research a DLL, we'll have export. And but it's not necessarily always the case because exes can have also exports and imports. Not the case. Okay, so let's find another way. So we can, for example, use IDA to identify the code blocks and see different things. As you already understood, I really found and like using IDA as my disassembler and debugger. Also use other tools like x64dbg for debugging purposes and WinDBG for rootkit analysis and kernel mode stuff. If I go here and let me load here in the Windows System 32 and load the DLL, copy it to desktop and load it from here. Copy the version of it. And one of the immediate things that you can identify is this DLL entry. Most likely will not see an exe file. Okay, so yeah, you have imports, right, and you have exports, which again likely will not see an exe, but can be that you have an exe file and can have an export some ways. So one of the things that you need to go and identify is whether you have this DLL entry point start. So if you have DLL entry point, the DLL. We have, if you have different like starting with like start or main or win main or other weirdo stuff, which is not DLL entry point, most likely it can be exe file. Okay, so those are the basic ways to identify whether it's a DLL or an exe file. Using a p parser, where check whether you have exports, and of course if you have this DLL entry point or not. Thank you very much for watching this video. See you. Hello everyone and welcome back. So let's ask a question. What is the purpose of malware analysis? So there are a lot of purposes. It can be used as part of the blue team side and also as part of the red team side. So if we're talking about the blue team, it can be part of a vendor or a product company, such as antivirus, EDR company. And it can be also as part of a service company such as incident response or DFIR, which stands for Digital Forensics Incident Response. So there are some tiers in blue teams and SOC companies or Security Operations Center. There's tier 1 for the analysts that receive the alerts, which most of the time will aggregate them to a tier 2 incident responders, and from there we'll aggregate, if needed, to more advanced and senior levels of researchers, can be malware researchers, threat hunters, and stuff like this. So what is the goal of malware analysis in blue teams and in red teams? So in blue team, it will be mostly to identify the type of the malware, to understand what kind of action it does in your system, find it, building a detection rule, and basically providing some remediation process for the incident response team while tackling the incident in the client's premises. So this is one of the reasons. Of course, there are other reasons for PR or public relations, blogging, and stuff like this. And for red teams, it can be also great to know malware analysis, to basically have the knowledge of other malware and the use of other techniques or TTPs. So for example, I can take a malware, reverse engineer it, analyze it, understand its execution kill chain, and re-implement those techniques or TTPs in my own malware that I'm using as part of red team engagements. So the 4 most basic things that are used for malware analysis, or the reasons, are classification, fingerprinting, which is the first step to determine the type of the malware, whether it's Trojan, worm, etc. The next thing will be to detect whether it's packed or not, because like one of the reasons that you need to first identify whether it's packed or not, it's the same reason that you don't want to, for example, know a person by its mask, but you want to know the person himself. So basically, you don't want to research the packing or the packed version. You want to research the unpacked version or the clean version of the actual malicious code. Of course, it really depends. If you're an antivirus or EDR researcher and you want to implement an automated approach or basically write an unpacking engine to unpack specific packers automatically, you need to reverse engineer some packers and to know how to automatically unpack them. So it really depends on the goal you're using. But as a regular malware analyst, you want to first unpack the malware, and then the real malicious code is revealed. Then you can go and extract IOC or indicators of compromise in order to create better detections and sign it based on those extracted artifacts. And in the end of the day, you want to create a detection rule or a signature. It can be a static signature. It can be a dynamic signature that sign a behavior on the system. In the next video, we'll talk a little bit about how vendors are naming their malware by their types, what is a variant, and a malware family. See you in the next video. Hello everyone, welcome back. In the previous video, we talked about the reasons and goals of malware analysis, and we talked about those 4 reasons: classification, fingerprinting, packing detection, extraction of IOC, and the creation of a detection rule. So one of the important things to understand is how antivirus or EDR vendors basically name their malware families and variants. So think of a malware family as a group of the same malware. Let's take an example, the DarkSide ransomware. DarkSide ransomware, the family of this ransomware. So DarkSide, for example, the type of the ransomware, which determined not only by its main goal, which is to encrypt the computer, but also by its capabilities, which can be also a Trojan, worm, and stuff like this. But the main goal is chosen mostly for the determination of the type of the malware. So DarkSide is a ransomware, and the family is called DarkSide, and there are different types of variants. So it's like taking COVID-19 or coronavirus, and you have different variants and types of viruses. The same goes for the malware world. So let's take an example. We have here the DarkSide ransomware. So basically, each vendor has their own naming convention, and sometimes they are descriptive and sometimes they're not. But they can sometimes tell us a lot about the detection or the way that the vendor's naming their malware. So here we can see this ransom something, which is basically the type of the malware. Win32 is the platform that the malware is running on, which is basically Windows. Then we have the, it can be the variant name or the family, whatever. And then we have this DA, which I actually don't know what it is, but it doesn't really matter. I can understand that it's DarkSide and it's for Windows and it's type of ransom. So it's just for the basic example. And basically you can read the summary about this ransomware and then some, steps to do in order to remediate maybe this attack and etc. And we have another website which we'll also use as part of our analysis. It's called VirusTotal. So in general, if you go to virustotal.com, this is the screen that is presented to you. You can upload a file, you can scan a specific URL, and you can search for other things, for IP addresses, domains, file hashes. And basically, it really depends. If you put a URL or an IP, it will use different scanners. If you upload a file, it will use and basically submit this uploaded file to different antivirus and EDR vendors. And it will basically tell us whether there are detections and of course, what is the name of the detection of the specific vendor on the specific malware. So here we have the DarkSide ransomware. We have the SHA-256 hash. We have the name and some tags of the malware. It can they're not always correct here, but you can use them in order to determine and understand what this malware actually does. You have the size of the file, the last analysis date. Basically, if you do here reanalyze, it will reanalyze it again. So if we do reanalyze, it basically goes, submit or resubmit it, or basically rescans it, okay, again, and we can see if the detection gone lower or even greater. So it can also be great indication for us which vendor actually detects it or not based on the detections capability they possess. Okay, so for example, if we'll take I don't know, for example, Skynet, we can see here malicious core 100. Doesn't really tell us a lot, but maybe it is part of their machine learning engine or other type of engine, whatever. If we go to Elastic, we can see here Windows ransomware DarkSide. They're very straightforward here. They don't have any specific for the variant, but they recognize it as DarkSide. F-Secure calls it crypt, and because it kind of makes sense because it encrypts stuff. And maybe they have a reason they calling it a Trojan also. Maybe like tries to masquerade itself as a Trojan. Like for example, we took the WannaCry, tried to masquerade itself as a disk partition utility or whatever, but it actually was a ransomware. So we have the details, so the hash types, and the creation time, this first submission of this specific file, the last submission, and the last analysis. So as you can see here, in the 2nd of August, this is the reanalyze that I did earlier. So this is the updated version now of the scan, and it goes and takes some basic data. And for the dark side ransomware, if you go and see my YouTube video on it, you can see it kind of the same. You have here the current 32 DLL with the exit process, get proc address and load library. You can understand from this that it will go and do dynamic API resolve, and basically tells us that the attacker wrote an API hashing or API hash algorithm, which basically hides functions from the IET or the import address table. And as you can see, you don't have any other functions here, which is very odd. And the load library and get proc address, so Windows API functions are used to basically dynamically resolve those functions. So if we go to virus total, for example, and do a search on WannaCry, you will see different thing, of course, but if we go to details, we'll see that we have more functions. It has its own packing mechanism. Basically, it's part of the resource section. They hiding another zip file, which inside the resource section, which has another PE file. Most of the times, don't catch me by my word. And again, we have a lot of different variants, and we can see here that VirusTotal uses also other engines like Detected Easy, and it recognizes that it's compiled with C++. We don't really see it here, maybe because the reach header part of the P structure is omitted. And again, those are the things that we can go deeper and analyze and do reverse engineering in order to understand those stuff. And of course, if you watch the videos where I show you about the P parser tools, like for example the total P that I showed you, they will give you the same basic information as you can see here. So this is a basic example of how those things are presented and how you can use this as part of your analysis. You can also have the relations here. You can see the relations to contacted domains, IP addresses, and other downloaded files. For example, it's very common that the dark side ransomware create this ICO file, which is used as the icon for the files that are already encrypted. Okay, and it's thrown to some path and then configured as a default icon in Windows via registry key. Again, I'm telling this from my experience and from researching this ransomware, so I already recognize this type of behavior. It doesn't really mean that if you see something like this or ICO, it will be dark side, but you know, add those captchas. Okay, so you need to have as many as indicators as possible to actually have a verdict and decide whether it's this type of malware or that type of malware and create the signature for it. We have another tab here called behavior, which is for it's basically some of the sandboxes that VirusTotal implements in their systems, and it can give you like dynamic analysis or automated sandbox capabilities for those malware, and it can give you some good overview on the malware, and can really help you also to use as part of your reports and understand which type of ETPs are used and stuff like this. And we have the community tab, which basically bots or other people can comment here and share their thoughts. So this is also another overview of so this is a generic overview of VirusTotal and how detections are basically called or named in different vendors. So yeah, for example, here we can see in Kaspersky we have this or heuristics. So here we can maybe understand that Kaspersky detected it based on or on their heuristics engine. And again, there are vendors that are very descriptive in their names, and then again, there are other vendors that are not so descriptive. So this is basically about this video. Thank you very much for watching. See you in the next ones. Hello everyone, welcome back. I want to talk to you about the difference between IOC and IOA, what's so called indicators of compromise and indicators of attack. And the next thing that I want to talk to you about is about a framework that's called Attack Miter. So an IOC or indicator of compromise is basically a set of indicators or artifacts that you can base your signature on. So it can be strings, a path to a file, the file name itself can be a hash, can be an IP address, URL, domain, everything that you can extract from the malware. It can be a Windows API function name, it can be an offset address, it can be a hexadecimal or opcode series of opcode or hexadecimal assembly code that you extract from your disassembler, from your hex editor to find this malware. And we'll go through some examples in the next videos. And an IOA or indicator of attack is something more generic. It's basically talks about the attack kill chain itself and the tactics that are used by the attackers. So, and it's all connected to Attack Miter. So by explaining you about Attack Miter, you can understand what it's an IOA. So this is the attack matrix, basically what you see here. And as you can see here, there are basically steps to an attack. Any attack starts with a reconnaissance. It can be either basic reconnaissance or very extensive reconnaissance. It really depends on the goals of the attacker and the time and resources you have. So then we have the types of reconnaissance or the techniques to use for reconnaissance. And for example, we go to active scanning, which is for, understanding whether a server is up or down, which kind of ports are open, stuff like this. And for each technique, you have an ID, basically, and you have also sub techniques. So you have the technique number, which is T1595, then 0.001, 002, etc. Okay, scanning IP blocks, vulnerability scanning, world scanning, and so on. You can access to each one of them, and you can have an explanation on this type of technique or TTP and some examples of attackers or tools that are using this technique. So if we go back, we can see that it goes through reconnaissance, which is gaining as much as information as possible on the victim. Then you have the resource development for tool development, malware development, stuff like this. Then we have the initial access, which is the vector from which we actually breach the target or the victim, which can be from email, from an SMS, from USB, so on. Then we have execution of code, persistency, to basically persist in the system whenever they try to, the victim try to restart the computer, try to delete your service. It will have its persistence, can be used as a backdoor to access the system in the future. Then we have escalation of privilege, so which is basically what's called so-called EOP, or in short, escalation of privilege or privilege escalation, basically. And you have different type of privilege escalation. You don't have everything here, of course. There are things that need to be updated and maintained here. But it's a great way also to understand the techniques and to also use this as part of your report. Defense evasion, credential access, or kind of self-explanatory. Discovery, which is an internal reconnaissance of accounts, groups, Active Directory, SIDs, permissions, OUs, stuff like this, containers, um, storage blobs of cloud environments, and the list goes on and on. Lateral movement, to laterally move between different computers and resources, collection of data, which mainly focus on information stealers or info stealers in short. Of the command and control, which is basically the functionality or the ability of the malware to communicate with an external CNC or C2 or a command and control server that is controlled and managed by the attacker. We have exfiltration of the collected data or whatever, and we have the impact. Impact can be removal of backups, can be a disk wipe using a wiper, and it can be a ransomware attack, of course, and stuff that are basically impacting the business continuation or the operation of the business itself, which lead to financial loss and stuff like this. Okay, now just want to share with you also a tactic that I've added here with the cooperation, of course, of AttackMiter. You can see here my name, and basically this technique that I'm using for a decade maybe, decided to publish it. I believe there are many people that know about this before even I got to publish it, but want to share it with the community. So you can use this KeyMGR DLL, basically run this exported function from this DLL and back up some credential stores or both like cookies, then basically recover them in your own attacker machine and hopefully have access to other assets of the victim. And also have a POC video on my YouTube channel if you want to see it. So just to have a summary, so if we talked about IOC, which is a collection of indicators to base our signature or detection logic, an IOA or indicator of attack, basically the way and the techniques used by the attacker in order to achieve his goals. This is in short. Thank you very much for watching this video. See you in the next ones. Hello everyone and welcome back. In this video, we'll learn how to identify different file types using a hex editor. So a hex editor, like I'm using here, HXD, is basically a program that can inspect content of files in their hexadecimal representation and in their decoded text, and can be very helpful in our analysis. So you saw me in the previous videos that I, for example, load an executable file and show you that we have this MZ or 45A in hexadecimal, which basically represents a portable executable or PE file in short. And we can identify the actual file type. Attackers tend to change the extension of the files. So for example, they can make it look like it's a PDF, like you see here, but it's not. So most of the victims, they don't have this file name extension enabled, and they can think that, yeah, it's a PDF, but it's not. And even the icon is changed here. So let me just again put it a PDF like this. Yeah. And if you double click on it, of course, you will have an error because Windows expects it to be a PDF by its extension. It's not like Linux or macOS that are not expecting any type of extension. Windows expects the right extension. There are ways actually to use one extension and make it in some ways even execute different file types, but it's another topic to talk about. So if I load it inside HXD, we'll of course see it's a PE file as before, but people who do not understand this and think that, yeah, if it's .pdf, it's actually a PDF, they will fall a victim. So let's change it back to exe. We just enable it here. And we're back to business. So, of course, for different file types, we have different magic number or magic value. So here we have the list of file signatures. It's a great page of Wikipedia with fairly documented table in which documents different file types and their magic value. So for example, I want to understand what type of P files I have, so I can search for portable executable, or just for an exe, and see that for the 45A or MZ signature, we have different file types. A lot of people also don't know this. They think that they have only exit or DLL, but you have a lot of more. MUI and SYS for drivers, SCR for screensavers, which can be used for malicious purposes, CPL files for control panel, and so on. So all of those extensions are based on the portable executable or P file format, which is represented by this MZ and or 45A. So it's very, very important to understand this and to distinguish between different file types. And one of the first things, or the first thing that I do whenever I search or analyze malware or a suspected file, I put it on inside a hexadecimal viewer or a hex editor, basically. And in that way, I can understand what I'm tackling. So thank you very much. In the next videos, we will continue with our journey. Hello everyone and welcome back. So we are progressing in our course and basically building the fundamentals to actually go and start analyzing malware. So before we get to the videos where I will show you actual malware analysis, we are building those fundamentals. So in this video, I will talk or teach you about hashes. What is a hash? A lot of people have this problem identifying the difference between a hash and encryption. Let's first of all talk about encryption. We have two types of encryption. The first one is symmetric encryption, which the same basically the same key is used to encrypt data and also to decrypt the data. For example, if I create a zip file with a bunch of files inside it and compressed, and I put it with a password, the password is actually an encryption key. So for example, if I take all of those files, put them inside an archive, I choose the compression algorithm or the archive format, and if I don't put a password, of course it will be compressed, but if I put a password, it will be compressed but also encrypted. So I'll do here test 1 2 3, test 1 2 3, and I can choose the encryption method. I use the AES-256, for example, that widely used also in Wi-Fi networks, for example. So again, in the Wi-Fi, when you put a Wi-Fi password, is actually the encryption key, which is a symmetric key, which means that the same key used for encryption is the same key used for decryption. So I put everything in the zip. Again, I can put it inside the hex editor to inspect its content, and I'll see the magic number of zip files or even other files like RAR and even the docx, xlsx, or all of those Office files with the X in the end of their extension. They're actually an archive file. A lot of people also don't understand this or don't know it actually. So the 54B is actually PK. You can also see it on APK files on of Android packages. So you also see their PK. You can see there's a bunch of mumbo jumbo data or random data with naked eyes. You can see here, and basically it's compressed, encrypted, or even both. So that seems like a regular file with sections and stuff like this, for sure. Now I want to decompress it, so I'll go do extract here. Well, let me just create a folder, put it inside, and extract it using 7-zip. And it will require me a password. If I don't know the password, of course, it will not work. So if I'll try, it will, of course, will not work. So, and 7-zip, they have this type, this thing, they first throw the what's it called, the objects of the file, but it's not actually the file. I don't know why they're working that way, but we don't really need to care about it right now. So if we do extract here and put the password test 123, it will actually go, and as you can see with the size here, they're actually the files, and they're decrypted firstly, and then decompressed and dropped inside or into the file system itself. Okay, so we can delete this folder, and yeah, so basically this is for symmetric encryption. And then we have an asymmetric encryption, which is basically what we see in websites. Like if we take here virus total, we can see here we have this connection is secure, and you can see even the certificate and everything. I'll not go into details because I believe most of you already know those basic things, but for those who don't, asymmetric encryption is basically using different keys, or actually a pair of keys, two keys. One of them is used for encryption, and the second one is for decryption. We have what's called the public key and private key. Of course, if you want to understand more about it, you can search Google and learn about it. Okay, so it's a different type of encryption. So now I understood what is encryption, we can understand how it is differentiated from hash. So hash is basically a mathematical calculation of some sort of data. It can be a text, a number, any kind of ASCII character, or even a file. Okay, so we have different type of hash algorithms like MD5 and SHA-1, SHA-256, and so on. And basically those hashes are used for different reasons. For us malware researchers, it is used to actually part of the fingerprinting process. So we want to, for example, search or research this file and distinguish whether it's like malware or a benign file. One of the first thing we want to do is actually calculate the hash. I'm using here a program called Hash My Files. It's also part of the Flare VM that we already deployed. And you can see it calculates different hashes, or basically a hash for this specific file, but based on different algorithms like MD5, SHA-1, and so on. So basically you can use those hashes in your own reports to refer to those files. So now you can go and create another file of this demo copy and write a different type of data. And even if I put a space or even something little, I will change in the file, whether it's through an hex editor or through the editor of the file type itself, it will be with a different hash. So a hash is used to identify different files by their data. Another important thing to understand about hashes, they're one-way algorithms or irreversible algorithms. So basically you cannot revert back this hash because algorithmically or mathematically you don't have an encryption key or a functionality to reverse the value or the file back or whatever it is. Okay, so one of the I had one of those students that asked me, yeah, but you can crack hashes using John the Reaper and Hashcat, and yeah, and then of course what I'm going to explain here is like, okay, so let's take, for example, let's take MD5 calculator just as an example, and let's calculate the hash of admin 123. Let's say it's a password. Okay, so this is the MD5 hash. Now let's say you breached or hacked to some computer and you found some way this hash. Okay, so what? I want to basically crack it. Now, you don't really crack a hash. You guess, or you actually check if this hash value is, if it exists in a well-known database with well-known hashes, with their well-known clear text passwords. So you're basically guessing passwords. Because cracking can be deceive you. You can think, okay, I'm actually cracking the algorithm, but no. So you copy this MD5 hash, and now you can say, okay, I go to an MD5. They call it MD5 cracker or decryptor, but it's, as you can see, cracking or decrypting, but it's not accurate, but we don't really care about it. Do crack hash, and voila. So yeah, we have admin 1, 2, 3, but let's add some complexity to it and do something very like this. So now we think, okay, so I have a calculated hash and I found it, I don't know, on some sort of a breached or hacked computer, and now I will crack it. But yeah, not found, because it's not a so well-known password as admin 1, 2, 3. So yeah, this is for hashes. And of course, whether you want to actually go and see if this file is already submitted to VirusTotal, you will go and copy its MD5 or SHA-256, whatever you want, and do a search. And of course, I didn't really upload this file, so I don't have anything here. But and if I don't have the hash of the file, so I can go basically take the file, upload it, confirm the upload, and of course the scanning will start, and all of the mechanisms behind VirusTotal, different antivirus engines, vendors, and the automated sandbox, and all of those systems will start to do the analysis. So yeah, this is basically the explanation about hashes, how they're used, the difference between hash and encryption. Yeah, this is it. So see you in the next videos. Thank you. Hello everyone and welcome back. In this video, we will learn how to extract strings from files. I'm here inside my virtual machine, and you can ask maybe why, because in the previous videos I was in my host. But this time, and from now on, we'll go to research actual malware. In this case, we'll have the space1.exe, which is actually a variant of FloatAmy, which is an interesting malware, which is basically based on the Amy admin legitimate software, which its source code was leaked allegedly, and basically attackers took this source code and created their own malicious version, and of course someone decided to call it FloatAmy. Okay, so let's basically go and learn how to extract strings. Of course, we can always use our hex editor and extract strings maybe from the hex editor if there are any visible strings, but as you can see, it can be sometimes hard. So let's use the better method. Let's go to our desktop, and we have the sysinternals built in. It's actually a suite that you need to download from Microsoft, and the suite includes the strings.exe utility. Of course, in FlareVM, it's there by default. So you have different parameters or options that you can use here to do only ASCII search, which is not in your interest to do, because you want to also search for Unicode characters to have broader and deeper results. You can also search for bytes and start from a specific offset and other stuff, but what I'm actually doing is a very, very simple and straightforward approach. Basically run strings on the file you want. It can be any type of file, and output its content into a text file, and opening this text file inside text editor, but I like to use the Visual Studio Code or one of those text editors that has this right pane. As you can see here, it can identify, okay, there is something long here. Maybe I can go here and oh, voila, I see here something strange. Now see here processes names and DLLs and other stuff. I can go here and see more stuff, which I need to make sense out of them, of course, but again, it can give me some clues where I'm going here. So it's one of the first things that we want to do is actually go through those strings and can tell us a lot about the functionality of the file, whether it's packed, encrypted, obfuscated, compressed. Because if it's encrypted, you will have less strings. You have different bunch of data. The fact that you see those type of data doesn't really mean it's encrypted or something. Maybe it is, but again, everything is pulled into a debate, especially in the research fields of cybersecurity, especially in malware research. Everything is in debate. Okay, of course, we have the fundamental basic stuff you need to understand, but always have this state of mind of questioning not only others, but first of all, questioning yourself, your own methodology, your own way of thinking. Be self-conscious and become better and better in each research and analysis that you do. Always think, how can I detect it and prevent it and maybe weaponize it in my own, white hat, red team engagements, legit stuff. I don't want you to be black hat, but of course, anyone is free to do whatever he wants. I'm not an educator or something in that sense, but yeah, so basically, those strings can be, of course, used as an indicators of compromise, as an IOC to sign the file. And of course, to identify stuff like this. This program cannot be run in DOS mode or it's a PE, but again, it can be also implemented just to make it to be a make-believe of a PE file, but it's actually a different file. So again, always seek for more data. Okay. So this is a very straightforward and simple video. We are very close to getting our hands dirty with real malware and with full approaches. So thank you very much. See you in the next videos. Hello everyone, welcome back. In this video, we'll learn how to identify whether a P executable or any type of other file is packed or not. First of all, what is packing? Packing is the technique or tactic, or call it whatever you want, to take a file and take his code or the code section, or on the most of the case the text section, and in some way obscure it, make it look differently, press it, crypt it, or even obfuscate it with different type of algorithms. Okay, so the general role of packers in their legitimate sense is compressing the code of the file. So it's not like taking a file or several files and put them inside an archive like zip or rar, but taking the specific code of an executable and pack this section of code only. And this way you can hide the intent of the code statically and also save some space on the hard drive, the SSD, or the file system in general. So we have here two files. We have the regular and legitimate calculator exe, which, as you can see, I'm executed it and it works. And we have the float amy space1.exe. So in this video, also in the next videos, it's very important for you to understand how to really identify whether the file is packed and the why behind things, not only using this tool or that tool, but to understand the reasons behind them. So if we phone hxd, for example, we can put the calc exe and the space one. As you can see here, they're both an MZ or a P file without too much of a difference. But if we go to space one and you search for just go through the data here, you can see some sort of a gibberish going on here. Now you can say, okay, the same goes for calc exe. We have also places with gibberishes like here, but you can identify some difference. In the gibberish of the calc exe here, you can visualize that you have different behavior. You can see some sort of data here, and there are some dots behind it, or zeros, or other definitions here. So not so random. As you can see, you have a lot of those going on, and a lot of other data that repeats itself. So it's not so random. So the entropy value here will be lower. Now you can ask, what is an entropy? So entropy is a mathematical calculation to detect whether or how much random data there are. Okay, so if we go to space one, you can see there is a high chance of randomization here, because you have this S, then D, U, O, and you can see a lot of gibberish, but they're also randomized without a consistent pattern. And you don't really see a lot of spaces between all those dots, as you can see here. Something is really going on here, something really weird. Now, let's try to identify it inside a tool called Detected Easy. Let's spawn Detected Easy. And first of all, let's load calc exe. And you can see it detects that it resides for, or it's actually compiled or linked with the Visual Studio 2019. It's actually parsed from the rich header of the P structure. And also for you to know, it detects the fact that it's Visual Studio based on predefined signatures that are inside Detected Easy. So we go into entropy, you'll see that we have two-level entropy calculation. The first level is the overall calculation of the entropy of the overall of the file. It takes all of the sections, all of the data, and basically calculates whether it has high entropy or not. So the value of entropy is between 0 to 8, or actually 1 to 8, and if it's higher than 7, it will be considered packed. If it's lower than 7, probably it will not be considered as packed. But you don't need to actually take this as the only indicator whether the file is packed or not. Because if you take a zip or RAR file and put it inside Detected Easy, of course it will be packed, because actually use the compression algorithm to compress the archived files. And of course, whenever you use compression, there are a lot of gibberish or random data goes on there. So it really depends whether it's a general packer like a RAR or zip, or it's actually a code packer like UPX, SPAC, SProtect, Armadillo, and others. So the second level is the per section entropy calculation. And as you can see here, all of the sections have lower than 7 entropy value, so they're not considered as packed. So now let's spawn another Detected Easy window and open space one exe. And of course, it will detect that it's compiled and linked in some way, because it has the rich header. If we can use here, for example, the very famous and known tool called PEBear of HasherZ, and you can go here and you have this rich header, and the rich header actually contains what type of linker, compiler, etc. Attackers sometimes tend to actually omit this rich header for analysts to not have the information regarding what type of compiler, linker, or even an IDE were used in the writing and compiling and linking of the code. So go here into the entropy, you can see the overall calculation is packed, but as you can see here, most of the sections here are actually not packed, but we have only one section. It's called the resource section, which is packed. Now, because here we're tackling the resource section, we have another tool that's called Resource Hacker, which basically created specifically to read data from the PE resource section. So if it were a different section, this tool cannot be actually used. So again, if you see something in resource section, it's interesting to use the resource hacker. It can be very helpful. So let's load in it inside. We have to place in this we have this RC data. We have something gibberishy here, and we have another place which can take some time to load because yeah, here you can see something very strange here. It's not regular. It's not an icon because you know legitimate stuff inside resource section can be icons or you know this manifest, for example, and stuff like this. You can also see in the manifestor you have this request execution level. As invoker is basically whatever. If you're a regular user, it will be executed as a regular user, or if you're an administrator, it will basically inherit the same permission. Whenever you do double click on it, it will inherit the same permission you have. You have another called for administrative or administrative access. So whenever you go and double click on it, it will prompt you this UAC window whenever it asks you to press yes or no. And of course, if you press yes, this double clicked or executed process will inherit administrative privileges, which can be potentially risky here. So it's actually a legitimate thing inside a file, but whenever you have this gibberish or encrypted or compressed or any type of other obfuscated data like this, it's suspicious. Okay, so this is basically how you can identify whether a file is packed or not. The next videos I will show you how to use IDA to identify between packed file and a regular file. Thank you very much and see you in the next video. Hello everyone, welcome back. In this video, we'll learn how to identify whether a file is packed or not using IDA. So in the previous video, I explained to you that basically the general or legitimate reason for a packer like UPX, ASPack, SProtect, and others is to take the code of the file. In most cases, it will be under the .text section in the P format and run some sort of an algorithm, like a compression algorithm, to save some space. And of course, it can be used for illegitimate purpose, like hiding the actual intent of the code and making the life harder for antiviruses, EDRs, and even malware analysts and so on. So in general, how a packer works. So we take packer like UPX, for example, and takes the code of this, for example, this calc.exe, runs a compression algorithm, and in some cases even renames some of the sections to different names. And the last important thing it does, it inserts what's called a stub code. It's a very small part of the code which used as the unpacking mechanism for the calculator exit to execute it. Actually need to be loaded by the operating system, or the code and all the sections on all the format need to be loaded and executed. So think of it like if we pack the file and we don't have an unpacking stub code, the operating system cannot really understand the code inside. The operating system cannot understand an encrypted or compressed code. It will basically crash. Need to have this unpacking stub, which actually translates, so to speak, this gibberish or compressed or obfuscated code inside a format or a code that the operating system can understand, load it, and execute it eventually. Okay, so we have the legitimate calc exe here. Let's execute UPX on top of it. So let's go to the desktop and do UPX calc exe, do -o for output. Let's call it calc packed. We'll differentiate it and use this for outputting this packed version. So if we use programs like, let's start with HXD, load calc, and learn the other one, the calc packed exe, they seems to have some changes. Here in the calc, you'll see the text section, RData, data, and so on. But here you'll see different sections. You will not see text, you'll see UPX. So it's very easy to detected. Sometimes attackers even change the section name to UPX, but it's not actually packed by UPX. They're using it to make your life harder. But here we can see UPX 0, UPX 1, and you can see here, let's start from this part. You see this UPX something, and you see like what seems a version number, whatever. So it's, yeah, it seems different. You can see a lot of those dots between those type of data, and it's not so randomized as you can see here. For example, it's more randomized and seems to have some difference. Okay, so this is one thing to consider. And let's now use the detected easy tool and open calc pact. And as you can see, it actually detected UPX with the 4.02 as we saw in the hex editor. And again, if we go to signatures here and we do UPX, we can see the signature logic of detecting whether it's actually UPX or not. So it goes and actually do p compare for entry points, or for hexadecimal values, or for section names, or so for some functions that are actually used, like get proc address, virtual protect, load library. You can read about each one of those functions in the Microsoft MSDN. Load library is for loading DLL files. Get proc address for resolving functions from the loaded DLLs, which were loaded by the load library. So they go hand by hand like a brother and sister. Virtual protect for changing the protection values of memory pages. Exit process talks about, basically does an exit from the process or terminates it. Virtual alloc for allocating new memory for the process or a new page. Virtual free for freeing the memory. And those are functions that are very common in Packers, actually. Okay, so let's try to see if they actually use there. So let's use the pbear tool and go to imports, go to current 32 DLL, and yeah, we have virtual protect, load library, get proc address, and other functions basically. Now you can see that there are lower functions and lower DLL than the regular calc exe. So you see less function calls. So it's another indicator for pack that the fact that packing took place here. Of course, you can rely also on the entropy value. You can see that we have here higher than 7 entropy value, and the overall it doesn't seem to be packed, but in the section specific level it is. So now let's go deeper and see the difference in IDA. So let's open our first instance, of course, with the legitimate calc exe. Do OK, and let's do another new instance. Let's put it here, new instance, and open the packed version. So here is another indicator. Whenever IDA throws a warning to you like this, some imported modules will not be visible because the IAT, or the import address table, is located outside of memory range of the input file. So it basically warns you about something very strange here. So if you see warning like this, it's another indicator to be added to the several indicators that you need to actually take into account, where to actually consider this file as being packed or not, and not to only rely on a specific tool or another. So now it will ask if you want to continue, because you cannot, it can't, translate this relative address. So we do yes. And if we actually check the differences, the first thing that you can notice here that is in this left pane, the functions window. In the original calc exe, you have a lot of more functions called here, or subroutines. In the packed version, we see a lot less. Not only that, if we go to the imports, we'll see, yeah, sometimes IDA or other tools have problems to displaying functions. As you saw earlier, we used bear and we actually saw the imported functions, but now IDA, for some reasons, don't really show it. But you will see the same functions in other instances that you saw in the bear. So you'll see lesser imported functions. And let's go even deeper. So now let's zoom in into calc packed exe and go into this call here. If we zoom out here using the control and the roller in your mouse, you can do zoom in, zoom out. You can see there are a lot of loops and jumps. You can identify them by this blue. You have an unconditional jump, which jumps whatever it, whenever the EIP or the instruction pointer of the program reach to this point or to this instruction, it will go and jump to the address that it referenced, in this case here. So it jumps in unconditionally, basically. Now you have conditional jumps, which you can identify using the green arrow here. So here you have a jump, but it's conditional jump because you have a comparison of a value, and if it's below or whatever, it will go and jump. If not, it will take the other route, which is this red one. So if it is, it will go green. If not, it will go to the red. So it's like true and false, basically. So basically you have an if statement, and then if this true, you go to the green. If it's false, you go to the red. So you see a lot of loops here. Okay, Uriel, so what? You see a lot of loops in other, legitimate stuff, but loops are part of unpacking process. So think of it like you have a zip file with, 10 files inside. You actually need to go and iterate through all of those 10 files inside the compressed archive and unpack them algorithmically and drop them into the file system. So in this case, we have the unpacking stub, which is this one, which is this piece of code, which actually goes and unpacks the packed code on runtime memory, allocates new memory, moves this allocated memory, and executes the unpacked original file. Okay, and it's what's called an OEP, or original entry point. So in the original file, we had one entry point and packed a different one. So if we go to bear calc exe, we can see that, go to the optional header, you see that the entry point here is one entry point, but go to the packed version, go to optional header, you have a different entry point. So it's where the code will actually start to be executed. Now, the original entry point is basically the entry point where the actual code will be executed while it's unpacked, after it's actually unpacked on runtime memory. Okay, so it's as a side note for you to understand the difference between entry point and the original entry point, which is taking place after the unpacking process. And the fact that you see a lot of loops here is because it goes through and reads packed data, iterates through them, and using the decompression algorithm that it has, it actually decompresses or decrypts or deobfuscates the data, and then basically jumps to the original entry point of the unpacked or cleaned data that the operating system can understand, load, and execute, and basically execute the calculator. So the original calculator here is running, and in the same way, the packed calculator is also running because it actually gone through loops, unpacked the data, So the operating system can actually load and execute it, and of course execute the original code from the original entry point. Okay. So another last indicator that you can use is to identify what's so called an indirect calls. So what is an indirect call? Before we understand what is an indirect call, we'll understand what is a direct call or jump. So here we can see a call to a subroutine. If we do double click, we'll see some sort of code here. Go back, and again, this is a direct call or direct jump. Direct call or jump is calling a function or the address of the function directly without the need of a register, for example, to hold the reference or the pointer to this location in memory. Here we can see, for example, a call or a jump to R11, which is one of the x64 registers. So whenever you see a call or jump to a register, it's called an indirect call or jump because it indirectly calls a function or a place in the code which the R11 references or points to. So this is the difference between direct and indirect calls or jumps. And whenever you see a lot of those indirect calls, it can give you another indicator that something going on here. So this is for the video. Hope you liked it, and see you in the next one. Hello everyone, welcome back. In this video, I want to talk to you about a small anecdote about detections and false positives. If you remember, in the previous videos, we took the calc.exe and basically explained the difference between the regular calc.exe and the packed calc.exe, and how to identify the difference between them. But I decided to do another video to show you how false positives can be made. So we have here the original calc.exe inside VirusTotal, and as you can see, nothing really suspicious or malicious. Now let's upload in another VirusTotal window the packed version of the calculator. And as you can see, there are 4 different vendors. Sometimes it can be more and less, but you see 4 vendors that are detected this packed calculator. Again, it's not malicious. You can see here regular calculator. Yeah. So why they actually detected it as malicious? There are a lot of reasons. In order to understand this, you need to actually go and read my book, Antivirus Bypass Techniques, and understand about the difference between static, dynamic, and heuristic engines, and what is the unpacking engine. It actually takes packed files or code and unpacks them. And there is a lot of logic goes behind them. Not making this video to mock those, those vendors, even though I'm a little bit, I'm always kind of surprised to see that they're detecting UPX or any type of packer as malicious, because again, in the original sense, packers are legitimate. You cannot really detect something, or you can detect a file as malicious based only on the fact that it's packed. You need to have more indicators to receive a better verdict, whether it's malicious, suspicious, or benign, which means clean. And as you can see, we received 4 false positives here. So the fact that you see 4 out of 71 doesn't really mean it's malicious. It can give you a sign that maybe it's a really cool and new malware that no one actually detects them, but in this case, so that it's not always the case. This is how a false positive actually looks like. Thank you very much, and see you in the next video. Hello everyone, and welcome back. In this video, we'll learn how to identify malicious functionality inside files. So as a first explanation, a lot of people can make wrong decisions regarding file, supposed malicious file or suspicious file, and say that yeah, we it has some malicious functionality and other stuff. But really important to understand that you need to have as many data as you can have to actually have a verdict whether a file is actually malicious or not. So it's that simple and straightforward. And I want to show you what I mean in that. I will use two tools here. A very great and famous tool called P Studio, and another, of course, IDA, as always. So let's on P Studio and drag the space one, float Amy inside. So P Studio is a really cool tool. It's not a regular PE parser, but it's actually a what it's all called a malware initial assessment. So it parses the PE, but actually analyzes and assesses whether it's malicious, suspicious, or even maybe even benign. So it gets you and helps you to to get a first glimpse to understand whether actually you know whether it's actually worth to invest the time into the analysis. And again, it's not perfect. Not there is nothing or any tool that is perfect, but this tool does an amazing job and actually is also maintained regularly. So you go into the indicators window, which gives you a general overview of the indicators that it gets. So first, the first indicator, yeah, for sure, it's that VirusTotal detects or the endpoint security engines behind VirusTotal detects it as a malicious. So yeah, it's the first indicator. It's a really strong indicator also. And you have another embedded file inside the resource section, as we already saw in the previous videos, and it actually even gives you the offset to it. So if you double click, you can go to the resource section here and basically see that the file ratio even is like the highest one. So like all of those sections are very small in the ratio and relatively to each other, but the resource section is most of the files. So something really goes on there. Not only that, but we see that both the text and our data sections are executable. They're signed as executable. Now, for the text section to be signed as executable, it's very logical and normal because you actually need this section or the code inside the section to be executed. So yeah, you need this permission, but for the R data to be an execution or to have this executable line, it's a bit of problematic because our data is remembers for read-only data, so it needs to have a read permission. Okay, so basically, this is for the sections. Now let's get back to the indicators and see if we have other indicators. So we have this basically another entry point, which leads us to another place here. So basically it finds that it has two entry points rather than one. In regular file, we will have one entry point, but in this case, you have two entry points. Okay, and you have two flagged or problematic like if you want to call it problematic Windows API functions. Now let's go to the imports here. Now let's check this flag tab. And yeah, you see some of those Windows API functions. So just for you to know, by themselves, Windows API functions are legit, but legitimate things can be used as malicious weapons. So it's like having a hammer. You can, do good with it and build with it, but you also can destroy and kill with it. So either it's positive or negative. Okay, so you have here those functions like create service, queue user APC, and yeah, it's like you can read about each one of those Windows API functions and understand what they does. But if you have a series of Windows API functions, like for example, we have this create tool help 32 snapshot and process 32 next and process 32 first and then the process 32 next, you can understand that those three functions are used to enumerate processes. Okay, and in the next videos, when we actually go and reverse engineer or analyze this malware, we'll see why those API functions are used and what type or what kind of process they're looking for. So it's kind of interesting, but you need to go inside the code and reverse engineer it in order to understand what it actually does and why it is using those functions. But there are more cases, like whenever you see a function that is imported as part of the IAT or the import address table, but it's not actually called or used in the code, and you cannot really consider it as being or as being malicious because it's not actually being used by the code or in the execution. And of course, those things need to be validated also. So in order to validate whether a function is used or not, it can be relatively simple and straightforward. You can go, of course, like always, I used IDA. You can open the file inside it. I do here load resources because we already saw that we have something strange and interesting in the resource section. So if we take this load resources, of course, it will also load the data inside the resource section of the P file. So in order to validate whether Windows API function is used in the code, you can go to the imports here, and let's say we want to validate if this set that's, for example, let's say for this create service function or Windows API function. So if we double click on it, we'll see that it's part of the imported functions. And now what we want to do is basically select one of those here and do X for cross-reference. And as you can see, I'm trying to do X on both this std call and the function, or this extern function, and there are no X references. So from what you can understand, yeah, they're imported, but they're not actually used in the code. So this is how you can understand that, yeah, the fact that create service is here, and in a lot of cases, like in the case of dark side ransomware, actually goes and create a service, use the create service Windows API function to do one of his dirty works. In this case, it doesn't really do it. Yeah, you have this flag, but it's not actually used by the code. Okay. Now let's take another example. Let's take the example of let's do a search process. For example, the process 32 first. Let's double click on it. If we go and select and do X, we see a call to this process under this subroutine. So yeah, in that way we can see that this Windows API function is used. But of course, if you want to actually validate it like in 100%, you can put a breakpoint in top of this function, or even in the start of the subroutine that actually uses this function, and then basically load it in the debugger. And yeah, the fact that it actually hit the breakpoint, we can see that is used in some sort of a context of the malicious purpose of this malware. So thank you very much, and hope you understood how to actually identify malicious functionality and whether they used or not in the code. See you in the next videos. Hello everyone and welcome back. In this video we'll learn how to read Windows API functions or other type of functions documentations. So you will encounter a lot of functions that you will read in the disassemble or the malware code. Some of them can be standard C type of functions, and can be also Windows API functions, native functions, and others. How do you really approach it? As I mentioned in the previous videos, one of the ways to learn and to approach reverse engineering is not to read each one of those assembly bytes. Of course, it'd be amazing if you can understand everything, but one of the approaches is basically to seek an understanding the context by the called functions, Windows API functions, and to understand what is actually happening. So the series of the create tool help 32 snapshot, process 32 first, force 32 next, Windows API functions can indicate that some type of process enumeration is going on in malware code here, trying to determine which processes are actually running on the system. So the thing that you see here, let's actually represent it also with sudo decompilation, so we can also see how it is actually look like from the C perspective code, like this, and synchronize IDA view. And now if I'm choosing create tool help 32 snapshot, I can see that, as you can see here, we have a variable tool help 32 snapshot, which is the variable name that IDA actually gave here, which the return value of the create tool help 32 snapshot, which takes 2 arguments, as you can see here. And the 2 arguments is actually the structure of this thread 32 pros ID, which is one of the parameters, and the flags. So basically, we're seeing that IDA determined what type of function and what type of parameter it takes. So from here, you can see it takes 2 parameters in the way of, and that in the assembly, you see that it actually goes opposite because it uses the push instruction. As we already understand about stack, stack is a LIFO, last in first out type of memory. So in assembly, we'll see everything in the reverse order. So the first parameter will be the 0, and then the second parameter, which in this case is 2. So, okay, now we have this function, and there are times that IDA actually cannot really understand what type of functions, or it really doesn't have the ability to determine what kind of function and what kind of parameters it takes. So it's really important to actually go and know how to and understand how to read documentations of those functions. So let's go to and search Google create tool help 32 snapshot MSDN. MSDN is the official Microsoft documentation website, and there are functions that are documented, and there are a lot of other undocumented functions, which sometimes you can find them in other websites, and sometimes you cannot, and you need to really go and reverse engineer function for yourself and understand its building blocks, structures, etc. So for this Windows API function, we actually have documentation. So you'll see here the name of the function and from where or from which header file it is important or included in the C code. So let's start from the bottom. We go here. It actually has what's so called this part of requirements. So the minimum and minimum supported client OS and server OS mostly are not so of a concern for us. Target platform, of course, most of the time we will see Windows, maybe sometimes something else or different types of stuff like WSL, Windows Subsystem for Linux, which actually allows Linux OSs to run directly on the Windows operating system in its own way, of course. We have the header file, which is tool help 32 header, the library kernel 32 lib, which is for static libraries and for dynamic libraries like this kernel 32 DLL. So whenever we actually include the tool help 32 or any type of other header file, we can actually use the specified function from this header file. But whenever we actually compile the file, the linker on execution, whenever we'll execute the executable itself, the linker will actually go and link the actual function implemented in the DLL file, not in the header file. So the function in the header file is used while you're writing your source code, but whenever the file is compiled and executed, it will be actually imported from the DLL module. Okay, so in this case, the create tool help 32 snapshot is from the kernel 32 DLL. So it's important to understand. And then we have the syntax. So it's actually we have the function here, the definitions, and the parameters it takes. So we see that it takes 2 parameters, flags and this third 32 process ID. So for each parameter, we have its explanation. So for the DW flags, we have the explanation about this one. So the portion of the system to be included in the snapshot. This parameter can be one or more of the following values. So you can specify the value. So if I go here to IDA, I can see that it actually is 0. So we can go find the reference of 0 for the process ID actually. So if we go here, the process identifier of the process to be included in the snapshot. So basically this parameter can be 0 to indicate the current process. So it actually goes and do process enumeration from its current process basically. You can do, and you can specify other parameters to do it in a different way, but basically this is the one of the requirements or one of the parameters that is actually passed to this function. And of course, if you want to understand more of the internals of it, you can research it for yourself. And for the second one, which is 2, so let's go and see what is 2 for the DW flags here. And if it's 2, you can see here it's actually of the type of snap process, includes all processes in the system in the snapshot to enumerate the processes basically. So of course this function actually required to also be used with 2 more Windows API functions, first 32 first, as you can see here. So here we have another definition. Of course we have 2 parameters, the handle and the process entry, and of course for each parameter we have an explanation. And another part of any documented function, if we go to the either to one of those functions or other Windows API functions, is the return value. The return value is very important because it will give us an indication whether the function was executed successfully or not. So if the function succeeds, in this case, again, each function has its own return values, and for some functions, return value of 0 can be success, for others it can be fail, so on. So if the function succeeds, it returns an open handle to the specified snapshot. So if it actually succeeds, we receive a handle value, which basically used by the other Windows API functions of process 32 first and for process 32 next. If the function fails, it returns invalid handle value. So this will give us the indication that the function did not succeed for some reason. And you have more remarks, some other comments that the developers or the one that is actually documented this function basically wrote here. So in that way, we can understand what are we tackling, what type of function we're using, and in what type of context it is used by the parameters and values. In that way, in this way, you can basically understand better and approach reverse engineering in an easier and way. So thank you very much, and thank you. Hello everyone and welcome back. At last, in this video we'll take everything that we learned in the static analysis part and we'll put everything together in this one sample of float-amy. So let's begin. So here we have this space1.ex, which I changed it from exe to ex so I will not accidentally execute it. So basically let's start by identifying the file type or the format of this file. So we'll see that with the MZ header, this program cannot be run in DOS mode. We have the PE header and all of the other standard stuff that we expect to see in the PE format. So let's widen up this view and let's see if we have interesting strings to find here. See some Windows API functions like get module handle, size of resource, get proc address, create tool help 32 snapshot, which can be used for process enumeration. Let's continue and see if we have more interesting stuff. We can see here some maybe encrypted blob. Seems like values with some high entropy stuff. So if we continue, we can notice here some interesting pattern of this 6F. As you can see here, some interesting pattern. And you see a very high entropy blob here. As you can see, there are a lot of random characters without spaces between them. So it can tell us that some type of obfuscation or encryption is going on here. Okay, so let's continue. And we got to the end of the file where the manifest is, and you see that the requested execution level is as invoker, so it will not ask for administrative privileges, or it will not pop up the UAC window. But of course it will be executed as the user context. If you're a regular user, it will be executed as a regular user. If you're administrative or local administrative user, it will run as the administrative privileges. Okay, so let's see what we have here, and let's in this step extract the strings from the sample. So let's spawn cmd and do strings on space 1 and output to auto.txt. And let's see if we have something interesting here. So first of all, we have we can see that we have process names with .exe. So maybe it's somehow connected to the create tool help 32 snapshot Windows API function, which can be used for the process enumeration. Let's see also if we have the create to help 32 snapshot. And let's see if we have process 32 first and next. Yeah, so the three Windows API functions, create tool help 32 snapshot, process 32 first and next, are basically used in conjunction in order to find or enumerate process in your system. So it can be kind of logic what we see here, and basically, yeah. So we need to validate it, of course, in the disassembly, in the code itself, and we'll do it later. So let's see what more interesting we have here. We have OpenSC Manager, Reg OpenKey, other Windows API functions that we see in a moment in a different program, PE parser. Let's see what we more have here. Okay, so some mumbo jumbo stuff, not something interesting. Okay. Let's see if we have more interesting information that we can extract from the strings. And for now, doesn't seem like this. From my experience, when you see a lot of strange strings, especially if you saw this type of encrypted blob like before with this pattern, and you can notice that maybe it's a first stager or a loader or an injector or some type of a first stager, basically. So if you have a malware attack, basically you have most of the malwares are basically broken down into steps or into stages. So mostly you have the first stage, which is attached to it's a file that is attached to the email, for example. It can be a Word file, PDF, stuff like this. So they can be a downloaders, they can download from remote servers, they can be droppers, they can basically extract something from themselves. Okay, in this case we have the float Amy. We'll see that it's actually extracting content, or this specific content, from the resource section. Okay, and let's continue. So basically we saw that we have the Windows API functions as clear text, so we can understand that the attacker didn't use any type of encryption here, like symmetric encryption, like AES, for example, to hide the presence of those Windows API functions in the strings. And we will also see that the Windows API functions are basically shown as plain and simple in the IAT import address table. So we can also conclude that API hashing or dynamic API resolve techniques are also are not employed in this specific sample. So let's now go to the PE parser. Let's use PBER in this case. Amazing tool written by Asher Z, very well-known security researcher, malware analyst in the cybersecurity community. So let's put the sample inside. And of course, if we go to the reach header, we can see what type of linker compiler it's actually used. So I get us an indication that it was used Visual Studio 2008, maybe different type, and doesn't really matter for us right now. If we go to the optional header, we can see stuff like the base address from where the malware actually start to execute. So it will be the base address plus the entry point. And this is the address from where the process, when it will be loaded into the runtime memory, will start to execute it. And other stuff that we can see here that we already talked about in previous videos. If we go to the sections, we can see that we have the text section, which holds, of course, the opcodes or the assembly instructions that will be executed. We have two R data sections, which is interesting to see for what they actually use. So we have one R data, which is read and execute, which is kind of anomalous because R data sections, like you see here, most of the times, need to be read only. This is more logical for the read only data to be read only, not Rx. So it's something interesting to check. We have the data section, which is read write, and we have the resource section. As you can see here, the resource section is only in read mode, but the size of the resource section is kind of it's relatively bigger than the size of the other sections. So we can see that the row size is bigger than others, and the virtual size also bigger than others. So the row size is basically for the size of the content inside this section, while it's on the file system, and the virtual size is the expected size to be when the process actually loaded, or the content of the process actually loaded into runtime memory and executed. So this is in simpler terms, the row size is what the size in the file system, and the virtual size the size in the runtime memory. Okay, so basically we can go now to the imports to see the imported functions, which imported functions and from which DLLs. So if we go to the current 32 DLL, we can see that we have virtual alloc, get proc address, virtual alloc. Most of the time, of course, it will be used for allocating memory. And we have other stuff like load library. Load library and get proc address are used in conjunction in order to load Windows API functions dynamically in runtime memory. So both they can use to load Windows API functions, which we will not see for now in the IAT, but you will see it in runtime memory while we debug it. So we see the parse to next first, and the create tool help to snapshot, the same that we saw in the strings. So we can conclude, but of course, it need to be validated in the code. The fact that you see a Windows API function that is imported as part of the IAT or the import address table, it doesn't really mean, or it's not a fact that it is used, basically, because a lot of times you will see Windows API functions which are part of the IAT, but they're not actually used in the code. So we need to validate it. Again, same thing that I already explained in the previous videos. Let's see what more interesting. So we have the find resource, load resource, lock resource, and size of resource. So basically, those are four Windows API functions which are used to basically load or extract content from, or specifically from, the resource section. So yeah, we see that we have a resource section. We see that we have find resource, load resource, lock resource, and also size of resource. So those four Windows API functions are used in conjunction in order to extract or to load content from the resource section. And it's something that is very interesting for me to note here. A lot of malware use it, so it's very common and standard, but it doesn't really mean that they need, or it's mandatory for them to use all of those Windows API functions. They can, for example, in the dark side ransomware, they are not using those Windows API functions. They're loading content from the resource section by using a simple move assembly instruction, and then they do their decryption and stuff of the code in runtime memory. but they're not using those Windows API functions. So again, also most of the times when I see for those Windows API functions, they're actually used to extract content from the resource section, but again, they need to be validated in the code, in the disassembly or the pseudo decompilation. So yeah, let's continue. If we go to user 32 DLL or even to GDI 32 DLL, a lot of people will say, or a lot of novice malware analysts will say, yeah, it's most of the time, those DLLs are not functions there are not, dangerous or can be abused for malicious purposes. And I strongly disagree with them, because if you go, for example, to one of my blogs, Dissecting RDMAX Keylogger, this is the name of the blog, you will see there that the set Windows hook X Windows API function, which is used with the ID hook 2 parameter, is actually used as a keylogger mechanism. So it's logging the keystrokes of your keyboard. And in GDI 32, you can see there that it uses like Windows API functions like create DC and set the DI bits and more Windows API functions in order to create basically take screenshots of your screens. And yeah, so it is it can be used or abused for malicious purposes. So be open-minded, it's very important. A lot of people also say, okay, if you see something like WinSpool or DRV or something with driver, it means that maybe something is exploited here regarding the spool SV or the print spooler service. Yeah, a lot of times malware do it, but not always. I didn't really see that it happens in this sample. Maybe it is. I didn't really check it. So if you want, you can do it. And we have the Advapi32 DLL, which in this case we have the reg open key, OpenSC manager, create service. So those are the functions that are important as part of the Advapi32 DLL. And yeah, so the final thing that I want to actually validate here is whether the malware is packed or obfuscated or whatever. We already saw that some strange patterns are going on here. So let's validate it with some entropy calculation. So let's go and use detect it easy. And we see, yeah, so it's extracted that the compiler that uses Visual C++ and Visual Studio 2008. Again, it's extracted from the reach header that we can see here. So if we go to the reach header, of course, if an attacker will omit or remove the reach header, programs like Detected Easy or even PEBear will not have the ability to extract this information, and a lot of malware do it. So let's go. Of course, you can use strings here. What I like about the strings here, you can basically show more content, Unicode, ANSI, different types of formats. It can really help in a lot of times. You can see programs that they're extracting ANSI, but they're not extracting Unicode, and a lot of strings are basically left out. So take it into notice. And one of my tips is actually, when you use one tool, use another one or two tools to validate the integrity or the validity of the first tool, and then you can actually this is one of the most important things in research. Whenever you're researching something, validate stuff using several resources, several sources, tools, etc. So if I go to the entropy, so we have the general calculation of the entropy, which is 91%. It's basically, it goes from 1 to 8, and if it's higher than 7, it's considered to be packed. So in the sections, if you go here, text are data sections are not packed, but we have the resource section, which is considered to be packed. Again, entropy, it's not something that you can take for 100%. It's only another indicator. But the fact that we see that the resource section size is bigger than others, and we see this strange blob, and we see the 4 Windows API functions of find resource, lock resource, load resource inside of resource, and we see that the entropy value is high, so we can conclude that yes, something is really going on here. So it's not that the file is packed with, you know, standard packers like UPX, ASPack, ASProtect, and stuff like this, but there is something going on. So it's not that the code is packed, some kind of data here is packed. So now that we see that something is going on in the resource section, the next step for me, again, I use my own methodologies that I developed with my ears. You know, for now you see, I think it's considered to be very standard, but eventually it's, you know, your methodology. There are people that like to use Python scripts to do everything here. You know, use your own tools, use your own methodologies, whatever suits you. So for me now, I will use Resource Hacker. I remember one of my students researched the WannaCry sample. One of the, you know, he found some sample in VirusTotal or whatever, and he saw something strange in the resource section, which is very common for WannaCry. For those of you who already researched it, you can also go and refer to my video on my YouTube channel. But Resource Hacker didn't really have the ability to read the file, and one of the reasons was that it's a very neat and simple and basic trick. One of the reasons is that the malware author actually added like more bits here. So like he added bits to the, so it like the MZ was here and the zeros was here. So the format of the P format actually says that you need to have the MZ header in the offset zeros. And what the attacker did is actually did something like this, and MZ. And if you try to load it into Resource Hacker, it will basically break. So one of the things is to basically to fix it, to remove the zeros, and left it. Do not ask it, please. Thank you. And left it like this. And then after you fix it, you can put it into resource into the tool like resource parsers like Resource Hacker. So yeah, it really it's really important to understand this stuff, because if you don't, you will go you will lose yourself, and it takes time. It takes practice. So take your time and enjoy, of course. Okay, so now let's load the file inside, and let's see if we have something interesting. So we have some GUI stuff going on here. For me, most of the time, it like indicates that you know, in this case, we're researching the flawed AMI sample, which is based on the dumped source code of the legitimate software called AMI Admin, which is a remote administration tool, or RAT in short. And the fact that I see here GUI tells me that the malware authors or the attackers maybe basically took the same code and they didn't really go extra mile into removing the GUI stuff that maybe AMI Admin had. And maybe they left the GUI so novice malware researchers will think that, okay, if it has GUI, it's not malicious, because most of malware don't have anything GUI. And it's, of course, false, because you can do whatever you want, especially if you're developing malware. You know what I'm talking about. So if you take an existing code and base your own code on top of it, you can left stuff there because you have your own reasons and whatever. So it's there. It doesn't really mean it's malicious or not. It's just there. Okay. So for me, it's not something really interesting for now. Let's continue. Let's see if we have something interesting. The strings table. Yeah, I see some pattern. You see some string comma, string, comma, string. I don't really know. It's like for the language lang. Okay, so it's like 1, 2, 3, 4, 5. 1, 2, no, I don't really know. So something that you can see in others, other samples. I don't really care for this one. Again, maybe it has some meaning for me. It's not. I'm really honest here. I'm really open. As you can see, I'm doing here the analysis very openly. I'm not showing you that here I did like this and that. You see how I do it, very raw and very real. Okay, it's something which is very important for me. Not interesting for me right now. And let's go to the RC data. We see something strange in the RC data. Most of the times whenever a malware dropper like WannaCry, for example, or Flodamy in this case, employ some type of an executable or a DLL or something that it drops out from himself, or out from itself, it will be called RC data. Okay, most of the times it doesn't really mean that the next stage will be from here, but because if you go to HTML here, you can actually go and validate or cross-reference what we saw in the hex editor. So we see something strange is going on here. You don't really see a P format or MZ or stuff like this, like you see in WannaCry. In WannaCry, you immediately see something with MZ or PK, and inside the PK, which is a zip or a RAR, archived file, and from this archived file, which is extracted from the resource section, another P and other files are extracted. Here you immediately see something strange without too much information, but you see something weird, like it seems like encrypted, obfuscated, or whatever. Okay, with time and experience, you will recognize those stuff much more easily. Okay, so let's take, for example, like I don't know, this blob here, and search it. Find hex values and do forward. Okay, so yeah, if we go even and try to see, yeah, so let's widen it up here like this, and you see it's in the same place that, like, it repeats itself, so we can conclude that some kind of pattern is going on here. Okay, and it's in the same place that you see the same pattern with the 6F that my eye is noticing. Okay, so some kind of pattern is going on here. Now again, I could just go into the code, reverse engineer it, blah blah blah, see the disassembly, show you stuff, but it very important for me to give you an overview and to show you as much data as possible, even with this very basic, like most of the time in our industry, whenever you use tools like hex editor, detected this, it's considered to be basic, but whenever you go and use IDA and stuff like this, it's considered to be advanced. But again, it's very relative. It's very I'm really into saying what is basic, what is advanced. I see research as something very wide and very deep, and you need to go with the flow and enjoy from it, basically. So let's continue. So yeah, we find that something is really going on in the resource section, and again, everything is okay. So let's conclude this video, and we will continue in the next video. Thank you very much. Hello everyone, welcome back. Real Kusav is here. We'll continue now with the second part of Flodamy malware research. So we got everything we learned from the static analysis part. We did the first video about the Flodamy malware. Now we're going to do the second one. So let's open up IDA freeware. and open up space 1.exe. And let's stick on the load resources, because as we already seen, there are some stuff going on in the resource section, and those and we saw also for Windows API functions like size of resource, lock resource, load resource, and find resource, which are the 4 Windows API functions, which are the standard or the most known way to actually go and extract stuff on the resource section of a PE file. So let's open up in IDA. So here we're going to do static reverse engineering. We're not going to put any breakpoints or debug it, or still not. We'll do it after the dynamic analysis part. So how do we actually start and approach reverse engineering here in general? So first of all, we can go and seek for some interesting strings. So we can do Shift F12 and we can go and search for interesting strings. And as we can see, we have a lot of Windows API functions also presented in the strings section. So we can go and search for interesting strings, and from those we can try and evaluate what is going on over here. So let's close the strings window. You can also approach it by going to the imports or the IET import address table and see what kind of Windows API functions are imported as part of this file. So if we'll go to the create tool help 32 snapshot, a Windows API function, for example, it will jump us to the iData section. Okay, the iData section is a section that is basically used for the import address table. Now, it's something very important to note that the iData section is not always used in a P file, and let me show you what I mean by that. So if I go and open up the space 1.exe in PEBARE, and we'll go to the imports or the section headers, we will not see any iData section here. So you can ask the following question. So why in IDA I see the iData section, while in the exe file itself or the PE file, I don't see the iData section. I see text section, RData, data, and resource. So basically, as we already know, the import address table can be part of the RData section or by a different section name like iData, but in this case, we only have 2 RData sections. And the reason why you see iData section in IDA is because IDA has its own way and its own reasons to add another section into the IDB file. The IDB file is the database file which holds all of the information of the P file. So whenever I go and do file and save, or Control W to save stuff, or whenever I close this IDA window, I can pack the database and store it as an IDB file. So for the IDA purposes, it uses the iData section to identify the IAT. But in the P file, while actually in the P file you don't have the iData section, IDA adds its own section. So it's another thing that I think it's very important to mention and understand about reverse engineering tools like IDA. So we got to the imports or the IAT, and then we double clicked on the create tool help 32 snapshot Windows API function. And here we can just go and select one of those API functions and do X to cross-reference. And actually, whenever you do X for cross-referencing, you ask IDA, show me where this function, or in this case, the Windows API function, is used in the code. In what context. So we can see it's on the subroutine sub 402640. As a reminder, sub is a subroutine, is another name for function. So IDA identifies 2 types of functions. It can be a Windows API function, and it can be a subroutine. A subroutine is basically a function or a custom function that the developer has actually wrote for himself, and basically IDA identifies it as a function code block. And the 402640, you can see it's the starting address of this function. So if we double click on it, we do space to change the view, we can see it's under the RData section, and the starting address is 40264E. Okay, so this is the create tool help 32 snapshot Windows API function, and there are also the two other Windows API functions of process32 first and process32 next, which will use as a loop mechanism to go through the snapshot of the process list on the Windows machine in this case. So all of this code and Windows API functions that used here is all of those are under this specific function, sub 402640. This is the name of the subroutine. So if we do X for cross-reference, we can go and see who actually called this function, because there's always a function that calls to a called function. So there is, like for example, we do X, we can see that the start subroutine or the start routine actually called the sub 402640 subroutine. So we can see that it's called several times in the code, more than once. So we can do double click on it and we see, yeah, we got back into the starting address. So what we can see here is basically we have the call for this function several times in all of those code blocks until it gets to this part. Like it can go both ways. It can go to exit process and it can go and calling this function here. So basically, what we can see here are some interesting strings. So for example, if we go and search for this ekrn.exe, for example, in Google, we can read about this process and we can see it's part of the ESET Smart Security. So it stands for EKRN, ESET Kernel Service. So what I can assess from this is basically the malware tries to enumerate whether there are some antivirus or EDRs or any other type of endpoint protection solution that is installed on the system. And the decision it will make basically that if one of those processes are presented in the machine, it will go and exit basically. So the malware will not run and it will not execute. So why? Let's try to think why they will do it. So first of all, they want to be executed on systems that don't have this antivirus or EDRs, because maybe those antiviruses are detecting them, and the attackers didn't find any way to bypass those solutions. And maybe they want to actually they don't want the antivirus or EDR vendors to have this sample and basically sign it and detect it. So they try their best to do everything basically to avoid and be under the radar. So they're targeting machines that don't have any of those specific process names. So how they actually know that those processes are presented in the machine? So first of all, they use specific Windows API functions to handle this thing. So first of all, we know that before calling a function, you need to basically pass some arguments or parameters. So here, before we have the call to this function, we have push to this string. Now, basically, if we go and double click on the subroutine on the call, you can see that the create tool help 32 snapshot is used here, process 32 first, and then process 32 next. So basically what we can assess from it, or if we read about those Windows API functions, we can assess that basically there is a process enumeration going on here. So if we go and read it about it on MSDN, so we can understand that it takes a snapshot of the specified process as well as the heaps, modules, threads, and etc. So it takes all the process information on the system, and then what you can do, you can use the other two Windows API functions, basically with the process32 first and process32 next, and basically do a loop and go over all of those process. And if one of those processes are presented, it will do whatever it does in the code. So basically we can understand that this subroutine is used many times in order to enumerate processes. So let's change the name of it. So we press N on the keyboard, or we can just do right click and rename, and let's change it to process enum, or enumeration in short, and I'll do here. Here it will be used as a flag for me for renamed subroutines. Okay, so now if I go to the functions window and do Control F, and I will search for the here flag, I will see all of the renamed subroutines that I already renamed them. Okay, so let's do X and go back to the start window, and basically we understand that if one of those processes are presented, it will go and do exit. Okay, so how it actually checks this: after we have a call to the function or to the subroutine, basically it goes and do a test EAX. It basically checks the value. Okay, and if the value is basically not zero, so it will do basically it will jump to this location. If it's not zero, it will jump here, and if it's zero, it will go here basically. Okay, so this is the check, or the if statement, so to speak, to check whether this process, for example, or all of the other processes are presented in the system. Okay, so if we'll try and do F5 and put it here like this and do synchronize with IDA view, you can see here that for each, so it's like a big if statement, and if one of those processes or one of the return values of this function, which uses the three Windows API functions that I mentioned earlier, match one of those strings, it will do exit process. Otherwise, it will go to this block here. Okay, so this is basically what it does regarding the process enumeration part. And then it will go and do other stuff, like basically execute other Windows API functions, which most of them are garbage. As you can see, like garbage parameters are passed here to the load library function, for example, so you don't really have something to do with it. So you can think maybe it decrypts a string beforehand and then loads a specific library, but if you put a breakpoint, you will see it actually don't do it, because in order for the string to be decompressed or deobfuscated or decrypted, it will need another function before it to basically decrypt it, and then pass an actual library name to the load library function. So you don't really have any reason to go into it right now. And then it will go and basically call for other functions and do whatever it does. So if we go inside this function now, we can see something really interesting is going on here. So it defines many variables here, and then you can see some values are moved to some registers, and from what it seems, it tries to import some functions basically from the current 32 DLL maybe, and is back. Let's see, try to make sense out of it. And basically it will do load library and get proc address. So it's kind of a basic dynamic API resolve. So it will take basically the imported functions that it want to import from the current 32 DLL, and basically load them with load library and get procedure address. So the load library would load the kernel 32 DLL, and the get procedure address or get proc address will load those functions to the import address table of the process. Okay, so it will do it several times. Again, we can dynamically analyze it later, but for now we're doing a brief reverse engineering, not something deep here. And eventually it will call a function or some location in the memory indirectly. So if you remember, I explained about indirect calls. So in this case, EBEX will hold some kind of a pointer address to some kind of a function or call block, and basically call it. and to do some kind of a loop here also, and several checks, and it will try to get module to execute get module handle to get a handle to the user 32 DLL, I suppose, and maybe try to import other functions. So let's call it import functions here for now. Now it will go, now it will do some tests. So it will do test jump 0. So if the value here in the of the execution, if the value of AL of the execution of this function will be 0, it will jump here. Otherwise, it will continue. It will continue here to this call block. So if it continues to this call block, it will do call here, and then it will basically use all of those Windows API functions, find resource, load resource, lock resource, and size of resource, in order to load this strange data or strange encrypted blob that we already seen in the previous video to the process memory. And from there it will go and allocate memory inside the process using the virtual alloc Windows API function, and then it will do RTL move memory. So basically it will load the encrypted blob, it will allocate memory, and then it will move the loaded encrypted blob from the resource section to the newly allocated memory. So, and again, everything here is understood only by understanding and getting experience with those Windows API functions without getting deeply into each one of those instructions. So basically, you can see it's pushing some parameters, calling a function. Then again, pushing some parameters, calling a function. Again, pushing some parameters, calling a function. So by the time you will, the more you analyze malware and reverse engineer them, you will recognize patterns more fastly and more easily. So you're getting the hang of it by experience. So you need to get as much as experience as you can, and a lot of it. So again, this is the patterns that I see here, and by understanding this pattern, I can understand that data is extracted from the resource section, memories, new memory is allocated, and then moved. This extracted content is moved from somewhere to the new allocated memory. Okay, this is in general. I can check how many times this function is called. I see it's called only once, so it's a very unique and specific subroutine that is written by the attacker to do one specific job. So extraction of RSRC resource here. You can rename it even with better names. Again, you can work whatever you want or however you want. And then it goes and compares the ESI data, which needs to be 0 because XOR ESI, which basically takes the data in the register and zeroize it, because if you take the same value and XOR it with, like you take two values and XOR it together, and in this the same, it will zeroize the value. Okay, if you want to understand more about what is XOR, OR, and all those bitwise operations, of course you can go and read about it. It's not something very hard to understand, kind of simple and straightforward. And then it compares the value which is 0 to this D word. Okay, and while in runtime memory execution, maybe it will not be 0. Okay, so it's like a kind of, maybe it's the actual extracted data, which is extracted from the resource section or whatever. Again, it needs to be validated on runtime execution, because not everything can be understood from static analysis. You need to also put breakpoints, debug it, and see all of those stuff. And eventually we'll see something very interesting. You can see some kind of strange and weird operations like imul for multiplications and shift or shift right, and like here, or and then you see this XOR operation. And in comparison to this XOR, which it takes like the source and destination operands are the same register, which basically gives the value of 0. Here you can see that it XORs something in AL with this pointer address. So this is a classic pattern of an encryption or decryption. And encryption and decryption in this case, it's the same because it's symmetric. XOR operation is symmetrical. So if you use XOR-based encryption, the same key for encryption will be the same key for decryption. This is why it's called symmetric encryption. So by recognizing this pattern, by using data from one register and XOR it with data of another register, for example, you can recognize a potential decryption, deobfuscation, decompression, whatever mechanism. Okay, so here we have a loop, and basically after this loop is finished, we will see that we have the decrypted blob that was extracted previously from the resource section. And eventually it will go load this decrypted data. It will allocate some memory, move this new decrypted blob from its source, this location to its destination location by using the call RTL move memory to the newly allocated memory here, which was allocated by using the virtual alloc Windows API function. And yeah, eventually it will go and call the new code in the newly allocated memory and move to do its malicious bidding. Here you can see a call to an indirect call to a pointer location, which the EAX register will potentially point to. So if I remember right, this call EAX will be the next stage, or even maybe other indirect call. Let me see if there is another indirect call here. There is a call EDI, maybe it will be here, but again, I don't really remember here. But after the data will be decrypted and the new allocated memory will be allocated and the decrypted memory will be moved to this allocated memory, then it will go and call this new decrypted function, and everything is done in memory without touching the file system. So basically this is the end of this video. We can rename it call after decryption, after blob decryption here, or whatever. So yeah, you can also see here there is a move for the 5A, which is MZ in, MZ, which is the magic number for PE. So it kind of makes sense because it will check where the starting offset of the decrypted blob is for the 5A and validate in this way. It will validate that the decrypted blob is actually decrypted. Okay, because if not, it will not have the ability to call this newly decrypted malicious code. Okay, so yeah, maybe a lot of things here from the static point of view will not be understandable for you, but you will see that in the end of the dynamic analysis part, we will get back to this same sample, and we will do everything by debugging this process, putting some breakpoints, debugging it on runtime execution, and then a lot of what I explained here will make sense. So thank you very much, everyone. See you in the next videos. Hello, everyone. Welcome back. In this very short video, I'll show you how to save all of the things that we did in our reverse engineering in IDA. So as you already seen, we actually renamed some function names and did a lot of other stuff. So if we do Control F and we'll search for the here flag, which we used whenever we renamed those custom written subroutines that were written by the attacker, we basically have here 4 subroutines that we renamed, and we want to save everything that we did here. So one of the things that you do before you exit IDA, you do Control W. Control W actually, what it does, it basically saves all of the data into the IDB file or to the IDA database file. Then what you can do is basically you can do exit here, and you have several options. You can basically you can do don't pack database. You can do pack database with the store or deflate. What I actually do is pack database for the default. So if you do exit, this is the default option. And if you do don't save database, it will basically wipe everything you did. So just make sure you don't take it whenever you want to save this IDB. So pack database, and you do OK. And here you can see basically you have this I64 file, which is the IDB file, which you can use afterwards. So if you double click on it, you are back from where you stopped. And if you do Control F here, you'll see the same functions. Thank you very much. See you in the next videos. Hello everyone and welcome back. In this part of the course, we'll go through dynamic analysis, which is the next part and very important aspect of malware analysis. As we already saw in previous videos, there are a tipping point where we cannot actually see and understand how malware works only by inspecting it statically. So we need to take it a step further and go into dynamic analysis and actually execute the malware and inspect its behavior. So first of all, let's understand the goals of dynamic analysis. So the first goal, as we already understood from the static analysis, but also in the dynamic analysis, classification. We want to understand and determine the type of malware, not only the type and the goal of the malware, but its technical capabilities. So if we take the WannaCry ransomware, that by its own nature is a ransomware which encrypts files and then demands a ransom or a payment in Bitcoin, for example, in order to provide an decryption key, so you can basically continue your production work in your company. So yeah, it's a ransomware, but it has other technical capabilities. First of all, it's a Trojan because it masqueraded as a disk partition utility. And then it's also a worm because this ransomware had the capability to basically laterally move between different machines. So it can infect other machines by exploiting the eternal blue vulnerability, or MS1710, and basically in that way laterally move and encrypt other machines, not only the first machine that it was landed on, which is called the patient 0 machine. Okay, so it lands on the patient 0 machine, it masqueraded as a Trojan, as a disk partition utility, then it is executed, basically encrypting the files locally, and then it searches for other computers to exploit the eternal blue vulnerability in order to basically laterally move into next computers and do the same thing, just basically encrypting the files and demanding the ransom. And all of this can be understood statically but also dynamically by executing the malware and inspecting its behavior, where it's on automated sandbox systems like we will explore later on the course, or by executing it inside your own virtual machine. Of course, you can execute it on a physical machine, but it's not so popular to do, and it's not so recommended because you can basically break your own computer. Of course, if you have other solutions, like you can wipe your SSD drive and then reinstall the operating system and then again execute it on a physical machine, you can do it also. there are a lot of reasons why to execute a malware on a physical machine, not on a virtual machine, is to inspect its behavior without all of uh, um, um, the cons or the minuses of the virtual machine, because basically malware can detect very easily that it's presented or executed on a virtual machine by inspecting the how much RAM do you have, because mostly if you, for example, configure 4 gigs of RAM for your virtual machine, the malware can conclude that it's inside a virtual machine, or by inspecting registry keys of VMware or VirtualBox, or even the VM tools, or other processes that are like the VM tray .exe that is executed. And again, there is a lot of ways for malware to determine whether they're inside a sandbox or a virtual machine, or whether they're inside an actual victim machine. So this is why a lot of times it's even better to run it at a physical machine. But again, it depends on the goals you have in mind. The second thing that you need to understand about dynamic analysis is fingerprinting. You want to detect and sign the malware in memory runtime level. If in static analysis you detect and even prevent the malware based on strings and the functions that are imported in the IAT, in the import address table, or by other like, for example, shellcode or opcodes in the assembly level, whenever you actually go in dynamic analysis, you can sign it in memory runtime level, so you can inspect what kind of functions and parameters those functions are using, how many threads it has. You can do a stack trace to understand the function execution kill chain. For example, if you have the create process Windows API function, and then you have open process, and then you have virtual alloc, and for example, write process memory, all of those Windows API functions can be concluded as part of a malware or process injection or code injection technique. So you can inspect it dynamically on the system. So it's another way of fingerprinting. Of course, you can also search for strings and Windows API functions, for example, that are loaded on memory runtime level, because each process has its memory pages, or that basically loaded with a bunch of data that you can search and detect and prevent based on those data. Another great aspect about dynamic analysis is basically to detect C2 communication. So you want to basically determine what or to where the malware tries to connect with. It tries to connect to some C2 infrastructure, to some servers, proxies, DNS servers, to some websites, domains, IP addresses. You want to actually understand it. You want to add it as part of your IOC, or indicators of compromise, and you want to maybe block it on your organizational network firewall, for example, to block all those network communications. So, for example, if you have a malware that communicates to C2 server, to a malicious C2 server, in order to download another malware, or to maybe exfiltrate sensitive data, you can actually block it on the firewall level, or even you can create a EDR rule, for example, to block this communication based on domain name or IP address, or some other type of detection or prevention logic. Then you want to understand the TTPs, or the tactics, techniques, and procedures. Not always by analyzing the malware statically you can understand all of the used TTPs, but whenever you actually execute the malware, you can understand what kind of utilities it uses, what kind of built-in operating system vulnerabilities, or even executables. Or, for example, a malware can use lol beans to bypass app locker or GPO rules, and do a lot of stuff. It can use even built-in capabilities like CMD and PowerShell, and even executing WMI queries to determine what type of antivirus or EDR you have, or even use the NL test exe or CSVD exe, which you can import from the ARSA tools, in order to determine what is the domain name, and what trusts do you have, and what is the forced functional level, whether it's a server 2006, 2016, or 2008. And in that way, malware and attackers can basically determine what kind of organization they're attacking, basically. What can they leverage, what they can steal, what can they can encrypt, and so on. So you want to understand the TTPs. You want to understand their tactics, their techniques, and their procedures, how they actually go. For example, if you take Emotet starts with a classical phishing email, which is attached with some VBA attached macro of a Word file, or if you take other threat actors, they can even use Excel, XLM, or Excel 4.0 macros to execute malicious code, which can download another exe or DLL file, load it into memory, and do its malicious bidding. So all of those are procedures or techniques or tactics that basically malware and attackers are using, and you want to understand all of those things in order to know where and when to stop the spreading of the attack. And the earlier you stopping, detecting, and preventing the malware in the earlier stages of the attack kill chain, the better. Okay, so you have the initial access, then you have the discovery phase, and then you have the lateral movement and the persistence, and then you maybe have another discovery stuff going on. For example, enumeration of endpoint security processes that are running, and the domain that it's part that the machine that the victim machine is part of, and all of those stuff are based on those stuff you can build an understanding of this malware or of the attackers. And of course, dynamic analysis can also be used to test organizational defense systems. So we can basically execute those malware dynamically, double click on them or whatever, and in that way assess and evaluate how much your organization defense system, whether it's antivirus, EDRs, DLP, firewall, IDS, IPS, etc., are actually aware of the malware. Okay, so whether it takes telemetry data of the, for example, a malware adds a registry key by using a WMI command. A lot of EDRs don't know how to, or they actually don't gain any telemetry data regarding WMI. So if a malware creates a persistence registry key on, for example, the run key or the IFEO key based on WMI technique, a lot of EDRs don't know how to actually detect it, because they don't gain any telemetry data and they cannot really create a prevention mechanism or a preventative measure or technique to actually prevent this specific technique or this specific behavior. So the first thing that an EDR or an antivirus need to do is to take a telemetry data or to inspect something, and based on this inspected data, create a preventative measure or a detection or a prevention. And basically, so you have the first thing goes is for the collection of the data, the telemetry data, then you have the detection, and after you detect the malware or the attacker, you basically go and prevent it. Now, there's a lot of EDRs and antivirus that are detecting the attack, but they don't have the ability to prevent it for their own reasons, for their own technical and business reasons. We'll not delve into it. We already gone through attack MITRE in one of the first videos of the course, and we understood how the attack kill chain is going on, and what kind of techniques you can learn from their tactics and procedures, and even some defense guidelines that you can learn from there. I encourage you to visit this website. So why attack MITRE? First of all, to understand adversaries' common offensive techniques, to understand compromised vectors, general infection flow, and understand how to mitigate most of the attacks and their techniques, and use their knowledge to write a better IR reports, followed by recommendations. And again, it's very important. I already got through those points in my previous videos, but again, it's very, very important to know and understand how not only to analyze the malware, but how to prevent them in the earlier stages of the infection or the attack kill chain, and then to provide better recommendations. It's very, very important. Let's talk a little bit about CPU protection rings, about process threads. Again, I will do it very, very generic, very basic. I will not go into too much details. If you want to go into more details, you can go to Pavel Yusefovich Windows internals courses, and you will gain all of the deep knowledge inside all of those. So basically, our CPUs today and the operating systems that are operated on top of those CPUs are based on what's called a CPU protection ring. So you have ring 0, which basically is the kernel level, which is the most privileged layer or level on the operating system. All of the kernel drivers are executed there. Now you see there is ring 1 and 2 for kernel drivers, but for now you see that most or even all of the operating systems are running on ring 0 kernel mode. And then you have the ring 3, which is our applications or the user mode. This is the mouse cursor that you're seeing, or the screen that you're using, and the GUI and all of the applications that you're using on a daily basis, the browser, the Outlook, or the email application, whatever. All of those are running on ring 3. Of course, every ring 3 application has its counterpart or some aspects in the kernel level. So it's like a human being that has a conscious and unconscious of the mind. So basically you have the conscious part, which is the process, for example, or some kind of application that is running, and you have the unconscious part, which is residing on the kernel level, which is kind of like the unconscious part of the operating system. So again, this is the in general. So of course, the lower the ring is, the most privileged it is, and as you already, I believe, as you already know, the kernel is the most privileged one. In ring 3, you have several privileges. You can have a local regular user, you can have a guest user, a local administrator, you can have a domain administrator, enterprise administrator. You can manage permissions for users like read, write, execute, list folder content, full privileges, and stuff like this in what's called NTFS permissions. Again, we're as I believe you're the one that watched this video, I believe that you already know what is NTFS permissions and how you can share folders and printers and how you can manage the permissions and all of this stuff. But in general, each process in the operating system has its own security token, and by its security token, it has its privilege on what you can do. And you have permissions in the folders level. So for example, if you have a shared folder in your organization which holds some interesting files, Excel files, Word files, and stuff like this, you can manage, you can allow or block users from reading or even writing to this folder, for example. So all this is on ring 3. Of course, anything is interconnected. Everything in the operating system is somehow interconnected. So things that you do in ring 3 is somehow interconnected into kernel mode, and vice versa. Now, why I'm even bothering in explaining this? First of all, it's an introduction to a more deeper knowledge that I believe that you need to possess in order to understand better the operating system that you're researching malware on top of it. So if you want to better understand the malware that you're researching, it's a great advantage and an added value to understand how the operating system that you're working with is actually working. So for example, if tomorrow we will explore and research kernel mode drivers like rootkits, for example, that are residing in the kernel, you can have a better understanding how this rootkit is actually operating in your operating system, in your computer, in the victim machine. Okay, so it's very important to understand. Of course, if a malware runs in the kernel, basically can do whatever he wants. So let's talk a little bit about Windows process and threads in general. So what is a process? Okay, I define it very shortly. A process is a unit or a container. Not to mention, it's not a Docker container. So if you don't get confused by it, but it's a unit basically of data that defines a loaded file in the runtime memory level. So whenever you double click on, for example, on a game or on a file, an executable file, for example, like Excel or Word or Outlook.exe or even GTA.exe, it will be basically loaded into the runtime memory of the computer or which the Windows operating system manages. It will be loaded into memory. So basically the Windows operating system will load this file from the file system into the runtime memory, which eventually is actually mapped to the RAM, to the random access memory, to this physical memory which is implemented inside your physical computer. So basically this is a process, but each process needs a thread. A process without a thread is not actually a process. It cannot actually run code without a thread. So a thread is a unit of a process that executes the actual machine code. So for example, we take the exe file, which holds the text section. For example, the text section for the most parts, or the code section, includes the machine code, which is actually the compiled code of the developer who wrote the actual code. So the developer wrote the code, for example, in C, compiled it, created an exe file, and then whenever this exe file is loaded into memory, a thread is assigned by the operating system for this process, and this thread goal is to basically execute the process code. Now, any process needs to have for at least one thread, and this thread is called the main thread. But if a developer so chooses, he can basically write his code or his application as multi-threaded. So he can assign more, or ask the operating system to assign more threads for the process, so the application can be executed more fastly, basically. That's it. This is regarding threads. Now, before we go even further, let's basically understand some of the Windows baseline process, the basic process, and then we will explore them in our next video. So, Windows baseline process. Which are the basic processes that you have in Windows? So you'll see that you have the idle process. Okay, maybe part of those texts are not so descriptable, or there is a lot of information about each one of those processes, but again, it's very basic and in general. Okay, so idle is basically a process with PID 0. It has always the PID 0, process identification, and basically you need to be aware that there is a process that's called idle, and also there is another process which is called system, which always has the PID of 4. Okay, and it also doesn't have any visible PPID, or parent process ID, which is because it created by the NTOS kernel exe, which is the process that holds the kernel itself, the kernel of the Windows operating system. And yeah, this is basically the reason why it doesn't have any parent process ID. Now, if you see idle or system process with a different PID, or even with a visible PPID, you can rest assured that maybe it's some malware executing on your system. So this is why it's very important to understand those baseline processes as an incident responder, as a SOC analyst, or as a malware researcher, or whatever. Very basic stuff. Again, I'm not a Windows internals expert. I'm not. I'm basically a researcher. I'm a security researcher. There is a lot of things that I myself don't really, for each understanding, there are many levels of understandings. So I have my own level of understanding, but try to validate the data you see here. Try to research for your own, and try to gain more and more knowledge for yourself. It's not that I telling you that take everything that I say here for 100% for sure, but try to understand things for your own. Okay, then you have the SMSS exe, which is called the session manager. Is the first user mode process with the PPID of system. So basically, system creates SMSS exe. This is why the PPID of SMSS, the parent process ID, is 4, which is the process of system. And it initiates the winlogon exe. Winlogon exe, it's basically the logon screen that you have with the username and password, which you putting in your keyboard, and you logging into your system, or via RDP remotely. Then you have CSRSS exe. Windows subsystem process is used by the anti-authority system user. If you see who is the user that executing it is the anti-authority system, and helping the kernel manage some stuff. Again, in general, if you want to understand more about this process, go to the Windows internal or other courses of Pavel Yusefovich. You have LSAS exe, which contains account password hashes, permissions, Kerberos tickets, and more. LSAS, for example, contains NTLM hashes of users. So whenever you put in your password in the winlogon exe, or in the logon screen, basically, it calculates the NTLM hash, and it checks those hashes against the loaded NTLM hashes in LSAS exe, and whatever the NTLM hash is correct, basically logs you into the system, and if not, it will give you an error. You have LSM exe, which manages local sessions from Windows 8 and above. The process is part of the SVC host exe process. You can again check this out. You have SVC host exe as multiple instances, initiate services with a -k argument followed by a value that exists in software Microsoft Windows NT current version SVC host registry key. So basically, whenever we explore it, you will see that there is a lot of SVC host out there. So if we go to Process Explorer, we can see all of those processes. And if you go here, you can see the idle process, which has the PID 0, and system, which has the PID 4. And as you can see, system actually is the PPID, or the parent process of SMSS exe. If you go double click on SMSS exe, we need to actually run it as an, I say it runs as an administrator. You see that the parent PID is of system, PID 4, and the user is anti-authority system. So again, you can go and validate this data that which you see in the presentation for yourself. And if you go and search for SVC host, you can see a lot of SVC host instances out there, which holds services and initiates them. So you see this -k and the registry key, which is actually auto starts from. Okay, you can go and even explore this registry key and see its data, whatever. For each process, you can go and view its threads. If you go here to the threads tab, you can see this SVC host has only one thread. I think this process not, for example, if we go here to another process like this one, or VMware VMX, for example, we can go and see there's a lot of other threads. So we can see it's multi-threaded. You can go to the TCP/IP tab, see whether this process communicates to an outside or to a remote or even local IP address or domain name. You have here this resolve address, which you can resolve basically an IP address to a DNS, to a domain name, based of course on DNS queries. And you have the security tab, which gives you the security context or the security token of the process, and for which user it's actually executed, and what is the permissions that this process has. You can even view some strings of the process on the image level, which is on the file system, and the memory level on the memory runtime memory level. So I actually like using a process hacker when viewing strings and searching for regular expression like IP addresses and domain names for IOCs. Process hacker gives me more capabilities than Process Explorer. So yeah, this is in general. If we go to LSAS, you can see LSAS exe here also. You can see here all the loaded modules, loaded DLLs, and the handles it got. So for example, if I go, I can see that it has a handle to the folder of C Windows System 32. And whenever you see, you have all of those types. So if you see the file type, basically it's a handle to a file object in the file system, and the key is a handle to a registry key. You have process handles. For example, if you use the open process Windows API function, you can get a handle into another process, so you can inspect it. For example, if you have a malware which wants to, for example, to inject a malicious code inside another remote malware, you can inspect the handles into the remote process or the remote threads of the remote process, whatever. And you have other types like mutant for mutexes and semaphore. And again, if you want to understand better those stuff, you can go and learn them in the course of Pavel Yusefovich. Okay. You have other processes like WinInit exe and services exe, which basically holds the list of the services and executes services as part of the SCM, Service Control Manager, and all of those services are under the HKLM or HK Local Machine System Current Control Set services. You have the WinLogon exe, which is the logon screens, which is basically the logon screen. Whenever you put your credentials, it basically checks this NTLM hash on the else's exit process, and whether if you're basically logging with the domain user, it will authenticate with based on the Kerberos protocol, or the Active Directory KDC, Kerberos Key Distribution Center, which is also basically based on the else's exit process remotely on the DC itself. So if you go to the remote DC and you will inspect the KDC service in the services.exe window, you will see that the process that stands behind the KDC is else's exe. And of course, you have the Explorer exe, which is the basically the whenever you go to the files and the folders that you're exploring and everything, it's called Explorer exe. Yeah. So this is the process execution tree that we already saw in Process Explorer, and yeah, this is basically for this video. Hope you enjoyed. See you in the next videos. Hello everyone, welcome back. In this part of the course, we'll go through dynamic analysis, and in this specific video through Process Explorer. So Process Explorer is one of the sysinternals tools suite, and it's used to actually explore processes in the Windows operating system. So first of all, let's change it to tree view by pressing here in the process tab. You can basically play with it, and then it will change to this tree view. And then you can see who is the parent process and which child process it actually created. So let's first explore what kind of tabs each one of those processes is having. So whenever you're choosing, for example, let's go to one of those processes, for example, explorer.exe, double click on it, we'll see all of those open tabs. So the first tab is image. It basically defines from what path the image was loaded from the file system into the process, as a process into the memory of the operating system. So you can see that the directory, basically that Explorer exe is loaded from the C Windows path. And the image type is 64-bit, and it doesn't have any parent process in this example, and the user that is running under is Calibre, which is my local admin user. I have also here the option to submit it to various tools to check whether it's malicious or not, to verify its signature, or even kill the process, or if you want to explore the path of where the file is coming from, or from which path the file is coming from. You can go to the performance tab to see the performance usage. You have a graph of the performance, disk and network usage, the resource usage of the GPU. You have the threads, the number of the threads, if each of the threads have a TID or thread ID, how much CPU it uses, how much cycles, or what's so-called CPU cycles, whether it's in suspend or not. You can go and actually suspend the thread. You can do right click, or basically here use the suspend button to suspend this thread. You can kill the thread, you can view the permissions of this specific thread, and so on. In the TCP/IP tab, you can view domain names or even IP addresses that the process is communicating to. In the security tab, you can see under which user it is executed and what are the permissions and the token privileges that are used. You can see the loaded environment variables for this process, and you can see or view the strings. You can see here the image radio button, which basically indicates that we see the strings in the image file system level, and in the memory we will see basically the same strings but loaded in the memory. So for example, if in the image level we will see encrypted strings, in the memory level we will see them we'll maybe see them decrypted because it's on the memory runtime level. So this is regarding the tabs. Now let's play a little bit and configure our tabs to work here as a researcher. So let's do right click on the tabs here, select columns, and here I can see the columns that I can use. So I have the process name and PID, which are mandatory, of course, so I don't have the option to remove them. Let's also add a username tab to see under which user it's executed. So for example, if you will see a process that is doing a privilege escalation attempt, you can see that maybe for the first time it is on running under a local administrator or under a regular user, and from there you can see it changes to an anti-authority system, for example. So you can understand that this process actually changed itself and escalated its privilege. You can basically also add the verified signer to see who is the company who signed the malware or the legitimate file or whatever. We can here add the image path. Let's also add the command line arguments of the process, auto start location to see where it starts from automatically. For example, a persistence mechanism from the services or run key in the registry key, etc. Let's see the VirusTotal tab also. So if we submit it to VirusTotal, we'll see it's the number of detections. And basically that's it. So let's do OK. And this is the way I like to play with it. I like to put the PID here, then the username that it executed under, then the path, and even before the path to see the command line arguments. Like this, the command line arguments of the process. But as you can see, the command line arguments also includes most of the time the path, so we can basically remove the path here. So let's remove the image path, and let's see what we have more, and we have the VirusTotal tab. So if I want, I can basically go and do, for example, I can go to options, VirusTotal, and check virustotal.com, do yes. Most of the time it will also spawn this browser. We can close it. Now we can see the number of detections for each one of the processes. So this is the way that I like to work. I can also configure the difference highlight duration. So for example, if processes spawned or even killed, for example, so I want to see the number of seconds after it's killed. So for example, if a process is killed, I want it to be hold on the Process Explorer window for example 5 seconds. The maximum amount of time is 9 seconds. So let's put 5 seconds. Just respawn Process Explorer again. Now it looks better. Had a bug for a moment. Only part of the process are shown for whatever reason. Now, if I want to view some information about the process, like the loaded DLL modules and stuff like this, I can go to View, Show Lower Pane, and here I can see for each one of the processes that I select, the threads that are running, DLLs that are loaded, handles that the process got, and stuff like this. So I can see here all the VirusTotal detections, and for one of the examples I use here this KMS server only to show how the Process Explorer is actually useful as part of an incident response or as IR, and you can see that it actually detected this process malicious, 43 out of 72 detections. And of course you can go and research about this file, what it does, and so on. Okay, if you want, we can even kill it, kill process. And because I configured it for 5 seconds, you saw that it took 5 seconds for the process to disappear from Process Explorer. So this is basically how I like to work with Process Explorer. And again, it's very useful to see where's the parent process, the child process, what are the permissions, how many threads that are in the process that we're or the malware that we're researching, the DLLs that are loaded, and even I can submit the hashes of the DLLs to VirusTotal, as you can see, the handles it got, and so on. So this is for this specific video. We'll continue with Process Hacker as another great utility to search strings and regular expressions inside a process. Thank you very much. See you in the next video. Hello everyone and welcome back. In this video, we'll go through using Process Hacker. Process Hacker, it's like Process Explorer, but with some more advanced capabilities, like the ability to search stuff inside processes, which I find very useful in malware research. So as Process Explorer, I can play with this view and make it tree view, like you see this parent and child process relationship. I can add columns like this command line column, which I did with choose column. You can remove it. This is the default view. Can again put it again here and play with it. So as you see, it's not so different from Process Explorer. But for example, I want to find a handle or a DLL inside one or more process. I can, for example, search for kernel 32 DLL, even do a regex search and see in which process those modules are loaded, and learn a lot about the operating system or even the malware that I'm researching. But not only in a system-wide search, but in a process-specific search. What I mean by that is, for example, if I can basically go to one of the process, for example, let's spawn CMD and write some dump string like example. Again, of course, it's not a real command, but it's just an example string that I put in the memory. So if we go to the CMD or even the conhost exe, which is a child process of CMD exe, we'll double click on it and we'll go to the memory tab. We can go and see actually each one of those memory pages. Part of them are mapped, part of them are private. And we have the protection bits. If we see read R, which stands for read, RW for read write, and we even have RWX for read, write, and execute. A lot of malware like to inject payloads into allocated memory pages. For example, a malware can do virtual alloc and then inject some malicious content into this allocated space to a remote process, or even do a self-injection and inject a payload to itself. A lot of malware like to allocate read, write, execute pages, inject their code and actually execute the code. And another thing that they can do, they can actually allocate memory with read, write. They can write their shellcode or their malicious code inside this memory page and then change it to RX, to read, execute, and then actually execute the code, and this way even bypass antivirus and EDRs. So you can do a refresh here if you want to see newly added or allocated pages. And what I want to show you is actually how you can search strings inside the process. So if you go to strings, what I like to do is detect Unicode, to detect Unicode characters and not only ANSI or ASCII characters. And most of the time I do private and mapped. And then I go and actually filter here. And I can search for this string, for example. Yeah. And here I can see the string example is not recognized as internal. So I see the string and I see the actual output. So what we can learn about this is that CMD, whenever I type something, it actually allocates new memory for the purpose of the output itself. Okay. So for example, if I do ipconfig to show the IP, can do another refresh strings mapped. Okay, filter contains and search for ipconfig. And you can see the result of ipconfig. So I will not see the output here in this example because ipconfig is actually a command, or it's actually an executable file which is under the C Windows System 32 folder. So it actually calls to a different executable. Okay, so this is how I can search for a string or even for regular expression. So let's take a step back and, for example, go to the network tab here, and I can see, for example, let's see, I have this svc host exe process which communicates to a remote IP, some kind of a remote IP. So I can double click on it and it will cross-reference and basically redirect me to the specific SVC host that is communicating with this IP. So I can do double click on it, go to memory, strings, mapped, okay, and then here I can not only find the specific IP, but even find other IPs using regular expression. So I can do here filter, regex, and use some kind of a regular expression that I can find in the internet or even write for myself. So here I have a pattern of an IP address. Do OK, and here I can basically extract all of those IPs, and here's the IP that is actually communicating with, and I can use it as part of my IOC list, or indicators of compromise, for example. So this is how I use Process Hacker as part of my malware analysis journey, and see you in my next videos. Thank you very much. Hello everyone, welcome back. In this video I'll show you how to work with Procmon, or Process Monitor. So let's spawn Procmon, and Procmon is part of the internal suite. You have Procmon 32-bit version and Procmon 64-bit. We'll use the 64-bit version. So if I want to remove all of those events, I could do Control X or this button for clear. And as you already saw, I stopped the capture button. So if I do capture, it will go and capture all of the system events that are occurring right now. So let me just stop it for now. And you have several types of system events that Procmon is collecting or monitoring. So it monitors registry activity, file system activity, network activity, and process and threads activity. So if I remove those buttons, you can see it will basically remove them from the view. If I want to be more specific on the registry stuff that are going on the system, I will choose only registry. And if I want file system, I will do file system. And if I want everything, I will basically choose all of those 4 buttons. Now, as you can see, there is a timestamp for each event. There is the process name, the PID, the operation that was made, the path on which, or from where or on which it was made, and the result, whether it was successful, name not found, failed, or otherwise. If I'll double click on this event, I can see the date, the thread, class, the operation that was made, the result of the operation, the path, and the duration of the operation, the process name, the loaded modules, and even the stack of the process. Sometimes it can be very useful. Now, let's, for example, monitor some activity. So let's monitor activity of a specific process. So let's do filter, and here I can choose on what kind of criteria or conditions to filter the events. So here I have some exclusions that are by default configured in Procmon. I will not touch them. I will leave them as they be. Let me go through some of those operations. I can filter by architecture, architecture ID category, command line arguments, company, image path, PID, process name, and so on. So let me choose process name, and the condition can be is. So for something very specific, is not, less than, more than, begins with, ends with. For example, if I want to see all the events that ends with .bat or .exe or .dll, I want to search for specific string on the process name, so I can do something contains. Okay, so for example, let's do process name contains PowerShell. Now, because I'm using contains PowerShell, I'll find any instance that is running under PowerShell, whether it's PowerShell exe, PowerShell ISE exe, and so on. So let me do OK. For now, you can see there is no nothing to show because I filtered everything. Another cool feature is to do drop filtered events. So it will drop any events that are not part of the filter that we choose. So let me choose drop filtered events. It will only show the events that I choose to filter here. So let me do Control X to remove everything. Let me start and capture it basically. Now, for now, we've seen no events. Now, if I disable drop filtered events, it will take events, but it will not show me any anything because again I filter them here. So if I disable it and do apply, I can see everything again. If I choose here and do apply, it will remove them. But for optimization purpose, I will do drop filtered events, so it will not take all of the system events. Do Control X to remove them. And while I'm capturing the events, and of course after I did the drop filtered events, you don't really need to do it, or it's not mandatory, but again, it's better because if you don't want to your Pokemon to be crashed and to take a lot of irrelevant events, and you want to research something very specific, you can choose this option. So let me execute PowerShell. So here I have Windows PowerShell, and I have the x86 and also the ISE version. So if I execute Windows PowerShell, I can see it found PowerShell exe. And also if I now spawn PowerShell ISE, it will also find PowerShell ISE. I can go and do auto scroll or Control A. So for new added events, it will scroll it automatically. So now we can see it also found PowerShell ISE. Why? Because I did filter with contains. But if I did this with ease PowerShell exe, I need to do something very specific like PowerShell exe. Then add. Okay, now you can see I have only PowerShell exe displayed to me here. So let me remove all the events. And now let's, for example, find another event type. So for example, let's do an exercise and let's change the process name to CMD exe. And let's find operation. And we have different types of operations. If we scroll down here, we can see a load of image, create file, which stands for creation of file and also for opening an existing file. If you read about the create file Windows API function, you will see that the same Windows API function of create file, it not only creates file, but also opens a handle to an existing file with the same name that is passes as the parameter to this function. So if I do create file for output.txt, for example, which is a file, and the file is not created yet, it will create it. But if the file is already created, it will open a handle to this existing file. But another thing to mention, it's not that the create file Windows API function is used here, but even if I use different Windows API functions that are opening files, or even if I use the C built-in fopen function to open a file handle, I will also see the event of create file. And what it means that the fact that I'm seeing the create file event doesn't really mean that the malware or a legitimate process actually used the literally create file Windows API function. Okay, so any event that surrounds surrounding creation or opening a handle to an existing file. You can do it for other event types, for example, querying a key in a registry and reg create key and stuff like this. So let's find anything that includes the file. So let's do, for example, write file. Okay, so the two filters are being CMD exe and write file. So now let's go and do CMD, go to desktop. And now let's create an event of a writing of file. So let's do echo something to out.txt. So now you can see that an event of a write file is created, and this content was written to this txt file, and the result is success, and the length of the characters is 12. And again, the fact that I used here echo and wrote this string to this file doesn't really mean that it actually used the Windows API function of write file. It can use different functions to do it. Okay, so this is what I want to show you. Again, if I remove for example, the write file operation, again, you don't see any other events because I did drop filtered events. So now if I'll do here, for example, I will see different type of events like create file to get a handle to a file, then query basic information, then close file, and then again for each one of those folders, directories, or files that are residing in the desktop folder. And in that way you can basically find interesting things. So for example, you can also go and find anything that in the path has the .txt, for example. So let's do path ends with .txt, and now I found again this specific event, and in that way you can find interesting stuff. For example, if you see a lot of write file operations, like for example create file, write file, and then close file, for example, and you see hundreds or even thousands of such events, you can maybe conclude that maybe there is a ransomware that encrypts files in the file system, in the operating system. Yeah, so that's it basically. We'll, of course, in the continuation of the course, whenever we do full-fledged malware analysis, in the dynamic analysis part, we'll see how all of those tools like Process Hacker, Process Explorer, Procmon, and the other tools, and we'll also see how to work with Procmon alongside IDA whenever you're debugging a malware with IDA, for example, and you can see alongside it the events that the malware creates in the system. So it will be very interesting. So thank you very much. See you in the next video. Hello everyone and welcome back. In this video we'll learn how to monitor Windows API functions on runtime execution. We'll use a tool called API Logger. In order to analyze a process, we'll take the Kronos banking Trojan as an example. I'll go here and select, go Kronos, and select the exe. The way that it works is by taking a DLL, injecting it to a target process, and actually hooking those functions. And by hooking those functions, it can monitor all of the Windows API functions that are used by the targeted executable in this lower pane here. So I'll do inject and log, and we'll see all of the Windows API functions that are logged or used by the Kronos executable. As you can see here, it gets some startup info. It uses the create tool help 32 snapshot and the process 32 first and next Windows API functions in order to see what kind of process exists. And as you can see, one of the processes it found in VM tools D. So basically it found that it working, basically running under a virtual machine. So by that we understand that we have an anti-VM or anti-sandbox techniques applied here. And there are other Windows API functions like the create mutex used here, the socket, sleep, and so on. So in that way we can actually monitor Windows API functions on runtime execution and learn a lot about the malware. I also recommend you to use the ignore long sleeps because if there are used sleeps, it will basically make it run faster. Because if you don't check this ignore long sleeps, it will actually wait for the sleep. So for example, if you have a sleep for 1 hour, it will wait 1 hour. And this is same for advanced get the count and ignorance of exit process, if there are something like that in the malware. Okay, so thank you very much. And of course, we'll continue with showing more tools in this dynamic part. Thank you. Hello everyone and welcome back. In this video, we'll learn about a tool called CMD Watcher. It's a great tool for inspecting command line arguments of processes. So in order to understand a little bit about what are command line arguments of process, let's go through some of the system process on Windows using Process Explorer, for example, or Process Hacker. Doesn't really matter which tool you use, but basically if you go to any one of those tools, for example the CMD exe, go to general, you'll see some information here. One of the information you see in process is what's called command line. So one of the questions to ask is from where this kind of information is coming from. So like how Process Hacker or Process Explorer actually collects such data from each one of those processes. So there's what's so called in Windows, of the Windows operating system, you have what's so called data structure. And the data structure basically is holding information for different type of entities in the operating system. So for processes, there are what's so called there's what's so called a PEB structure, or process environment block. So if we go to the PEB structure and read about it in the MSDN documentation, we'll basically understand that each one of those processes in the Windows operating system, each process in the Windows operating system, whether it's the default system process or the process that you are executing, whether those are applications or games or stuff like this, they're having what's so called a PEP structure. It's a user mode structure that holds all of this information that you see in the process. And one of this information is called command line or command line arguments. So there are processes which executed what's so called standalone without any type of arguments, but again there are other processes which are executing with some arguments. So for example, if we execute cmd and we'll do cmd/c, for example, and run PowerShell, which a lot of malware tend to do, well, basically if we go down, we'll see that cmd actually created PowerShell. But if we go to the cmd process, we'll see the command line of cmd/c and PowerShell. So you have many different fields on the PEP structure, and one of the fields called process parameters. If we go read about it, you'll see it's a pointer to an what's called RTL user process parameter structure, which contains the process parameter information such as the command line. You have more fields like whether it's being debugged. So if you saw, for example, the isDebugger present Windows API function used, so if you go to the internals of this Windows API function, you'll see that it basically checks for the being debugged field under the PEP structure of the process. If it's 1, it is debugged. If it's 0, it's not. You have other information like the LDR, which is a pointer to what's so called, if we go down here, if we go to the LDR, it's a pointer to what's so called a PEB LDR data structure. If we click on it, it will basically point to what's so called the in-memory order module list, which will hold all of the DLL or loaded DLL modules in the process. So basically, if we do double click on a process and we go to modules, all of those DLLs are presented, and Process Hacker or Process Explorer, such tools, actually collecting this type of information from this structure. So this is a little bit about the internals behind it. So now that we understand a little bit about the internals behind process and command line arguments and stuff like this, let's take and extract the CMD Watcher tool here. Do 7-zip, extract here. We'll ask for a password. So basically, you have the website of Chaos Security. They provide this tool called CMD Watcher, and you can take the password for the zip file and extract. So I have both 32 and 64-bit version. We'll run the 64-bit version. And basically execute the doc here. Now this doc is actually an Emotet malware, or the first stage of the Emotet attack. Now if we do enable content, now before we do it, actually we'll do start to enable content. It basically, what CMD Watcher does, it actually takes arguments of process and then shows it to you. So you can either kill the process or resume the process. So for the SVCOs, for example, we'll resume the process. And as you can see, we cached the command line arguments of the Emotet malware. So we see CMD, CMD/C, and some obfuscation they did here, and some other cool stuff. You can take, of course, this information, we can base64 decode it and continue with our analysis. So this is a basic introduction to this tool, which can be very useful in dynamic malware analysis. Thank you very much. See you in the next videos. Hello everyone, Uriel Kosaiv is here. In this very short video, I will show you how it is possible to debug DLL inside IDA Pro. A lot of people out there are struggling to debug DLL files with IDA Pro and rather use x64dbg, for example, which automatically import the DLL and basically execute instructions and code there. With IDA, it's a little bit different. Let's see how we can debug a DLL file inside IDA Pro. So first of all, we need to discern whether the DLL file is a 32 or 64-bit. As we can see, it's 32-bit. So we can choose which IDA version to use. If it's 64-bit, we'll use IDA 64. If it's 32-bit, we'll use IDA 32-bit. Second, we'll go and launch IDA 32-bit. And I will load the DLL file. In this example is an actual Emotet DLL file. And just for this example, I'll put a breakpoint in the prologue of the first function. As you can see, we're in the DLL entry point. And if we go and check the exports of the DLL, we have only one export. So first of all, we need to select our desired debugger. In this case, it will be local Windows debugger. And in order to configure the DLL to be debuggable, we'll go to debugger and do process options. So here, a lot of people are struggling and it's a little bit tricky. A DLL file is basically a file from where functions are imported into processes which are based on executables, p.exe. So we basically need to configure an exe file which has the ability to import or load functions from DLLs. So we'll use the well-known run dll32.exe in order to do that. Now, because in this case we are debugging a 32-bit DLL, we use the CISWO64 version of the run dll32.exe. I know it can be confusing, but the CISWO64 folder are holding the 32-bit version of system binaries, and system32 folder is actually holding 64-bit binary version. So let's put our path inside. So we have C Windows syswo64 run dll32.exe. And the input file will be emotet.dll. The directory will be the same directory as the DLL itself. And we'll put the DLL also with full path on the parameters here. Now, because we only have one export, which is the DLL entry point, we'll use the comma, then #1. So from a different point of perspective, if we will use run DLL, for example, run DLL32, go to Windows or to the desktop actually, and do run dll32.exe, we'll then want to load our DLL, and then we'll do comma and the exported function that we want to load. In this case, we'll only have one, so we can do #1. Of course, if I'll do enter now, it will load and actually execute Emotet. Let me get back to IDA, do OK. Now run it. Yes. Now you can see we hit the breakpoint and you can debug it freely. Hello everyone, welcome back. In this video, we'll go through analyzing pickup or packet capture. As part of dynamic analysis, it's very important to know how to analyze network packets and how to analyze network communication in general. Not by only using tools like Process Explorer and Process Hacker and seeing IP connections and domain connections and stuff like this, but actually go into the guts of network packets. So I have a file here called 404 not found .pickup, and it's actually a challenge that I give in my CMAP, Certified Malware Analyst Professional course that I do for many years. And it's one of those challenges that basically opens up the minds of my students. It not only shows you some very basic and you know some basic stuff of like exfiltrated data or stuff like this, but it actually shows you all of the attack chain from point A to Z, from the starting of the attack to the end of it. And basically it's part of what's called the flood Amy malware, or you already know. I know if you've gone already through this course, you saw me basically reverse engineering and analyzing the flood Amy malware. Till this point, I did very basic stuff with the flood Amy malware, and in the next videos, I will show you a more full-blown analysis of the flood Amy malware. But before I go into analyzing flood Amy and reverse engineering in some level, I want you to get with me a step back and see how that actually started. So let's double click on the pickup and start to analyze it. So before I go and dive into the data of the packets here, I just like to do a brief overview what I see here. So I believe you already know what is Wireshark, and basically it's a packet sniffer tool. In this case, I haven't already captured packets inside this 404 not found pickup, and will analyze this traffic now. So in the left window, we'll see basically the data of each one of the packets, or the levels or the dissected levels of each one of the packets. In this case, you'll see the TCP packet here. So the left pane is based on the TCP IP model basically. So if I'll check the HTTP, we'll see also the application layer. So in this case, it's the hypertext or hypertext transfer protocol, or HTTP. So in the right pane, you'll see all the hexadecimal values and ASCII representation of this. So again, I'm not going now to explain what is Wireshark and how it's built and all of that, because I really believe that it's a very basic knowledge to have, and you can learn it from anywhere basically. So I basically will go through this data, and you will see how to also use Wireshark while you're analyzing packets. So you can use many filters, like for example, if I'll do HTTP, and you'll see all of the HTTP packets relevant for this capture. So let me just remove it. So let me just go through the packets. I see many TCP packets, HTTP packets, and so on. Many data is transmitted here, and also some SSL connections or whatever. So basically, this is what I see. I see basically here the source IP address that are communicating, which is seems like a local IP address, and there is some destination IPs like this 103 and 169. Seems like public IP addresses of some kind of sorts. Let me get back up. Now, if I'll go packet by packet, it can take some time, but let's see. So I have a local IP address of 10.7.13.101, which is communicating to some sort of IP which is 169.239.129.17, which is some kind of a remote IP. And the first three packets I see here is what's called TCP three-way handshake, which is communicating to port 80 of this IP address. So basically it's the mechanism to actually see whether this destination port is open for communication. So now see there is also called an HTTP options method. Is sent basically to the server. It's just to check what kind of HTTP methods are can be communicated with, or what kind of HTTP methods the server is supporting, like HTTP GET, POST, PUT, DELETE, and so on. So let me just go into this packet. We'll do follow HTTP or TCP stream, doesn't really matter in this case. Go inside and I'll see here the request and the response. So the request is basically highlighted in red and the response is highlighted in blue. Now I don't see something very, very interesting. I see the host header, which is the destination IP address. It can be also a domain name. I see that the server response included with this Nginx whatever server, and it responds with the 200 OK, which basically says that okay, you can I communicate with you. There is an OK to this type of communication. So for example, I go to a page, I get the page, I get all the content of the page, I get 200 OK. Sometimes you will also see 404 not found for pages that do not exist, and it's actually one of the reasons why I call this this challenge 404 not found, and we'll see in a moment. One of the interesting things to inspect in HTTP packets is what's so-called the user agent. See that the user agent here is Microsoft Office Protocol Discovery. So now remember, the red highlighted text here is from the one that made a request. So it's basically tells me that some kind of an Office application made this request. It can be Word, Excel, PowerPoint, or any kind of Office application. So it gives me a hint that the process or the application of this machine, could be the victim machine, is made through an Office application, which is interesting thing to note. Okay, so let's note it on some notepad or whatever. And let's close it, remove this filter, and let's continue. So sent a request, got a response, whatever. Now let's continue. And then we'll see an odd HTTP GET request to a /404. Now it can get confusing, and a lot of people can think that it's actually the 404 response code. And it's not, because you see that the local IP sends a HTTP GET request to a remote IP on port 80 with an HTTP GET request to a 404 something. So it's kind of weird. A lot of people will think, yeah, maybe it's the 404 response code. I don't really need to go into it. Now let me just, get all of this mess and get all of those HTTP GET requests for you. So let me do HTTP request method equals to get. And now I only see 4 packets. I see a GET request to 404, 200, another thing called space1, and another gibberishy name resource or file, whatever. Okay, so let's get into it. Let's go follow, it should be stream. Okay, now I see something very odd, very strange. See, this equals cmd/c, then PowerShell, and it executes web client download string and makes a request to this 200 file, which again, if I go to the, if I'll do again the same filter I used before, I see that there is another request to 200. So basically what I can understand is that, yeah, there is an Office application that actually executes this PowerShell or CMD, or it's an Office application it can be Word, Excel, or something, which executed CMD with the /c. It can also be with /r potentially, which is actually execute PowerShell and executed something from this 200 resource. And another odd thing to see here is this exclamation mark A0. If it basically can remind you something, like let's ask it again. We saw that in the user agent in the first packet of the options packet with this Microsoft Office protocol discovery. Now, one of the questions arise is, it's okay, it's an Office application, but it is a Word, Excel, PowerPoint, because if it's Word, it must be in a VBA macro or malicious VBA macro executed. But if it's Excel, it uses XLM macro, Excel 4.0 macro. Now, this exclamation mark A0 actually indicates for me that it is possibly Excel actually used here. Excel and malicious Excel file with XLM macro or Excel 4.0 macros. Okay, so let's note it also. And let's continue to our next packet of 200. Follow HTTP stream. And here we'll see something else interesting. So I will see another PowerShell script, which is the PowerShell script retrieved from the 200 resource from this /200 that we saw. And this one actually goes into this IP and takes this resource space 1, and actually, from what it seems, it takes the file of space 1 and saves it as a winmedia2.exe under the user's temp folder. And you can see it with the download file here. Then it actually goes and starting the process, or starting this executable with the start process PowerShell function. And if you go further, you'll see that we have actually a PE file in the response with the MZ header and all of the other very known headers, like this program cannot be run in DOS mode, with all the sections here, the text section, R data, and all the other. We actually have 2 R datas. And yeah, it's actually the flawed AMI malware that we already started to analyze in our course here. So this is how the attack actually occurred here. Now, if we go to File, Export Objects, HTTP, we can actually go and export all of this, including the space 1 file, which we're analyzing in our course. So the attack actually started by a phishing email attached with an Excel file, which is weaponized with what's so-called an XLM macro, which actually executed CMD, which then executed a PowerShell, which then loaded and executed another PowerShell script in memory, which eventually downloaded a file named space1 and saved it in the victim machines as winmedia2.exe under the user's temp folder or the victim's temp folder, and then executed. So this is how the attack chain started. If we go to the end of the packets and we'll go for this SSL packet, for example, to follow TCP stream, we'll see some strange data here, like the ID of the machine, the operating system version, which is Windows 7 in this case. The specifically this victim was an admin privileged user. It's other what's called, the machine is called BOPC, and all of this information is actually what was exported or exfiltrated from the victim machine and sent to some sort of C2 server. And even the AV name variable exists here. So you can learn from it that the Flood AV malware tries to see whether there is an antivirus or EDR or some sorts installed here. Very interesting stuff. So in the next videos, we'll go and actually dissect the Flood AV malware. Thank you very much. See you in the next videos. Hello everyone and welcome back. In the previous video, we got started with analyzing the Flood AMI attack chain based on the 404 found pickup file. So let's continue with the analysis of the Flood AMI malware. Let's do double click, and basically in order to continue with this pickup, we can do file, export objects, HTTP, and we can actually go and save this space1 file, which is the actual winmedia2exe file, which was saved in the temp folder, as we already seen in the analysis of this pickup. Let's do save and save it on the desktop. And close Wireshark. And here we go. So let's start with the basics. Let's put it on a hex editor like HXD, and we see that it's the MZ header, and this program can only run small. We have the PA header and all of the standard stuff. We actually see we have the text section, two R data sections, which can be odd, something that we can check. We have the data section and a resource section. Okay, let's go and see if there are any interesting strings to see here or something that catches our eyes. And we see the patterns that we already talked about in the previous videos in the course. We see some kind of an encrypted blob. Okay, so let's spawn up CMD, go to the desktop and export some strings. Let's read the strings, open it up inside Visual Studio Code. Okay, let's see if we have something interesting here. There is a string, huge string here, not something interesting for us right now. Okay. Let's see if we can find something like .dll, for example. We see here. Okay, see .exes, .dlls. Maybe we can use them to sign this file. So let's collect them as IOCs for now, or potential IOCs. Let's collect all those process names. If you search them in Google, you'll see that are basically antivirus or endpoint protection. We see the use of Windows API functions like find resource, which goes for the resource section in the PE. We see the gets the system directory. We don't really see that it tries to hide those Windows API functions with some sort of encryption. Use load library. Immediately, if I see load library, will go to the get proc address, and I'll see also the use of get proc address for potential dynamic API resolve. And if we're already talking about, Windows API functions, let's already put it in tools like PE Bear. So let's first of all save this side as notes. Let's go for the imports. And also we have kernel 32 DLL with all of those processes, with all those, excuse me, the Windows API functions. So see the create tool health 32 snapshot with create with the process 32 first and process 32 next for process enumeration, possibly lock resource, load library, get proc address, a virtual for allocating memory, and other interesting stuff. If we go to user 32 DLL, don't see something interesting here for now. See the use of WinSpool DRV, and what I see, it goes for the service manager or whatever. Okay, so now okay, from what I see from the retailer, it's actually was compiled Visual Studio, C, C++ possibly. Let's put it inside Detected Easy and see whether it's packed or not. We see it was compiled in Visual Studio with C, C++. Let's check the entropy. And we see that the resource section has heavily packed. Can be possibly encrypted, compressed, obfuscated, or whatever. So immediately I will go try to use resource hacker to inspect the data in the resource section. Let's check this RC data or this HTML. And it's possibly the encrypted blob here. So it will try export this encrypted blob from the resource section using the four Windows API function of find resource, lock resource, load resource, and size of resource that we already saw in the strings and imported in the import address table or the IAT. Decrypt it, allocate some memory, move it to the allocated memory and execute it. So this is my goal on this case, from what I think. But again, it's whenever you think of a direction, it's for the take it as a theory, but you need to actually go and validate the theory. So yeah. So from what it seems, again, we have a heavily packed resource section. We saw those gibberish stuff. We see a very little imported functions relatively to other malware, other legitimate files. Not too much visible strings, and some visible strings of process names of antivirus products. And it's actually interconnected to the fact that if we go to the pickup and we go down here and do follow TCP stream, if you remember, we saw this AV name variable or part of the data that is actually exfiltrated and sent back to the C2. So it kind of makes sense. So now let's go and statically check the code inside IDA. We've already done it in our previous videos. So let's go and actually open up this IDB file. And let's go to our starting point. So we already saw in the previous videos in the starting of the course all of those process names, and each one of those process names are pushed to the stack as a parameter to this called function, which we renamed to proc_enum with the flag that I like to use over here. So we can actually go and do Control F in the function name window and search for the here flag that we use in each one of our renamed function or subroutine, and that way recognize what functions we already gone through or basically reverse engineered or understood what are the goal of those subroutines or functions. So if we double click on them, we see that create tool help to reduce snapshot and the process to first and next Windows API functions used in conjunction to actually go and check whether those process names or one of them are presented in the system. And if so, they will go and do exit process. So after those checks are done, we'll basically come to this point. So let us basically go and before we actually go and analyze this malware or reverse engineer it, let's do a very basic dynamic analysis. Let's try to execute it through some tools and maybe take some points from there and continue with our reverse engineer. So for a moment, let's close IDA and let's try to go as simpler as we can. So now let us open up Process Explorer. We have all our tabs already configured and the different silo duration configured for 5 seconds. And let me fire up procmon. Let me remove all of those and basically change the process name to space1 .exe. So this is the process name that we'll monitor. As we already saw in the actual attack, in the pickup, it is actually called win_media_to_exe and it is saved to the temp folder, but we will just continue with this name. It doesn't really matter. So space1.exe. Okay, let's do filter, drop filtered events. So we'll only monitor this specific process name. And let's put it like this, side by side. And again, let's validate the filter, process name space1.exe. And basically, we can use other tools like CMD Watcher, Wireshark to do all of the stuff, and we can even fire up our Remnux virtual machine if we want, but it is okay to continue like this for now. So we can actually also use API logger to log Windows API functions running on runtime, but for now let's use just both of those tools. So let me double click on it. One of the things that I like to actually do is to double click on a malware without with regular user permissions, and then again execute it as an administrator and see the number of events in procmon, and that way to distinguish where there is some kind of difference behavior between a regular executed malware or whether it receives administrative privilege and it behaves differently. So let's double click on it. And we see space1.exe is running. And from what I see, it terminates itself. Okay. So Let me just pause capture here. And for now, see 5,576 events. So let's just do a quick brief on the events we captured here. Let's see if we see something interesting. We'll try to see if it created some kind of a persistent mechanism. Maybe you can use tools like autoruns or even filter out operations like recreate key or exit value. So I don't see any type of registry based persistence in this case. Don't see it try to configure an IFEO or in run key or run once key or stuff like this. It just got and set some keys in the internet settings and stuff like this. Not something interesting for me right now. So let's remove this filter. And if we get back, we don't see the exe file. So it's actually deleted itself. So yeah, it has a self-deletion mechanism, and this is why it's one of the interesting malware for me to analyze. So for now, we see 5,576 events. Now let me just go and note this number. And let's see if we have more events with administrative privilege. So let's do it again, export objects, HTTP, save this. Okay, and let's do Control X to remove all of the events and do run as administrator. Okay, very interesting. Now we saw less events. So I think it's because it actually detected that it were executed before something like that. So if we now go and run it again, even without administrative privilege, interesting. Now again with administrative privilege. Okay. So it gets to a point where it actually detects something that it does like and removes itself. So yeah, let me just get it back here. So as you can see, in such cases, you actually need to go and deep dive into the malware. And using automated sandboxes or static analysis or even dynamic analysis tools without actually understanding the code can be very difficult, especially in such cases. Okay, now let's try to attack it from a different way, or a different perspective. Let's try to use tool like API Logger, for example, and see if it will give us something. Let's not give up on dynamic analysis tools. So let's go for API Logger and try to execute it. Go to desktop, amy space 1 exe, injected log. And we don't see any other Windows API functions. Very interesting. You can even see that I try to use here those checks. Nothing interesting. Okay. For some reason, it cannot actually continue. We do stop logging, for example. Let's see if the DLL is actually loaded into the space 1 exe, and you'll see API log DLL is actually loaded. Interesting. So for some reason cannot really go and monitor stuff here. Let's see if the API logger exe is actually terminated, if the space 1 exe can continue and execute its code. And it's actually continuing to execute its code and basically delete itself. Very interesting. Very interesting. So even tool like API Logger didn't have the chance to actually log the Windows API functions inside. Now we can go and try to use different tools like API Monitor and you know, go around and around and around. And this is a point where we actually understand we need to go into the code itself and reverse engineer it. And in the next video, we'll do just that. Okay, this is the next video that we're continuing now with our Flood Amy malware reverse engineering. And now we're actually in a point where we cannot really continue understand what the malware actually does with the basic stuff of static dynamic analysis tools. From the static analysis, we understood that the resource section has an encrypted blob inside, and it is potentially somehow decrypted on runtime and executed. Because why the hell it will have encrypted blob inside it? And furthermore, we saw that Windows API functions like the find resource, lock resource, size of resource, and load resource are used. So yeah, it kind of makes sense. Now we try to use tools like Process Explorer, Proc1, and even API Logger, and didn't get much. And I did it for purpose. I did it to show you that you have to go and to use reverse engineering tools like IDA and x64dbg, even if you don't understand too much assembly or you don't have the deepest knowledge out there. And I want to show you how you can approach it and get the best out of it, even if you don't have a great experience in reverse engineering, which can take some time to actually understand those topics. And you need to have a lot of patience and a lot of efforts put into it. So let me just close Process Explorer here and get back to our business. Let me clear all of this garbage here and get back our sample. Let me put it here, and let's call it space one exe, or can just remain with it .ex. Doesn't really matter for IDA, because if I go and use IDA and debug it to basically execute it, doesn't really matter whether it's with the .exe extension or whatever. So now how I would approach it without going too much into details, and reading any assembly line, is basically open up IDA, going to the starting of our code, and put a first breakpoint. Now, what I will do, after I put this breakpoint, I will use procmon and filter for the specific process name, space1.exe, or in that case it will be .ex because I renamed it, and I will monitor it. Now we'll see that after I will start IDA, actually wants to use the .exe, so let me just update it here, like that. Rid of those windows, and now we are in debugging mode. Now we are at the starting of our malicious code here. We are at the start. So if we go now to procmon, you'll see a lot of events, 460 events. All of those events are basically part of the loading of this process, or the loading mechanism. So all of those events are not relevant to the basically to the execution of the malicious code. All that you see here is basically part of the loading process of this executable to the machines or the operating system's memory. That's it. So you can get rid of all of it. And I like to use procmon alongside a debugger like IDA or x64dbg, because in each executed code block or function, I can see if there are any interesting registry, file system, network, or process and threads related events, any type of system event. Now, basically, if, for example, from this line of code to here, for example, will be something interesting like creating a registry key for persistence, I will see it in procmon without getting deeper into each line of code here. So it's a trick to use. So always when you go and reverse engineering something, put a breakpoint in the start of it, monitor with procmon, and for the loading events, all of the loading events that you see, all of the starting garbage, basically get rid of it. Now always also go and do Control E in IDA and validate whether there is what's called a TLS callback. TLS callback is a potential function or mechanism to potentially execute code before the entry point. So let's say this is the main entry point and you have more entry points like TLS callbacks, they can execute code before the entry point, and a lot of analysts can actually miss those parts. So it's very interesting and very important to check for those TLS callbacks. So just make sure you check it. So now what I will recommend here is to put breakpoints in each part of the code where test has been made, or a jump, or even a call to a function. And basically jumping between the code blocks with F9, or basically letting the debugger run the code and see if something interesting happens in the system or something interesting is logged on Procmon. So let's say I put a breakpoint in this part of the code. It actually finishes with all of those checks, whether of those processes are existing in the running machine. And I'll do F9. And I get to this part of the code. So all of the code before were already executed for us. Now if we go to Procmon, we'll see that some system events were actually made. So we see that stuff like language was actually checked. What kind of language or custom or locale our machine is using. So you see that the requery key is actually used here to query the values of the locale of the machine. There is another thing here which I don't really recognize, so we can try and go jump to and see it actually goes to this value for some reasons. Don't know the specific reason for this one. I can check this up later, but for now it's not so important. So I can do Control X because it's not so interesting for me right now, and continue. I can do F8 to continue with our code, and we can see that now it highlights the red cursor here. So basically it will go to this part of the code. So again, I will continue and put breakpoints in each one of those calls, and in that way I will see how it behaves in my machine. See here, call to indirect call to pointer, which will hold, which the EBP register will hold. No, whatever. Put a breakpoint here, another breakpoint here. And another breakpoint in this jump, because this jump is basically will go to either one of those code blocks. So eventually it will get to this part of the code, and then there will be a decision to go to this part of the code or that one based on the test EAX, and then by the jump 0. So let me do F9, again F9, and something very weird happened here. If I do OK, see it got to a very weird point in the code and actually stopped. So if I'll try to do F8, it will actually go and crash. So this shows us that in this part of the code or of the function, there is something that actually hinders our analysis. We go back to Procmon, we don't see something that can help us in understanding what it was, but it can give us some kind of, it can potentially in other cases give us directions of what kind of system operations were made, and maybe give us some kind of checkpoints of, okay, in maybe did some registry key enumeration or created a file, and based on that operation it decided to do something. But in this case we don't see something that actually helps us with this case. So we need to understand what part of the code actually hinders our analysis. Let's do Control X, run it again. We're at the start of our code. Again, this is all of the garbage of the loading of the process. Do Control X. Let's again do F9. This part of the code. And let's try to do F8. And we see here 4 parameters are pushed, and then F8 we do F8, it will actually go and execute the code in this subroutine without getting into the subroutine. So if we do F7, it will go inside. But if we do F8, it will basically execute everything here. And again, just to validate, if we do F8, our code is our debugging is crashed. So something in this function or subroutine does all this problem. So I'm trying to understand what is this function. So let's do stop. And we can basically turn off this breakpoint here, because it doesn't really matter for now, because we know that till this point everything is fine. But when you go in calling this function, something hinders our analysis. So again, go to proc1, Control X, start our debugging. And again, as you saw, we didn't really go and understand each one of those assembly lines here. Just go with the flow, okay, for now. Now, if we do, so basically till this point, it didn't find any of those processes. If it were to find any one of those processes, it will go to this exit process, and our process terminated, and so on. So no found process, then it goes to this check. So let's go with the flow. Let it push all of those 4 parameters to our stack without getting into the details of what are these parameters, and do F7. Now, when we did F7, we got to this part of the code. So we have the push EBP, move EBP SP, which basically gives us an indication that is the prologue or the starting of the function. Both of those instructions are basically making some space for us, or initialize our stack for the initialization or the execution of the code that we'll see or be executed here. So now let's go F8. We have some interesting value. We have some value in EAX. We saw that something was moved from this place to EAX, and then the value from EAX was pushed to the stack. I'll not go into understanding what it is right now. We'll continue with the F8. Even if we don't understand each one of those operations, why they are actually done here or executed. Generate an exception, run idle, resume application. Okay, let's say do run. So basically it seems like a garbage code which makes our execution basically to break for some reason. So for me, I will not go and understand why there is get module handle for now, or this debugger present, and I will not get into it. Basically, I'll do just stop, execute it again. And to actually bypass this crappy subroutine, which eventually will try, I believe, to go and basically check the presence of a debugger or whatever, and maybe do exit process. But in this case, it already actually breaks my execution for some reason, and I don't really care about what is the reason, because whatever. So let's rename it code breaker or execution breaker here, which is for the one that actually wrote this malware. It's a great anti-analysis technique, anti-debugging, anti-whatever. Okay, so we actually want to jump and bypass this part of the code. So There are some ways to do it. We can try to change this instruction from J and Z to JZ, from jump node 0 to jump 0, but it will actually divert it and we'll go to the exit process, and we don't want to actually do it. Basically, the best way to do it here is to bypass it and basically try to put the instruction pointer or the EIP in this address here or other relevant address for us. Let's just remove all of those breakpoints for now. And you have two ways to do it. You can go to the EIP here, do basically modify value and modify to the value of this address, or just do right click and set IP or set instruction pointer. Now you notice that I did it before I did all of those pushes. Now it's because I didn't really want to break the execution flow of the program. Now if I did push of part or even all of those 4 parameters and then I did the jump and bypass this call, I could potentially break the execution flow of the program, because other calls will basically use those values in the stack which are not relevant for other functions, and it will just break the operation of the code. So now let's just continue with the execution. So see, push ESI. ESI is basically the start address of this program, of the malware itself. It will call erase tape. Now we can go and actually read about this function, but let's do F8 and you see that basically does another problem for us. So again, we can go read about this Windows API function, try to understand why, but we understood that this part of the code, and even potentially this one or that one, maybe even, can be problematic. So let's again execute the code. Remove the stuff in prop mode here. And just remove the break mode here. And I can even highlight this part of the code in red, so I'll know to not go through this code part. Yeah, like a red alert or whatever. And this problematic code here also. And I believe this is another problematic code, because it will call this and basically kill the process. And I even suspect all of those other code blocks. And I see another find window, which is used here, but with some gibberish values. I don't really care to go through them. Seems like a garbage code with all of those parameters with load library. Again, doesn't make sense. And if you remember, we got to this part of the code in the previous videos in the course, where it got and imported functions or dynamically resolved them. So what we can do, we can basically bypass all of those parts of the code and do like this, set the instruction pointer and continue on. So if we go do F8, we already know that it actually goes and extracts the resource section basically, or the encrypted blob from the resource section. So we'll do F8. Now it does a comparison to check value in ESI, which is 0 to this D word. It does another comparison. And there is call to EDI, which is basically pointer to this start address. So basically jumps me again to the same code, as you can see here. So let me again get back here, and in order to counter this this code, I can go basically and do again all of this thing, and jump it here, set instruction pointer again, run everything, loaded the stuff from the resource section, did a comparison, and I will not fall for it again for this call EDI. I'll basically again do set instruction pointer here, and basically if I go double click here, you'll see that the encrypted blob is actually loaded here. This is the encrypted blob, and with this +6, let me try to recognize it. Here you go. You see this +6 UGSI. This is the encrypted blob actually from the resource section that was loaded to this memory, and the AL is actually with the value of 66 now, which will be used as the XOR key to decrypt the content there. So if I'll do F8 and continue with this, so now you see that this plus actually got to M. Now after the M, you can think of it, it will be Z, like MZ of PE. So let's continue. I will go and increment the ESI, which is now 0. Now it will be 1, and do another comparison of the IF600, which from what I remember, it's the size, can be the size of the encrypted blob. So it checks whether it's, or the size or the number of the loops that it needs to go through to actually validate that it decrypted all of the relevant content or of the this encrypted blob basically. Now it goes again, do this jump 0, and again EDI. If I go to this EDI, it will jump back to the code and yada yada yada. So let me do set IP here, and it will do another XOR, and now you see it's MZ actually. Okay. So again, we'll increment the ESI, and basically it will basically go and allocate the memory in this function. When it will end with all of this decryption stuff, it will go into this function here. Memory will be allocated. All of the decrypted content will be moved to this allocated memory, and eventually it will go and execute the next stage code. Now if we'll see and go to proc1, till now we see that it only got to some language stuff, not something beyond it. So what you can understand is all of this code is actually for the first stage to decrypt the content and then continue with the decrypted code, which will do all of the other notorious stuff. So we'll continue in our next video and we'll get to the next payload. Thank you very much. Hello everyone, welcome back. In this third part of the video, we'll go and find a strategy to let the program actually decrypt the encrypted blob that we found in the resource section here and actually let it decrypted in the memory. Now the problem is when we get to this point of call EDI, it actually points and get us back to the starting of the program. So let me again bypass all of those problematic code blocks and get back to the import functions here. This part of the code, do set IP, execute it normally, and if you remember the previous video, we actually need to go and do a set IP here to bypass this call EDI. Let it decrypt the content. As you can see here, we have this plus, which is then decrypted to M. And if we go through the loop, again, I need to bypass it with the set IP, go again, decrypt it, and we now see the MZ. So we want all of this blob to be decrypted for us so we can continue and analyze this malware. So we need to find a strategy to actually bypass this. So let's try to go back, go with the flow, and do call EDI. Now we're actually here. Now if we change this jump not 0 to jump 0, it will go to this exit process. It's not a good strategy. And if we let this call blocks to be executed, everything will be broken. Now we can go into each one of those functions and try to fix those instructions so the program will not be broken and stuff like this, but I think we can take a better approach and do something more simpler. Let's get back to our problem here, which is call EDI. Let's highlight this, do edit, patch program, and a sample. Let's change it to NOP. NOP stands for no operation, which basically will do nothing. And every time we get through this loop or through an iteration, it will not jump us back to the start of the code. So now there is a catch. I can continue with our decryption process and everything, but if I stop the debugging and go down here, I'll see that I have this NOP X slot, but I want to be sure that it's actually saved. So I'll do Control W. Now it's saved as part of the IDB. So now let's continue again, do the debugging. Yeah, no problem. The database has been patched. It's a normal warning for us that we patched something in the code, and it's only patched in the database level. It's not actually applied to the P itself. We can apply it if we want to by going to edit, patch program, and patch or apply patches to input file, and then it will apply the patch to the actual P file. So let's go check the code, and we see this dbff, and we don't see the NOP here. So again, we can try to change it. Do edit, patch program, sample, NOP. Maybe it will not interfere us, but let's just to make sure, just in case, have the snap in place. And just let's do all those reds so not miss them. We'll understand that there are problematic call blocks. Red, garbage. Those ones also. And we'll do set instruction pointer. Let's do some breakpoints on those calls, or just let us get to let's put a breakpoint here. Now if we want to get to this place, we can put a breakpoint, then do F9. So all the code from this point to this point will be executed, but we can do another thing which is F4. So now I did F4 and everything is executed till this point. Now let's do F8. So we'll see that, yeah, we see the MZ or the M for now. And now we'll go through this loop. And again, now because we have this NOP, we don't have this call EDI to interfere with us. We can continue with the decryption process without any problem. And we see now the MZ, great. And we can continue like that, or just get it finished with. So basically you can go, just if you want to see all of those values changing here, so you see the decryption process, you can put F2 or breakpoint here and do F9 and just let it execute it. And as you can see, stuff gets actually decrypted here. You can also do synchronize with hex view. Let's get to this address and in that way we'll see that stuff gets decrypted, of course, and yeah, you'll see it here like that. And now basically let's remove this breakpoint, and we can again put a breakpoint here, do F9. It will basically execute all of the decryption mechanism, or we can just do F4, and basically we finished with everything got decrypted. So double click, we'll not see the actual place here because it already been changed. So now I can basically just go into F7, go into the function itself here and try to understand how it actually allocates the memory, moves the memory, and everything. Now, because the encrypted blob already has been decrypted, we can go and use tools like Process Hacker. Go to space 1, to memory, do refresh. And we see here we have an RWX, or read write execute region, with 128 kilobytes in its size. Don't see other RWX regions here. You can double click on it and we see MZ with some, all the data. can actually see different kind of M's that we see that we have only one R data section. In this space one that we actually research, we had two R data sections. So it's another indicator that is a different kind of code. So you can basically go and dump it. You can go with the flow here and see what it does. Just to make sure that we understand everything. So the F8, then it will check, do comparison of the value in AX, which is 45A, to validate the MZ header. And yeah, it is actually validate the MZ header. And we see that it's validated to the memory region of 5C0000, which is this exact memory region that we see here, which we can already dump. So then it goes and validate all of the other headers, like the P header that we see here. And just it checks that it's an actual decrypted P file. And it goes and allocates some memory. Now, see if it. Now we see another new allocated memory here. Don't see any content for right now. It will use the RTL move memory even several times. So let's check them. So it will basically now move chunks of the P file to the new memory region. Another RTL move memory. And if we go do reread, we'll see now it moved the P header and the other headers. And again, if we go to the next RTL move memory, and as you can see, it calls it indirectly. It basically calls the EDI register, which holds the pointer to the actual RTL move memory function. Do reread again, and now it actually copied the section stable, in this case text r data resource and reloc, and it continues, and eventually, now again if we do reread, now it will go and do a loop to actually copy all of the data. So we'll do F4 to basically get out of the loop. Let's do refresh. Go to this allocated region. And now we see basically we see let me just check if it's the same one, and our data NW, our data NW, yeah, it seems like the same. So it's basically the same payload. And now it will do call to the subroutine, which will do other stuff. Now, if we'll check procmon, whether it did something interesting till this point of the code, nothing interesting. So as you can see, procmon can help you a lot, but it really depends on what part of the code you're actually analyzing. So, trying to go through the code here. Let's see how many times it's called. It's called only once. Okay. Didn't go into this subroutine and understand what it does by each one of those code blocks, but it got some return values, like it popped some values into those registers and then saw some values like the MZ value there and stuff like this. Just an overview I did, and then it goes to this function, and here it actually goes and do get module handle, load library, seems as and get proc address to do dynamic API resolve from what it seems. So dynamic API resolve here. It's called like that. So basically, if I'll do F7 and get inside, just for the example, we'll do get module handle into kernel32DLL. It can either use get module handle or load library to load DLLs like kernel32DLL. And just continue. Then it goes for the get proc address to get the relevant Windows API function from the kernel32DLL. And of course, it'll go and loop and import more functions. Now I can do F2 here and F9. So see that it imports virtual frig, get short path name, open pros, get current pros ID, exit pros, and all of those functions. So this for the dynamic API resolve. Let me just get rid of this breakpoint. Do F4 to the return to finish the API resolve. F8 checks for the return value of 1 to see that it's actually finished. Okay, let me check what it is here. And to push this data, which is basically the target pros to be executed, which is this one, which is allocated here. And call EAX will jump us to a new loaded PE inside memory. So, and full-fledged PE was resolved from the resource section, or should I say loaded from the resource section as an encrypted blob. Then it was decrypted on runtime using XOR keys. There were new allocated memories, and another new allocated memory. Then it was moved to the other allocated memory. And of course, the P headers of the decrypted P were also validated, as we already saw in the code above. Just to show you, we checked all of those code blocks, and there were a dynamic API resolve, and now it will actually call this new PE file. Now, before we continue and do F7 to actually to get access to this code. If we do F8, we'll execute the this new PE code without us having the ability to inspect the code. So if we want to inspect the code and continue to reverse engineering, we need to do F7 and get into it. Before we go into it, let's dump the content. So we'll do save. And let's call it space 1 second stage. Now just to validate, we'll put it into an X editor. Seems like a clean P. A bunch of interesting strings, potentially. Let's put it into pbear to see if memories or different sections are aligned, so it will not be broken when we execute and analyze it. So we go to section headers, and it seems to be aligned. Or not. See all of those imports that are not resolved, they're broken. You can try to use this button here to resize and fit sections. Do yes. If we go now to imports, you don't really see it. Manage to help. So let's synchronize this value here, 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 here. Now we can see some of those Windows API functions presented to us. Okay. And basically, let's try to get like that. So that I can even do it the opposite way. Synchronize the raw address to the virtual address. The raw address is your address for the file system, or for the file in the file system, and the virtual addresses are for the loaded address in the memory space of the loaded process. Go to imports. Okay, now see all of the Windows API functions, and I don't see anything broken here. So now it's actually synchronized. So I synchronize the raw address into the virtual address. So now I'll do right click, save the executable as. Let's do it. Let's just like that. And again, just to validate for 200%, put it here. See the sections are aligned, the imports, and I can see all of those Windows API functions here. So I can basically go and do all of our analysis steps on this executable from scratch, or I can do F7 here and actually go start to analyze this code from here. And then I need to go and fix stuff here, and it'll be much harder to continue like that. It is possible, but we already found another way to actually do it. Basically dump the content here or from this memory region, fixed the sections alignments using pbear, and then we actually can see all of this Windows API function. So let's just stop the debugger here, save the database, Now we can open it up in IDA, in a new IDA instance. Let's see that we have a clean code to read. Now before we go, we have this check of load resources. Let me just check that if there is something interesting in the resource section. So I don't see any interesting thing in the resource section. I can just check hxd. So I see we have a resource section, but nothing interesting to show in resource hacker. Okay, something that can be checked. So let's check this load resources, because why not? And yeah, we actually see WinMain here, and if we could try to continue, see if there's, okay, just inspect the code, go to the imports, see we have all the functions here. Let's try to gather some strings. Yeah, we have visible strings to us. And yeah, basically this is what I want to show you for the float AMI sample. So thank you very much, guys. See you in the next video. Hello everyone, welcome back. In this video I want to show you how you can detect a malware using Yara. Specifically, we'll take the float AMI and basically detect it using Yara. So let's do Yara download. And as you can see, you already have in the Yara main page the syntax of Yara, which is very simple and straightforward. You have the rule name, the category that you want to put, it's optionally. Then you have three parts of the rule. You have the meta for metadata. You can put whatever you want in this part. You're the author of this rule, for example, the date that the rule was written, stuff like this. In the strings part, you put all of the indicators that you want to detect, whether it are hexadecimal values of assembly opcodes, strings, encrypted values, and stuff like this, and the condition that you want for the detection to actually, based on this condition, to actually detect the malware. You can use or, and stuff like this. Very simple and straightforward. And of course, there are more advanced stuff like using plugins like import PE to detect the presence of a PE file, using directive like file size to scan for files that are less than a specific file size, and stuff like this. So let's do download, and let's download the Win64 version and extract it. I'll put it inside the Flare folder here, create folder called Yara, and extract it. And try to do it like this. Copy it here. And now I want to access Yara from any path or place when I'm using this command line tool. So let me just change it to Yara without the 64. It will be much easier to use it that way. Let's take this path, go to this PC, right click, properties, then go to advanced system settings, environment variables, go to the system path variable, add new path, and do OK. That way I can use CMD and Yara from anywhere. So now let me go to the desktop, and before I, of course, using use the ER utility, I need to write the ER rule itself. So let me use Visual Studio Code in this case. Let me open a new tab and select the ER language. Now, I don't see the ER language because I need to actually install it. So I go to extension. Search for Yara. And I need to install it. Trust Workspace install. Sometimes you'll see that the workspace is actually restricted, so you actually need to click on it, do trust, and then you can use the arrow language. So let's write a rule. Let's call it load Amy, which is a rat category. Open and close. And let's do meta. Strings and condition. Those are the three parts or the building blocks of a YAR rule. And you just save it on the desktop with the .yar extension. Let me use the author date hash. Let's take the hash of this file. _1, hash my files. Take the MD5 or SHA-1. And let's define the strings that we want to use. So we saw that we have strings like all those Windows API functions. Let's sign Windows API functions that are basically part of the flow of Float Amy, and those are the 4 Windows API functions of the resource section: find resource, lock resource, load resource, and all of that. So let's do dollar to define a variable. Let's call it our resource C equals and actually take the other. So let's copy and paste it. So 1, 2, 3, find resource and find it. Load resource, size of resource, lock resource. Those are the 4 Windows API functions. And let's not use the W or even the A part of the Windows API function, because it can be changed between different variants of Float Amy potentially. So think of, like, for example, you have a different variant with the find resource A, and then you basically search for the W and you don't have the A, you can potentially do not detect this variant. So you need to be as much as generic as possible from one side with your detection rule, but not too much generic, so you will not fall for false positives. And you don't want to be too much specific, so you will not miss other potential variants of this kind of malware family. So those are for the resource Windows API functions. Let's try to find other stuff. Let's take all of those process names. Let's put them here for now and do proc name or EPP name, because those are for endpoint protection software. One, two, three, four, five, six, 7, 8. Okay, now that I put all of those EPP names, let's see what else we can take from here. To detect this variant and other potential variants. Okay, I want to detect the presence, whether it's a PE file, of course, so let's write another private rule. Private rule PE or is PE. I can also use the import PE plugin, but let's do something much simpler than that, just for the example. X or and let's detect the 45A value for MZ. Let's do X for the condition, and let's use this private rule as part of our condition of the float AMI tool or malware. So let's do ESP. So basically, if we will detect the malware or this signature will be true, or will find something in the malware, it will show only the rule name that is defined as a rule, but not the rules that are private rules. So basically what I mean is when I use the Yara utility and scan a file, you will not see the results of a private rule, only of the regular rules. So private rules are only used as part of a condition of regular rules. You will see what I mean when I scan the file. Okay, let's also define the directive called file size. So let's see what is the file size. So we'll not scan, for example, if we scan a full computer or a number of computers, we'll not scan all of the files. We'll scan files that are only PE, whether exe or DLLs, and they're less than a specific file size. In that way, we're optimizing our rule to not take too much resources from scan computers. Very important. So we see here we have 156 kilobytes. So let's do it less than 200 kilobytes, because let's do a bigger value so we can find also potential other variants. So let's do SPE and file size, or even let's start with the file size less than 200 kilobytes and ESP. So files will be scanned. The conditions for files to be scanned are for files that are less than 200 kilobytes, and there need to be a P file, XDLs, and so on. So now we can use those strings also as part of our detection. So let's see if we have other interesting strings that we can use potentially. Okay. Can even take the encrypted blob from the resource section and or something like that. So let's go to resource hacker. And take part of the encrypted blob. Let's say this part. See if we can detect it as a hex. So same blob. In this way, we can also detect hexadecimal values of assembly opcodes in the file. For example, if we want to sign a call of a Windows API function, not by its name, but by its assembly opcodes, can basically extract the hexadecimal values and put them here as part of the signatures. Like that. You can do it spaced or without spaces between the hexadecimal values, it doesn't really matter. So if you want to extract a hexadecimal value from a sample using IDA, for example, let's say you want, for some reasons, to sign those hexadecimal values as the decryption mechanism, for example, you can just go and do Shift E, and Shift E in IDA basically will give you all those hexadecimal values. You can do it unspaced or even spaced, and you can take and basically put it part of your YARL. So let's say the decryption routine and put it like this. You notice I didn't take the NOP or this XLAT opcode because they're not relevant. I did it only for the bypass, if you remember in the previous videos. So this is the decryption routine and encrypted blob taken from the resource section, and so on. All of those are APP software. And let's define in each one of those variables no case for no case sensitive, because if malware will try to change this to a lowercase q, for example, and will not use the no case directive here, it basically our signature can miss a variant or miss this sample. So we'll use the no case just in case. And the attacker will want to change it, those process names, to a lowercase in our strings. Now for the Windows API function, I don't really need to do no case, because if you basically call a Windows API function, it will be called in this way and not change like with, for example, it will not be with this lowercase r. Maybe someone saw something, a case like that, but I didn't really see a case like when you call Windows API function like find resource and then you have different like lowercase or uppercase. But if you want, just to make sure, you can also use no case in those places. Yeah, so let's now write a condition to include, for example, let's say, and all of resource rsrc and at least two of EPP name and let's say for now let's not use those variables, because if I'm defining a variable in the string section and I don't use them as part of the condition, Yara will throw me an error. So let's just focus on those variables for now. And now let's do a scan. So if I execute Yara, it will show me the command line arguments to use. So I'll do Yara. If I'll do Yara-R, for example, I can do recursive search or recursive scan on a folder. Or if I do Yara-R on the C drive, I basically can scan all the C drive or the Windows machine. And that way I can also check this signature, for example, for false positives. So if my signature will find legitimate executables, like detecting CMD and PowerShell.exe, it's a rule that you need to change. So yara floatamy this is the rule name, and basically the file name, which is space1.ex. So for some reasons it didn't detect the space1.ax, so we need to check why is that. Okay, so let's check it again. As we see, there is no detection of this rule, so it can be several reasons. Now if we go and search for all those strings that exist in the file, we can go and also test this private rule. Now, for example, if we don't think that this rule is right, so we can just remove the private of the rule, the private part, and just scan it, and you'll see that it's actually detecting that is a PE based on this condition. So you can put it back. So it's not a problem here. And if you test each one of the strings, it will try to change all the conditions, even if you do any of them. So even if one is true in one of those strings, it will basically, now we'll see that the rule actually catches space1, but it's too generic. If you do all of them, you will see that it doesn't catch anything. Kind of weird. So by my experience is only because sometimes the characters are different. They can be white character, Unicode, or ASCII and stuff like this. So we define here that two of the EPP name at least need to be detected as part of the FlowDAMI malware, the space one exe. So let's try to put the type of the string as ASCII, at least in two of them. You see that it doesn't really help, but if we'll put wide, now you'll see that we actually detected it successfully. Sometimes you'll see weird stuff, but experience, you will learn some stuff. So let's use this wide directive and all of those rules. Now let's test it again, and we have a detection rule for this sample of FlowDAMI. Thank you very much, and see you in the next videos. Hello everyone, welcome back. In this part of the course, we'll go through analyzing some malicious documents. So this specific video will be a short introduction. So the goals of threat actors in using malicious documents is to basically infiltrate into organizations. Most of the attacks will start as a phishing attack, whether it's a whaling or a spear phishing to a specific high valuable person in the organization, or even a spam that will send to to a lot of organizations and a lot of people in different companies. So if we take, for example, Emotet, they send a spam hell of emails, a lot of emails, and basically the ones that are falling victims into it by executing the attached files. It can be a VBA macro Word file, or an Excel with an XLA macro, or a PDF with a JavaScript, or whatever. I'm talking here in general, yes. Emotet most of the time they use a simple Word file with some VBA macros inside, and it still works, which is kind of a problem. So the first thing is to infiltrate organizations, steal sensitive information, evade detections, of course, harvest money, credit card information, and even encrypt files and stuff like this. Some of the exploitation methods used by the attackers. So first of all, user awareness. You still have a very low user awareness among companies in the world. I personally go to a lot of companies and do a lot of awareness training, and one of the most amazing thing that I noticed that actually when I show the behind the scenes of how those phishing campaigns are built and how those malware are written, like let's say I show some of the technical aspects and the psychological aspects and the decision making behind those stuff, then people actually realize that they need to be more careful. Because if you come and talk in general about what is a phishing email and what type of phishing attacks there are, it's annoying and very it's not fun. And basically whenever you do a phishing training, you want to get people to know this and to understand why it's a problem. This is why even in this video I'm going out of track and I'm talking about phishing, because it's a very big problem in our industry. And a lot of people think, yeah, I'm fine, I know what I'm doing, and I'm even if I'm, a lot of those technical people in IT, and even if in security, they think that yeah, I'm okay, I'm a security expert, I will not fall into it. But everyone will eventually fall to a phishing in some point of their cybersecurity lifetime. So if you're a security expert and you want to go and actually teach people how to be aware, show more practical stuff and even simulate a real phishing attack in front of their eyes, in front of the audience. so they will understand the impact and they'll be in shock. And I do that, and I'm doing this all the time, and it actually works. Um, so user awareness, phishing, all of those attacks, or most of them, should I say, are stage-based attacks. So the first stage is attached file or a link. The link can be an exploit kit, which basically, you have all bunch of redirects whenever you click on the link, and one of those redirects includes some kind of a malicious JavaScript code which exploits a vulnerability in your browser and injects some malicious code into your computer without you noticing, or basically double click on an attached file and run malicious code in your computer. And those Word files with VBA macros and XLM macros in Excel, and they have direct and free access to Windows API functions. So let's say we send a malicious document attached in an email. You double click on this Word file. It can be a doc, docx, xls, xlsx, and whatever. It executes a PowerShell code. It's actually an Emotet sample. It runs an encoded script in base64, downloads a file from a remote server, and executes the file. That's simple. Here you can see all the execution kill chain in a different view. And one of the things that people don't understand, that VBA macros, while they're very legitimate and used in different organizations, they have the ability to access Windows APIs like any other language, like C and C++, and C#, etc. So what kind of malicious document file types are there? So of course there's MS Word for VBA macros, PowerPoint, Excel with Excel 4.0 macros or XLM macros, and even PDF with an embedded JavaScript. Today I see PDFs with like PDF exploits with embedded JavaScript less and less, but there is always a chance that they will be a comeback for PDF exploits like in the past. And there are some common malware in the wild that use such methods like Emotet, Drydex, Agent Tesla, APT12, APT28. We even saw already Flawed Amy, whenever we actually analyzed the pickup in the previous videos, we actually, by analyzing the packets, we understood that the first stage of the attack was an Excel macro file double clicked by a victim, and all of the other attack chain was executed. More CMD and PowerShell, which eventually downloaded another executable file, and then actually reverse engineered this executable, and you saw all of this in the previous videos. All of that started with a simple Excel file attachment. So thank you very much, and see you in the next videos. Hello everyone, welcome back. In this video we'll do a small introduction into analyzing PDF documents. So let's talk about some indicators. If you see a PDF with an embedded JavaScript stream, it is a sign that something is off and it's something that it needs to be examined. Now there are some cases that JavaScript is legitimate in PDFs, but something can be potentially off and you will need to take a look on it. If there is a use of shellcode in a PDF, it's very problematic. If you see any execution of OS commands or again shellcode or something like this, it's another indicator. If you see connections to IP address and domain names, and if you see the use of flayed encode or flayed decode in PDF analysis tools, it's another indicator. PDF is basically built in like other file structures, but let's say you have an object, you have the file structure, and you have then the document structure and the stream of the content. So basically you have the PDF header, the body, and basically all of the other building blocks that building the PDF. So if we analyze a PDF with tools like PDF stream dumper, PDF ID, etc., you'll see, for example, something like this stream. So this stream of data can be something like a picture, it can be a text, or some other hexadecimal value. Tools of the trade, which can be used in analyzing PDF. It's again hex editor like HXD, PDF ID to check whether there is a presence of JavaScript and stuff like this. PDF stream dumper, which is a great graphical user interface tool. PDF parser, PPDF, SpiderMonkey, which is basically an emulator for PDF. It can emulate PDF files with JavaScript and so on. And also Remnux VM has a lot of other tools like PPDF and PDF parser and PDF ID built into them. So see you in the next video. Hello everyone, welcome back. In this video we'll go through analyzing a PDF file which is malicious. So we have a PDF file here which is 6.49 kilobytes. If you double click on it, see a blank page. Now in PDF exploits, it's very well known that in order for a PDF to execute a malicious code, if it's a OS command or some kind of an injected shellcode, it needs to exploit a vulnerability in the specific PDF reader. So let's start with using a tool called PDF ID. Go to desktop and do PDF ID on Notice PDF. Now see that we have 6 objects, 1 stream, and we actually have 1 JavaScript. Now, most likely if we have a JavaScript, especially with the open action, which basically executes the JavaScript, something that we need to analyze. So now let's put it inside PDF stream dumper, PDF stream dumper. We do load PDF file, notice of PDF. So as we saw, we have 6 data streams. So if we go to the first one, we see that it has an open action to 5. If we go to 5, we'll see that basically it calls for an action of JS code in streams number 6. So if we go to stream number 6, you can see a variable defined here with some characters, which is what can understood here. It's basically some characters which are eventually decoded to be a shellcode with some unescaping characters, and eventually this shellcode will be injected into the memory after the vulnerability will be exploited using this util printf. So it's a very old PDF exploit that exploits something in the util printf using those characters, and by exploiting this vulnerability it injects this shellcode. Another cool thing in PDF stream dumper is you can use many features. For example, if you do exploit scan, basically it will scan the code for known vulnerabilities or exploits. So as you can see here, it actually found that there is a vulnerability from 2008 and is exploiting something in the util printf function. Now we can go and read about the CVE, what it actually means, and so on. So also you can go and use the JavaScript UI, so you can have easier way to decode and understand this code. You can even go and select this, shell code and try to unescape it, unescape selection, and try to see what you can do with it. And you can even use scdbg for shellcode analysis. To actually try and see if you can debug the shellcode in some way. And you have other tools like zlib or basic-c4 decoding and stuff like this. So this is a very straightforward and basic overview of how you can analyze PDF exploits. And yeah, there are not for now in the wild, you don't have a lot of PDF exploits. In the past, you had a lot of them, but there is always a potential that they will rise again. So it's very important to know at least the basic tools to how to analyze such PDF files. Thank you very much, and see you in next time. Hello everyone. In the previous video, we talked about analyzing malicious documents in general. In this specific video, we'll do an introduction into analyzing VBA macros, and in the next video, we'll actually go and analyze one. So, some VBA indicators to look up when you research VBA macro-based files like Word documents. So, if you basically open up a Word file and it asks to enable content, you have this enable content pane colored in yellow, so it is probably using VBA macro. Doesn't really say that it's malicious, but an indicator. If you see VBA strings seen in hex editor like HXD, if you see VBA strings seen in package extractors like 7-zip, RAR, so basically if it's a docx file, for example, which is basically a compressed version of a Word file, like let's say Office documents, or like Excel and Word and PowerPoint, ending with the X extension like PPTX, XLSX, docx, are basically a compressed version. So if you put them into an hex editor, you'll see the magic number of PK. It's like the magic number for other compressed file types. Like, for example, if you take an APK package for Android applications, you will see a PK in the start of the file. And whenever you inspect the magic number in a hex editor, for example, so you can actually open up those file types like docx, pptx, xlsx, which are compressed files inside package extractors like 7-zip, rar, etc. And if you see the lowercase or especially the uppercase M indicators while using OliDump, it also shows you the stream data or the stream location of where actually VBA macro is in the file. So for example, if I open up, you can see in the left screenshot here, if I open up docx file, for example, with VBA macro, I will see something like VBA project.bin or VBA data. So it's a great indicator for you. And if I'll use tools like OliDump and basically on a docm or docx file, it will show me the streams of the file. And in this case, I can see an uppercase M on the file. So it's an indicator that the A3 and A4 streams, including a VBA macro code. And the difference between uppercase M and lowercase m is basically that the uppercase M is basically a VBA macro code which is actually executed, while the lowercase m is not an executed macro code, basically. So tools of the trade that you can use while researching malicious documents, or specifically VBA or XLE macros. You can use a hex editor, of course, package extractors. You can use only VBA to scan for malicious artifacts. You even have this dash deob for the obfuscation. Sometimes it can be useful, sometimes it doesn't really help you. It really depends. You have Office Mouse Scanner and only dump, and you have even Viper Monkey to emulate and run the VBA macro. You can even extract, for example, base64 encoded data and stuff like this while emulating this VBA macro. And there is another tool called Evil Clipping with a -UU to actually unlock protected documents. So attackers sometimes saw Dridex, for example, the Dridex malware at the time. They like to use Evil Clippy to lock documents, and basically you can unlock it use Evil Clippy to basically unhide sheets and inside an Excel file and stuff like this. So this is regarding this video. See you in the next video, and where we actually analyze a malicious document. Hello everyone, welcome back. In this video we'll go and analyze malicious Word document. So let's start by inspecting it inside an X editor, and we see that we have the D0CF magic number, which is the magic number for a Word.doc file. If it were a docx file, we're using the PK magic number. Yeah, so now we can go and try to open up it as an archive, and if we go to this folder, we have this macros and actually VBA, and yeah, so as we can see, this is a file weaponized with VBA macro. It can be potentially also legitimate, but in this case it's actually malicious. Now let's use a tool called only VBA. Let's go to the desktop, only VBA, and agreement. We'll basically take the macro code inside and analyze it. So it actually found that some suspicious code is actually used here, and there is what's called an auto execution mechanism with the auto open command to actually execute the malicious VBA macro inside. And basically this is the extracted code. You can actually go and use only dump to dump this code, only dump and agreement, and we see that the actual code is in stream 8, which is with the uppercase M. So basically it indicates for us that this code is actually is an actual executed code, because lowercase m, it's a VBA macro code, but it's not actually executed. So let's do only dump -v for decompression, -s for stream number 8, agreement, and let's output it to 8.bin.txt. And basically we extracted the code, so we can open it up in Visual Studio Code. And select the VB language. I can go and analyze the code. So basically it's kind of straightforward. We see that Windows API functions, or 4 Windows API functions to be exact, are imported from the kernel 32 DLL. And basically it is checking whether it's VBA 7, and if it's not VBA 7, then it basically imports the Windows API functions. So basically it's for versions, so it checks if it's VBA 7, and for the other VBA 7 versions, it basically does the same. So basically it calls or renames all of those functions and gives them some kind of what's it called, naming. So whenever you see create stuff used in the code, it will basically call create remote thread. So it's like a nickname for the create remote thread, and alloc stuff will use virtual alloc. So if you actually take create stuff, you'll see that create stuff is actually using the parameters of create process, which is 1, 2, 3, 4, 5, 6, 7. 7 parameters for create remote thread, virtual alloc, which is for alloc stuff. And basically, you can see that basically from what we see here, it seems like a process injection is made here. So there is actually a process created, a process, legitimate process of run dll to exe, and to this process actually new memory is allocated. This shellcode is injected, and then basically the create remote thread function is basically used in order to basically execute this shellcode. Okay, so this is regarding using only dump to extract code. So we can basically close it up, and if we double click on it, can actually go here into view macros, and do edit on the auto open, and we can see the same code here. And we can go actually put some breakpoints and watch stuff like this. So we want to toggle a breakpoint, we can use F9. So let's put an F9 for run stuff, RWX page for alloc stuff, and create stuff. So, and also for the my array, and let's execute it. In order to execute it, we need to do actually enable macros. So, or enable content. Let me just use process hacker before I actually do it. And just let me just exit it right away. And terminate tree, and then again agreement. Terminate tree. Let me go to view macros, put a breakpoint here, and breakpoint will create stuff. I think it's enough. You can do also an RWX page, and yeah, so, and run stuff for the spawning of run dll to exe, do execute. So now basically hit the breakpoint here, and we can also do watch points. So we can go and do add watch, and add a watch here. Actually, so we can see each one of those variables with assigned values. So for example, we go debug here and do step over, and now my array actually has all of those, all the loaded shellcodes, and that way we can actually inspect values inside variables when we debugs, VBA macros. So basically now what we'll do, go to process hacker. So for now we don't see any child process created because we didn't get to the point of run stuff. So now let's do play. Now we're in the run stuff. So again, we don't see anything. Now if we do play again, now it's actually created the run dll to exit with this as suspended. So if we go to general, we'll basically we'll see that basically and now suspended. If you go to threads, see that everything is suspended. So basically it was created with the create process with the flag of flag number 4. in hexadecimal, so it's basically with this create suspended flag. And now if we basically go to the memory of this process, do refresh, we don't see something very interesting here. So now if we do play and go here and do refresh, now we're seeing new memory region was allocated with the read write execute for now. And basically also the function of write stuff is already executed. I didn't put a breakpoint on it, so it's already executed. So an allocated memory with RWX permissions and the write stuff, which is the write process memory function, actually was used to actually inject this shellcode. And we can even see some kind of an email here. Okay, so we can actually go and dump this shellcode dynamically, or we can even take this and put it into CyberChef and do some kind of decoding tricks statically and then write it to a file and stuff like this. And basically that's it for that. So if we now actually go and execute create stuff or create remote thread, we'll actually go and execute shellcode. Okay, so try to see if it tries to connect to some kind of place or do something, but basically let's go cross explorer. So basically we have run the editor to exe process with injected code, which tries to basically in the end of the day it's a interpreter shellcode which will try to communicate back to some kind of a C2 server. So this is how you can inspect it dynamically. Now if I want to decode it statically, in this case I can just take this shellcode, go to CyberChef, and do from decimal, put it here. Now we have this problematic spaces here, so let's just remove them. Let's clean them up. So each one of those itsy bitsy parts, let's do Control H for replace, remove them all, and take the clean version and put it here. And the delimiter here is not space, actually comma, and support signed values, because actually you have two things. You have unsigned values, which can be only regular numbers like 10, 40, 56, 5, 7. It can be what's so called positive number. And signed values can be either positive values like 10, 12, etc., or negative values like -4, -5, etc. So in this case you see negative values, so that's why you need to take the support sign values. So now if you take and copy it, copy this value. So now for now it seems like gibberish, but you see there is some kind of string here. So if you copy it, or before we actually copy it, you can validate it by do to hex, and now you can actually see this FC E8 seems like a normal assembly opcode. So if we go to process hacker and run the alternative to exe, which still is running, and RWX, see that is the same opcode as you see here. You can go and do even disassemble x86 if you want to extra validate it and see that it actually translates to logical assembly instructions. So basically you can take this hexadecimal values like this and go to desktop and basically, or just, just take it hxd, create a file like this, paste it like this, save it, code.min, and you have the shellcode. And you can try to analyze it in different ways. You can even use tools like shellcode to exe and then put it in IDA and stuff like this. So thank you very much. See you in the next videos.